one good thing about probability theory is it says that there is certain probability with which everything will happen. So whatever you are trying to do, you will definitely be able to achieve it with certain probability. And if you want to increase the probability of success, later I'll show you with some examples that if you increase the number of attempts, even the probability of success will increase. Okay, so anyway, in order to understand this theory, probability theory, you are supposed to understand certain terms. So first what I'll do is I'll try to introduce you to the terminology that we are going to use in this subject, and then using examples I'll make the concepts clear. So in this particular subject, instead of talking about the theory, even though it is probability theory, we will be talking mainly about the examples, and then using the examples I'll explain you all the concepts. It is not that I'm going to give you just the definitions. Definitions are never useful in this subject. We'll just stick to as many problems as we can, only the problems. Okay, so first let's talk about the basic terms which will be useful in this. So one basic term that will be useful in defining anything here is random experiment. So what is a random experiment is, for example, if you take a coin and if you toss it, the outcome may be head or tail, but what it is exactly going to be, we don't know, right? You can term such an experiment as random experiment. So what an random experiment is, in simple words, we'll be knowing set of all possible outcomes, but we don't know in advance what is the outcome we might get. That is called as random experiment, and all the events that might occur are equally likely. Okay, so what is a random experiment? We know all the set of outcomes, but we don't know what is the outcome that will come in advance. It is just like tossing a coin. So for example, I'm just taking just few examples, right? So for example, tossing a coin is a random experiment, right? And similarly, you can think of dice, rolling a dice. Rolling a dice is a random experiment, right? And similarly, you can think about picking an object from a collection. Picking an object from a collection without looking at it. For example, if we have a basket in which we have 10 red balls and 10 white balls, and if we are trying to pick one of them without looking at them, then we don't know which ball we might pick up, right? So that is nothing but a random experiment, but we know that we will get either a red ball or a white ball, which means we know the set of outcomes, but we don't know exactly which one we are going to get as the outcome of that particular that instance of the experiment. That is called as random experiment. And after knowing about random experiment, the next thing is, for each random experiment we'll have something called as sample space. Sample space. So what is a sample space is, set of all possible outcomes of an experiment is called as sample space. For example, if you say that experiment is about tossing a coin, then what is set of all possible outcomes? Then sample space is nothing but either you will get a head or you will get a tail. Right? So why are we doing this? All this is convention. That is, these are the conventions that we follow, so that later when you are talking about some problem, even the questionnaire, he will use the same terminology, and also we will understand what do they mean by sample space and all. So it is better that you know all of this now. And then sometimes they will say that instead of using this sample space, they will use the name sample set, right? Or they will use the name domain space, something like this, but then they are going to explain you. So in most of the textbooks they are using this term sample space, most of the textbooks. Let us say you are trying to roll a dice. Then if you are told you are trying to roll a die, single die, then how many outcomes are possible? 1, 2, 3, 4, 5, 6, isn't it? Now let us say you are trying to toss 2 coins, then how many outcomes are possible? So when you are trying to toss 2 coins, now the outcome could be either head head or head tail or tail head or tail. Similarly, if you are trying to roll 2 dice, then outcomes will be one die is going to give you 6 outputs, and other die is also going to give you 6 outputs. So 6 into 6 is going to be 36. If you try to roll 2 dice at the same time, then we may get 36 outputs, right? 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, so on till 6 6. 36 outcomes we will see. And if you observe this, these are all countable number, right? For example, here if you are seeing it, it is nothing but a countable set, and the events are discrete points, which means we have head and tail 2 points, right, and 6 points, like that. But sometimes we might even have a continuous sample set. What is a continuous sample set is, let us say the experiment is about finding out the lifetime of a car. Now when you buy a car, how many years is it going to last? It might immediately be, it fail immediately and it will not run. It doesn't happen in the real world, but still, so it might have 0 lifetime, or 1 year, or 2 year, or it might last forever, isn't it? Just an assumption, nothing will last forever, but in this theory we can go about like that. I'm just giving an example. So in that case, the lifetime of a car, let's say S5 is the sample space for the experiment where we are trying to find out the lifetime of a car. Now lifetime of a car can be 0, or it can go to till infinity. It can be any number from 0 to infinity. Got it? So simple. See, let's keep the thing simple. What is random experiment? We know set of all outputs, but we don't know which output will be the next output. That we don't know. That is a random experiment. And what is the sample space? It is set. See, again, sample space is nothing but a set. This word is important. Why is it important? I'll tell you. Sample space is set of all possible outcomes, right? And this is an example. And the next thing is, we define something called as an event. An event is nothing but any subset of the sample space is an event. For example, if you are tossing one die, there can be an event. You are interested in event of getting heads, then you can define the event as H, right? See this, if the sample space is head and tails, and if you are interested in knowing about the event of getting heads, then we define the event E as H. And if you see this, E1 is a subset of S1, which means once you define the sample space, then we define the event as a subset of the sample space, right? And what about if you are trying to roll dice? If you are trying to roll a die, then maybe if you are interested in getting an odd number or even number, that is an event. So for example, E2, which is a subset of S2, because we are now interested in rolling a dice, that is the experiment, and this is the sample space. And now my event of interest is getting an even number, right? It has to be a subset of this. So what is even number? 2, 4, 6. So E2 is a subset of S2, which is called as an event. And similarly, let's talk about this one. Let us say we are trying to toss 2 coins. We are trying to flip 2 coins, and now while flipping these 2 coins, I want to know about the event in which I'll get at least one head. Then what will be that event? Let's call it E3, which should be a subset of S3, right? And now let's say I want at least one head. So how can I define it? So HH will contain at least one head, or head tail, which means, see, this is head on first coin and head on second coin. This is head on first coin and tail on second coin, or tail on first coin and head on second coin. So this is the event in which I have at least one head, right? So that is how you can define it. Now when you are rolling 2 dice, let's say I want to find out all the events in which the sum is a odd number, right? Or let's say the sum is equal to 3. So what are all the outcomes that will result in a sum 2. So when I'm rolling 2 dice, so if the sum has to be 3, one die has to give me 1 and the other die has to give me 2, or one die has to give me 2 and the other die has to give me 1. So these are the two points that we have to have in this event. And again, if you see this, E4 is a subset of S4. And similarly, when you're trying to find out the lifetime of a car, let's say I'm interested in the event where the car's lifetime is at least 6 and at most 3, at least 3 and at most 6 years, like this, 3,6. So this is actually a subset of this. So again, it is an event. So what is it? We defined a random experiment, and then we defined a sample space, and then we defined a event. That is what we did. And now if you again see this, one important interesting thing here is event is also a set. Even though it is a subset, it is still a set. So what is sample space? It is a set. And what is event? It is a set. Therefore, we are going to apply all the things that we have learned for sets again here. So for example, we might apply union of two sets, we might apply intersection of two sets, and we might apply complement of a set, right? So which means like this. See, now let's say we have defined an event, S1 is the sample space, and we have defined an event of getting a head as this, and an event of let's say E6 getting a tail as this. Now what is E1 union E6? E1 union E6 is nothing but either this or this, which is head comma tail, right? What about even intersection E2, right? So if you think about these two events, and if I take the intersection, there is nothing in common, then we call it as a null set, represent with 5. Now the interesting point about this 5 is, whenever you have two events in such a way that their intersection is 5, then they are called as mutually exclusive events. Mutually exclusive means nothing in common. They are called as mutually exclusive events, right? So don't get confused with the term independent events and mutually exclusive events. Independent events are completely different. People generally think that if nothing is common, then they are independent. No, it is not that way. So independent events are completely different, which we'll see later. But for now, stick here to mutually exclusive events. What is mutually exclusive? If you are having nothing in intersection, then they are called as mutually exclusive events, just like mutually exclusive sets, right? And similarly, you can define complement of a event. For example, if you see E1 complement, if you say this, E1 complement is nothing but S minus E, where S is the sample space and E1 is the set. So what does it mean? E1 complement is nothing but set of all points in the sample space that are not in E1, right? For example, if you are having a sample space as S2, right, and the event E2 is defined on it. Now what is E2? It is set of all even numbers, isn't it, which are possible on rolling a die. Now if I say E2 complement, now what does it mean? From the sample space S2, you remove the points which are present in E2, then whatever are remaining, then we are going to use them. So what are remaining? 1, 3, 5. So this is nothing but set of all odd numbers, right? So E2, if it is containing set of all even numbers, then E2 complement is going to contain set of all odd numbers, right? So just try to understand all these concepts. Now these concepts are going to be used throughout this theory. Throughout the probability theory, I am going to use what is the sample space, what is the event, right? And then the next part is how to apply or how to assign some numbers which are called as probabilities to the events, right? How to apply the probability for the sample space and how to apply some numbers to the events, that we'll see now. Okay, see this. Now we know what is a sample space and what is a event. So sample space is set of all possible outcomes and event is a subset of sample space, right? And then we can even go further and define types of events like simple event and compound event. If an event contains a single point in the sample space, then that is called simple event. And if an event contains a combination of points, right, or if an event is a union of two or more simple events, that is called compound event. But anyway, these definitions are too much in detail and they are not required. So let us assume that E is an event, some event which is a subset of the sample space. Then what is probability of E is, it is a function or it is an assignment of a number to this event. Okay, so I'll just take an example and then I'll tell you this definition, what probability is. So let's say we are having a die, or let's say we are flipping a coin, and the coin can give us either head or tail. Assume that they have used the word equally likely, or they have said that it is a fair coin. Fair coin means it is not biased. The probability of getting heads and the probability of getting tails is equally likely. Okay, now assume that that is the scenario. Then since we have two cases, two possible outcomes, then what is the possibility that this outcome will come up? It is 1 by 2. And what is the probability that this output will come up? It is 1 by 2. Therefore, to the event of getting a heads, I am assigning, let us say this is the event E, I am assigning the probability 1 by 2. Similarly, to the event of getting a tail, right, let's say E2 is the event of getting a tail, I am assigning the probability 1 by 2. That is how we define the events, and then we assign some numbers to them, right? And let us say we are conducting the experiment in which we are actually flipping two coins. If you are flipping two coins, we know what are possible outcomes. Both can be heads, or one can be head, the first one can be head, second one can be tail, or the first one can be tail, second one can be heads, or both can be tails, right? So in this case we have totally 4 possible outcomes, and assume that all these outputs are equally likely, which means the coins are fair. Then we can assign the probabilities of 1 by 4 to this event, and 1 by 4 to this event, 1 by 4 to this event, 1 by 4 to this event, right? Now what are the probabilities we can assign? So what are the rules that we should follow when we are assigning these numbers called probabilities to the events, are given by these rules, right, or explained by the probability theory. See this: for each event capital E in the sample space capital S, we assign a number P of E. P of E means probability of E, such that 0 is less than or equal to P of E is less than or equal to 1, which means always remember probabilities should be a number which should be less than or equal to 1, which should lie between 0 and 1. It can be either 0, or it can be either 1, or it can be any number in between. And the next one is P of S equal to 1, which means if you add all the probabilities assigned to individual points, you are supposed to get 1. See this: 1 by 2 plus 1 by 2 is 1, and here also 1 by 2, 1 by 4 plus 1 by 4 plus 1 by 4 plus 1 by 4 is 1. And the next one is, for any sequence of events E1, E2, so on En, that are mutually exclusive, the union of these events probability is nothing but sum of all the individual probabilities. So the last point is simple. See this: assume that we are flipping two coins, and let us define event E1 as an event in which we get both the coins as heads. Both the flips we want them as heads. Now what about P of E1? P of E1 equal to 1 by 4, right? And assume that we define one more event E2 in which both the coins have turned out to be tails. Now what can we define about P of E2? P of E2 is 1 by 4, right? Now assume that we are defining an event in which a new event E3 in which both the coins should show the same output, which means both of them should show heads or both of them should show tails. Now what can you say about it? It is nothing but E3 is E1 union E2, which means either E1 has to occur or E2 has to occur. Now if you observe these two events, they are mutually exclusive. I told you already about mutual exclusive, right? So two events are said to be mutual exclusive if the intersection is 5. So there is nothing in common between these two events, therefore they are mutually exclusive. Now whenever you have mutual exclusive events, now the third rule is saying that whenever you take the union of mutual exclusive events, the probability of that compound event is going to be sum of the individual probabilities. So which means in this case P of E3 happens to be P of E1 union E2, and since these two are mutual exclusive events, we can write P of E1 plus P of E2, that's it, which is nothing but 1 by 4 plus 1 by 4, which is 1 by 2. These are the basics. Okay, we'll slowly get into complicated questions, but let's go with the basics. I think you must be knowing about all this, right? So, and the next thing is, what if they are not mutual exclusive? Sometimes they might not be mutual exclusive, right? Then what should we do? See this, what I mean to say is, if this is the sample space, right, and if you have two events like this which are completely disjoint, right, mutual exclusive, then the probability of the union of these two is nothing but sum of the individual probabilities. But it might so happen that the events might not be mutually exclusive all the times. There might be something in common, right? They are not disjoint. In this case, let us say this is E1 and this is E2, right? Then if I want to take the probability of E1 union E2, then it is not simply E1 plus E2. The reason is this: you have various regions here, 1, 2, 3. Now when you try to take E1 union E2, see this, E1 union E2, there the regions will be 1, 2, which will be from E1, union 2, 3, which will be from E2. If you look at this, the total probability has to be 1 plus 2 plus 3, but here we get 1 plus 2 times 2 plus 3. Therefore, what we should do is we have to subtract 1 time 2, got it, which is nothing but E1 intersection E2. So in this case, what happens is we have to, probability of E1 union E2 has to be probability of E1 plus probability of E2 minus probability of E1 intersection E2. Are you getting why am I subtracting this? Because when I just add these two, I am going to add this intersection part 2 times, right? And since we are adding it extra, I am just going to subtract that extra part. Therefore, the resultant is just going to be 1, 2 and 3. There are only going to be 3 areas or 3 regions, got it? So now the ultimate aim is, okay, let's do one thing. Let's try to take an example and see how that such kind of model can be implemented in practice. So assume that we are defining an event E1, a new event E1, as an event in which the first coin is going to be head. Okay, the first coin is going to have heads. So then E1 is going to be head, head and head tails, got it? And let us define one more event E2 in which the second coin is going to be heads. So here second coin is going to be head in this case, as well as second coin is going to be head in this case, right? Now let's define one more event E3 as an event in which we get at least one head, right? So now that head can be from the first one, or it can be from the second one, or it can be from both. Now we can clearly know that if you have to have at least one head, these are the 3 possibilities. So which is nothing but E1 union E2, isn't it? Now clearly here E3 equal to E1 union E2. Now if you try to find the probability, now probability of E3 equal to probability of E1 union E2 is equal to probability of E1 plus probability of E2 minus probability of E1 intersection E2. Why am I doing this? Because they are not mutually exclusive. The reason is, you can see that the intersection of E1 union E2 is not equal to 5. There is something in intersection, right? Now, what is the probability of E1? The probability of E1 is 2 by 4, which is nothing but 1 by 2. What is the probability of E2? Again, the probability of E2 is 2 by 4, which is nothing but 1 by 2. So probability of E1 is 1 by 2 and the probability of E2 is 1 by 2 minus what is the probability of E1 intersection E2. The E1 intersection E2 contains only one event, which is HH, heads and heads on both of them. Therefore it is going to be 1 by 4, right? So you are going to get 3 by 4, isn't it? Now even if you count it, we have 3 events and therefore 1 by 4 plus 1 by 4 plus 1 by 4, which has to be 3 by 4. Either from this formula or from this counting, you are going to get the same answer, 3 by 4. And this method can be extended not just for 2 events, it can be extended even for more than 2 events, right? For example, if you have 3 events which are not mutually exclusive, like this, if you have 3 events and if you want to find the probability of union of these 3 events, then how can we do it? Same, you can do, just like in set theory, how you did it, you can apply the same method here. P of E1 union E2 union E3 equal to P of, you can take single terms and add them, E2 plus E3, and then you can take 2 terms and you have to subtract them, minus P of E1 E2, E1 E2 means E1 intersection E2, minus P of E2 E3, which means E2 intersection E3, minus P of E3 E1, it is E3 intersection E1, plus P of E1 intersection E2 intersection E3. Got it? So this is how we can extend it even to any number. Even if you have E1 union E2 union E3 union E4, generally that question will not be asked because it is going to be very lengthy, but still you can remember it. If you have E1 E2 E3 E4, then single terms you add them and double terms you subtract them, and then triple terms you add them, and then triple terms will be more, it will be 4C3 terms here, and then again 4 terms you subtract it. So alternatively you keep adding and subtracting the terms, right? So it can be extended to any number. So now what are the things that you should remember here is, whenever you are trying to take the union, you have to see whether they are mutually exclusive or not. In most of the cases they will give you in the exam whether they are mutually exclusive or not, otherwise you are supposed to find it out. Once you find out that they are mutually exclusive, you are supposed to add them. If they are not mutually exclusive, you have to subtract that intersection term, right? And then all the other set theory notations can be applied. For example, we know that, see, one thing is here, same, we know that the probability of the sample space is always 1. What does it mean? One of the elements present in the sample space will always show you as the output. That is the meaning of it. See, try to understand this. P of S equal to 1 means it is always possible that you are going to get one of the elements which are present in the sample space as the output, which means sample space is definitely going to happen. It is certainly going to happen. So whenever you have 1, it means it is certain, it is definitely possible, right? See, if you take an exam, then what are the possible outcomes? Either you fail or you pass. Then I can say that the probability that you either fail or pass is going to be 100%, isn't it? But the probability that you fail or the probability that you pass individually is not going to be 100%. That depends on various factors, right? So this means that the probability of the sample space is very certain, right? And now in the sample space, if you have the sample space, if you have an event E like this, then the other part is going to be E complement, isn't it? Now these two are mutually exclusive. Are you getting this? There is nothing in common between the event E and the E complement. Therefore, I can write, yes, I can write S equal to E union E complement. Are you getting this? Now this entire S, the sample space, can be written as E union E complement. Now I can take that, if I apply probabilities on both sides, then what can I get? Probability of S is equal to probability of E union probability of E complement, and we know that these two are mutually exclusive events. Therefore, what should we do? When they are mutually exclusive events, we need not subtract anything, we have to just add their individual probabilities. So probability of the events S is equal to probability of the event E plus the probability of E complement. Now we already know that probability of S equal to 1, which means S is definitely going to happen, certainly going to happen. Then what can we say about probability of this is E plus E complement, right? Now what can we say about probability of E complement? Probability of E complement is going to be 1 minus probability of E. Therefore, assume that they have given you the probability of an event happening. Then what is the probability of the event not happening? It is nothing but the complement, which is 1 minus this. For example, let us say if you are taking an exam, the probability that you pass the exam is 0.6. Then what is the probability that you fail the exam? It is nothing but the complement of it, which is 1 minus 0.6, which is 0.4. Got it? So these are the basic things about probability. Later we one thing, we are never interested in this whatever I told you, we are never interested in this. Maybe if you get a 1 mark question, you might get it sometimes, but then what is rather interesting is a combination of the original sample space as well as the new sample space. Okay, I'll continue in the next video what is important, that is called conditional probability. So once you understand all these basics, now I'll move on to the conditional probability. Okay, fine. Now let's assume that we are rolling a die which is a fair die, which means any one of the 6 outputs 1 to 6 are equally likely to appear as the output. So in that case, what will be the sample space? The sample space S is going to be 1, 2, 3, 4, 5, 6. All these 6 outputs are equally likely, right? And now how are we going to assign the probabilities? Already we have seen that when there are 6 events and if all the events are equally likely, we are going to assign the probability of 1 by 6. Now how did we do that? See, let us assume that E is an event of getting 1 as the output, right? And if you want to find out P of E, some of the authors will also do this. It is not exactly right, but it is only applicable for the finite sets when S is finite, and discrete events. Discrete event means non-continuous, right? So for such kind of system, you can even think of it this way. P of E, probability of E, is nothing but number of elements in E, n of E, divided by number of elements in S, cardinality. If it is possible to count, we can go that way. In case of continuous, let us say we are talking about the lifetime of a car, then the lifetime of a car can be anywhere from 0 to infinity. It is a continuous system and we will not be able to count the number of points, but then in this case we will be able to count the number of points. Therefore, some of the authors, they even will try to assign it this way, and it will definitely work for this discrete events, and you can also do that. Okay, so what I mean to say is, if you are trying to find out the probability of an event, you can go with the number of elements in the event divided by total number of elements in the sample space. Now in this, number of elements is going to be 1 divided by total number of elements is going to be 6. That is why we got 1 by 6. Therefore, for each of these simple events, right, so event of getting 1, event of getting 2, event of getting 3, so on, event of getting 6, we can give the probabilities 1 by 6, 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 right? Now these probabilities are going to change in case if you know something about the output. For example, if it is given that the output, the die is rolled and the output is one of the even numbers, if that is the case, which means, are you getting this? Now this is the one which we normally do. Now let us say someone has rolled the dice and you didn't see the output, and he told you that the output is an even number. Then these numbers are going to change. Why? Because the probability of getting any number other than even number is going to be 0, isn't it? Therefore the probability of getting a 1 is going to change to 0. Earlier it was 1 by 6, now it is going to change to 0. And probability of getting a 2, let's keep it that way, let's derive it later. And 3 is going to be 0, 4, let's leave it, 5 is going to be 0, right? Therefore now 3 events have become 0, and now there is only possibility of 3 events. Therefore now our new sample space will contain only 3 events. Are you getting this? Since it is already known that one of the even number has occurred, so I am directly assigning 0 to the odd numbers, and to the remaining even numbers I am supposed to assign some probability. See, initial probabilities were 1 by 6, 1 by 6, 1 by 6, 1 by 6, and now they have changed it to 0, 0, 0 for 3 numbers. Now for the other 3 numbers also I have to apply some probability here. Now what is the probability that you are going to apply to the remaining numbers? Now remaining numbers are 3, and we know that one of the 3 has occurred. Therefore again, since the original die was fair and all the outcomes were equally likely, now any of these 3 events are also going to be equally likely. We are not going to bias, but then we have only 3 elements. Now by this definition, if you see this, now if you want to find the probability of an event, it is going to be number of elements in the event divided by number of elements in the new sample space, right? So the number of elements in this event of getting 2 is 1, which means, and then the number of elements in the new sample space. What will be new sample space? The new sample space S dash. If it is already known that we have got an output which is an even number, then the new sample space is going to be 2, 4, 6. Therefore these probabilities are going to change as 1 by 3, 1 by 3 and 1 by 3. Got it? Let us say instead of this, if it is known that a prime number has occurred, then what will be our new sample space? Let's say instead of this 2 even number, someone has rolled the die and they said that the output is one of these prime numbers. Then what is our new sample space? Our new sample space is going to be either 2 or 3 or 5. So in this case, how will the probabilities change? For 1 it is 0, and for 2 it is 1 by 3. Why 1 by 3? Because the number of events is going to be 1 and the total number of events in the new sample space is 3. That is why 1 by 3. And what about this one? 3 is also 1 by 3. And what about this 4? It is 0. What about this 5? 1 by 3. And what about this 0? Got it? So anyway, whatever the assignment of the probabilities are, they are all going to follow that rule. What is the rule? The probability assigned should be between 0 and 1. That is the first rule. And the second rule is the probabilities, when you sum them all up, you are going to get 1. If you add all this, we are going to get 1. If you add all this, we are going to get 1. If you add all this, we are going to get 1. So what is that I want you to observe here is, now let us say we have a sample space, and now they have performed an experiment and they said that something has occurred. Then the new probabilities to the simple events, which means the points in the sample space, should change accordingly. That is what I want you to understand. Okay. Now let us say E is an event. Instead of S dash and S, let me say E. Let us assume that E is an event of getting a even number. Then what will be the probability of E? Now if you go by this definition, number of elements in E, 1, 2, 3 divided by number of elements in S, which is nothing but 1 by 6, 3 by 6. So 3 by 6, which is 1 by 2. Now let us say f is an event of getting a prime number. Now what is it I am talking about? I am just talking about an experiment in which a simple die is rolled, and now what is the probability of getting a even number, what is the probability of getting a prime number. Now these are not what I am talking about. This is what the case is. A simple fair die is rolled, and now what is the probability of getting an even number? The probability of getting an even number is 3 by 6. Why 3 by 6? Because number of elements in E is 3 and in number of elements in the sample space S is 6. That is why 3 by 6, which is 1 by 2. Then what is the probability of getting a prime number? Prime number is nothing but again 3 by 6. Why? Number of elements in F is 3 and number of elements in the sample space is 6, which is nothing but 1 by 2. Got it? Now what is the probability of E intersection F? Now what can you say about E intersection F? A number which is both even and prime, which is nothing but 2. Now what about P of E intersection F? P of E intersection F is nothing but 1 point is there and the total number of points is 6. That is why 1 by 6, which is, let's leave it that way, 1 by 6. Now these are the numbers we have. Okay. Now assume that they have already told you that, they have already told you this point. Let us say they already told you that the output is an even number. Okay, the question is like this: what is the words are very important here, that is why I am writing. What is the probability of getting a prime number given that an even number showed up. Okay, so now they are asking about this. This is called as conditional probability. See, I am going very detailed, in a very detailed manner, very slowly. The reason is this is very important topic. If you can understand this, we can go till Bayes theorem very easily. Just try to understand it. I will be very slow. I'll be talking about really small things, really basics, but you should understand each and every point here. Otherwise, it will be very difficult for me to explain you other things later. Okay, so let's try to understand it everything. Now, what is the probability of getting a prime number given that an even number showed up? That is what we wanted. Now, how we represent it is called as conditional probability. Probability of getting F, which means a prime number given that E has already occurred. This is what we want. Okay, now there are various ways we can solve it. I'll show you all the ways. I mean, you can directly do it or you can apply these formulas, but then try to understand the formula, and whatever method you can solve it fast in the exam, you can use that. So see this one, already even number showed up, that is what we know. So these probabilities are going to change. How are they going to change? For the even numbers we are going to get the probabilities, and for the odd numbers we are going to get zeros, which means for 1 there is no probability, and for 3 there is no probability, and for 5 there is no probability, which means for odd numbers there is no way we are going to get anything. So we are applying zeros. We are not going to get odd numbers. For the even numbers, yes. So there are 3 even numbers, and all these 3 are equally likely to happen. That is why each one is going to get 1 by 3, 1 by 3, and 1 by 3, right? Now what is the question? What is the probability of getting a prime? Which means, what is the prime number now? Prime numbers are 2, 5, 2, 3, and 5. Now in this new probabilities, you have to find out the sum of the probabilities of getting 2, 3, and 5. Now 2, 3, and 5 is going to be simply 1 by 3. Therefore, directly answer is 1 by 3. You know it. You can write it down. That is not what I am worried about, isn't it? Now, can't you directly say this? Now, from this new probability assignment, what they wanted is, what is the probability of getting a prime number? Now, given with the given information you have changed the probabilities, and now among these changed probabilities you can apply that union theorem. What is union theorem? 2 union 3 union 5. Now 1 by 2, 1 by 3 plus 0, which is 1 by 3. That is the answer. We can directly write it, right? But then I want to derive the steps and I want to show you some other ways of doing it. Now see this. One event is event of getting a prime number, and other, this is event of getting a prime number, and this is event of getting an even number, right? Now it is already given that E has occurred. This event has already occurred. Okay, now they are asking what is the probability that F has to occur. If E has already occurred, and now if F has to occur, definitely the part which we should be interested is this, isn't it? Which means only the elements present in this are going to give us the required probability. Therefore this is going to depend on n of E intersection F divided by, earlier sample space was this entire thing, isn't it? But the now sample space is E. That is why we are only interested in number of E. Try to understand this one carefully. See this. Now, are you following this? Let us say F is the event of getting a prime number and E is the event of getting an even number, right? And given that E has already occurred, which means now our new sample space contains only this part. Now what is the probability of getting this part? So what is that they are saying? Already now we know that this one has occurred. Now what can we say about this part? How much probability do you want to assign to this part, right? And we know how to assign the probabilities. So what is it? We count the number of elements in this in case of discrete elements, and then we count the number of elements in this. Now the number of elements in this part divided by total number of elements in this part is going to give us the required probability, which is nothing but n of E intersection F divided by n of E. Now what is n of E intersection F? Now what can we assign? What is the number of elements in the intersection? The number of elements in the intersection is going to be, if you take these two, intersection is going to be only 1, which is nothing but 2. If you take the intersection, it is only 1, right? So which means 1 divided by, what about n of E? So how many elements are there in E? If you look at E, it is going to be 3 elements. 1 by 3 is the answer, right? Either you can get like this, or you can apply that formula and get it. Or the standard way is, now I am just trying to divide this one, n of E intersection F divided by n of S. N of S is original sample space, divided by n of E divided by n of S, which means I am just dividing the numerator and denominator with number of elements in the sample space. Numerator and denominator I am just dividing with number of elements in the sample space. And we already know that if you take an event, if you take the number of elements in the event, and if you take the sample space and if you divide it, we are going to get the probabilities, which are nothing but the original probabilities, not the changed probabilities, right? So that is how I can write this as P of E intersection F divided by P of E, isn't it? P of E intersection F divided by P of E. Now these probabilities are original probabilities. So what is the difference between using this method where you change the probabilities and then you take the union, and this one? The difference is you need not change the probabilities. You can take the original probabilities, just think that the die is fair, and you apply the original probabilities, and using those original probabilities itself we can apply this formula and get the answer. See this? Now in the original probabilities, what is P of E intersection F? What is probability of getting 2? P of E intersection F is 1 by 6, isn't it? Original probabilities, not the changed ones. And what about P of E? P of E is 1 by 2, right? Which is nothing but 2 by 6, which is equal to 1 by 3. Again we got 1 by 3. Got it? So what is that I did? I have changed the probabilities and I have summed them up. Here also I got 1 by 3. When I sum this one and this one, here also I got 1 by 3. Or I have found out this method in which I'll find out the number of elements in the intersection part and the total number of elements in the part that has already occurred. There also I got 1 by 3. Or I have found out that probability of E intersection F divided by probability of E, which is 1 by 3. So which one is the easier for you? You might intuitively feel that this is the easiest one, or you might feel that this is the easiest one. Yes, they are easy, but then if you think deep, you are not actually changing anything. You are actually writing these numbers and you are directly using this formula and getting it. So this one is easier actually. Okay, so whatever method you like, you can answer the question, but then I recommend that you just remember this one: P of probability that an event F will occur, given that the probability E has already occurred, is equal to probability that F and E will occur divided by probability of E. This is called as conditional probability, right? The conditional probability that F will occur given that E will occur. Why is it called conditional probability? Because we are discussing about what will be the probability of an event given that other event has already occurred. That is the condition we are applying. That is why it is called as conditional probability, right? So now let's see one more example. I think you understood this clearly, right? So if you didn't understand it, please rewind it and then again watch the video completely from the beginning. It is really the beginning, this part. From here we are going to get into next one is multiplication theorem, and then total probability, and then Bayes theorem. So if you have to understand all these theorems well, you should understand this one really well. Okay, fine. Now try to understand this one with one more example. Let us say I am having two dice and I am rolling two dice, and it is already known that there is 4 on the first die. So let us say the experiment is now rolling two dice, two fair dice, okay, and E is an event that the first dice is 4. Then what are the elements in this event? 4 1, 4 2, 4 3, 4 4, 4 5, 4 6, isn't it? E is an event in which this is the case. So these are the elements. Now what can you say? What is this sample space? Actually the original sample space will contain 36 elements. If you are rolling two dice, then the original sample space will contain 36 elements, 6 into 6, right? And the probability of each simple event is going to be 1 by 36 because all are equally likely. And now in this event we have 6 elements. That is why the probability of this event E is going to be 6 by 36, because probability of each event is 1 by 36. Since we have 6, it is going to be 6 by 36, which is nothing but 1 by 6, right? And let us define one more event F. Let F be an event in which the sum of outcomes is 6, okay? So which means if I see the sum of outcomes on both the dice, then if I add them up, it has to be 6. So what are the possibilities? 1 5 and then 5 1, both are going to give us 6, and then 2 4 and then 4 2, both are going to give us 6, and then 3 3, it is also going to give us 6, right? Now what is the probability of probability of F? Probability of F is, it is going to contain 1 2 3 4 5. 5 elements are there. That is why it is going to be 5 by 6, isn't it? Now assume that E has already occurred. What is the probability of F occurring? Which means given that first die has turned up to be 4, what is the probability that sum of the dice is going to be 6? Which means probability of F given E. Now how are you going to do this? You can do it in various ways, right? So one method is you can use this, or you can change the probabilities and do that. See, in the original sample space there were 36 elements and each element was taking a probability of 1 by 36. Now once the condition has been applied, what is the condition? The first die has turned up to be 4. Now all the remaining elements will become 0. All the probability of the remaining elements. What are the remaining elements? The remaining 30 elements will take the probability 0, and these 6 elements are equally likely to happen. Why? Because the original elements are equally likely to happen, because therefore any of the 6 elements are equally likely to happen. Now how many elements are there? 6 elements. So you can apply 1 by 6 to each one of them. 1 by 6, 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 because there are only 6 elements. Now what is the element that we are interested in? Now from this sample space we are interested in the element in which the sum is 6, which means we are interested only in this one. Therefore what is the answer? 1 by 6. The probability of getting a sum as 6 given that first die has turned up 4 is 1 by 6. You can directly say it, right, by this method, by changing the probabilities. Otherwise the second method is you can count the number of elements. How many number of elements are there? 6 elements. And then how many number of elements are there in E intersection F? Only one element, which is 4 2. Therefore you can use this method, which means 1 by 3. Or the third method, which I suggest that you always use, is P of F intersection E is equal, P of F given E is P of F intersection E divided by P of E. Now let's try to find out what is P of F intersection E. Now P of F intersection E is nothing but how many elements are present in this intersection? Only one, right? Therefore it is 1 by 36. See, this probability is the original probability before knowing the condition, isn't it? That is the beauty of this formula. Even without changing the probabilities, we can know the original probabilities and we can work out the answer. So F intersection S is 1 by 36, right? So what is the answer? P of F given E is P of F intersection E, which means 1 by 36 divided by P of E. What is P of E? P of E is 1 by 6. That equal to how much? It is nothing but 1 by 6. This is the answer. Alright, so you can easily do that. So let's do one more example. Let us say there is an event. Again we are rolling 2 dice. Now the event E is that we got 2 odd numbers, right? So assume that we are talking about event E. We have rolled 2 dice, and event E is the event in which both the dice have shown up odd numbers. Then how many will be there? If both the dice have shown up odd numbers, then it will be 1 1, 1 3, 1 5, right? And then 3 1, 3 3, 3 5, and then 5 1, 5 3, 5 5. So 3 odd numbers are there. So 3 into 3 is going to be 9, right? And let us say the second event F is the event in which the sum is 6. So the event in which sum is 6. If the sum has to be 6, then what are the possibilities that we are going to take? We are going to take one is 1 5 and other is 5 1, right? 1 5, 5 1, and then 2 4 and 4 2, as well as 3 3, right? Now what is the probability of getting F given that E has occurred? Which means if it is already known that both the outcomes on the dice is or even or odd numbers, then what is the probability that sum of the dice is actually 6? If that is the question, how are you going to answer it? Now again we can do in all the 3 methods. You can choose any of these 3 methods, right? So what is the first method? What are the changed probabilities? Originally it was containing 36 elements, and each element was getting 1 by 36 as the probability. But now after the condition has applied, which means the event E has occurred, now out of this 36, right, 9 events has occurred, and 36 minus 9 events will get 0 as the probability. For these 9 events, the probability will become 1 by 9, right? All of these events are going to take the probability 1 by 9, right? And now in this one, just choose what is the output that you wanted. What is the output that you wanted? The sum has to be 6. Just choose how many are there. So if the sum has to be 6, this is there 1 comma 5 and 5 comma 1 and 3 comma 3, right? So these are the 3 items we have. Therefore it is going to be 3 by 9, isn't it, directly, which is 1 by 3, right? Otherwise, what is the other method? You can find out what is intersection part. Intersection part, we did the same thing, right? What is the intersection part? The intersection part is 3, and what is the total? The total is 9. Therefore 3 by 9, again we get 6, 1 by 3. And what about the other one? The other one is P of F is P of F intersection E divided by P of E. Now what about P of F intersection E? P of F intersection E is nothing but it contains only 3 elements, which is 3 by 36, right? Divided by what is P of E? What is P of E? E contains 9 elements, which is 9 by 36, which is nothing but 1 by 3. You can go by any method, you are going to get this, right? So what I mean to say is, conditional probability is a way of finding out a probability of one event given that other has already occurred. That is the condition. This is what we are looking at. Got it? So using this, using this formula, this one, we are going to do many problems, right? So I'll take all the problems one by one and I'll explain you. Okay. Now let's see a few more examples on conditional probability. Let us assume that, see this question, a family has 2 children. If one of them is known to be a boy, then what is the probability that both are boys? Okay, so now it is again a conditional probability question. So how do you identify that whether it is a conditional probability question or not? So they will use the terms like this, it is known that, or given that, or what is the conditional probability. So they will use such terms. So using the question you can identify whether it is a question on conditional probability or not. So clearly it is a conditional probability. So now there are a family is having 2 children. We don't know who they are, but then it is given that one of them is suddenly boys, right? One of them is suddenly a boy. Then what is the probability that both of them are boys? So first of all, let's frame the question from the initial terms. So initially, initial sample space is this: both can be boys, or one can be boy, other can be girl. First one can be boy, second one can be girl, or first one can be girl, second one can be boy, or both can be girls. So these are the probabilities, right? When you have 2 children. Okay, this is the actual sample space without applying the condition or without applying our knowledge. Now all these are equally likely, right? So what is the initial probability for each of the event? For each of the event it is going to be 1 by 4, 1 by 4, 1 by 4, 1 by 4, right? Because one event divided by 4 events, 4 elements. And now it is given that one of them is boy. So if one of them is boy, then just rearrange the probabilities, right? Just change the probabilities and see what happens. If one of them is boy, then the probability for this event, both of them girls, is 0, and the probability for this event has to be something greater than 0, something greater than 0, because they are all possible, because one of them is boy. Now how many events are there? 3 events. As the initial events, they were all equally likely, or they were all equally probable. Now these 3 are also equally likely. Therefore I'll distribute the probability equally between them, 1 by 3, 1 by 3, 1 by 3, whatever it is. After assigning the probabilities, just see that sum of all probabilities of the sample space is 1, isn't it? Okay, now they are asking about the event. What is the probability that both are boys? So after changing the probabilities, what is the probability of the event BB, this one, which is nothing but 1 by 3. You can directly do it like that, or by using the probability of conditional probability formula. Okay, without using the conditional probability formula, if you are directly going to answer it, why did I teach it? You might get that question, right? But later it is going to play a very important role. Now even though I am not using it, later I'll use it. So let us say E is an event that at least one of the children is boys. So then E will contain BB, BG, GB. right, and F is the event that both are boys, right. Now I want probability of F given E, which is nothing but probability of F intersection E divided by probability of E. Now what about F intersection E? F intersection E will contain only one element, which is BB. Now what is the original probability? Just look at this one, this assignment, not this one. Okay, so when you are using this this formula, just look at the original assignment, which is nothing but BB, right, which is 1 by 4 upon, what about this one, probability of E. Probability of E is nothing but 3 events are there, so it is 3 by 4, isn't it? We had to add these 3 by 4, so which is nothing but 1 by 3. Got it? Or even you can take this one and then you can add, you can divide it by this. So this is the new sample space. They are asking about this event, which is nothing but 1 by 3. Either that way also you can get it. Got this? So you can follow any of these methods, but I just want you to learn this one more. Later we are going to use it a lot. Okay. Now let's see one more example on conditional probability. Let us say we are performing an experiment in which we are going to flip 3 coins. Then what is the sample space? The sample space for these 3 coins is going to be, see, each coin can have head or tails. Let us say all the coins are fair. Then we are going to have 8 events, right, or 8 outcomes. So all can be head, or head tails, or head tail head, or head tail tail, or tail head, or tail head tail, or tail head, or tail tail, right? All are 8. So all these 8 are possible. So initially what happens to the probabilities? The probabilities are all going to be 1 by 8, isn't it? Now let us say an event has already occurred. E is an event that at least it is already known that at least one of them is turned out to be head, or let us say at least 2 of them is turned out to be head, which means E is an event in which 2 of them has turned out to be head. So what do I mean by that? E will contain all this, at least 2 of them have turned out to be head, right? Now let us say F is an event in which at least one of them turned out to be tail. Okay, at least one of them turned out to be tail. So it is going to contain all these, I think, except one chance we are going to have all this, right? So except this, all are possible here, right? So what is it? E is an event that at least 2 of the coins have showed up heads, and F is an event that at least one of the coin showed up tails. Now if it is asked that what is the probability that E given F, which means if it is already given that at least one of the coins has turned up tails, what is the probability that 2 coins have showed heads? How can you solve it? Again the same, we can use this formula, E intersection F divided by P of F. Now what is in the intersection of these two? So how many is going to be present in the intersection? So H is not present, right? And HHT, yes, it is present. This is present, and then this is present. THH, it is present, right? Therefore intersection is going to be 3. So 3 by 8. Why 3 by 8? Because originally all of them are having 1 by 8 probability. Therefore if you have 3 points, then they are going to have 3 by 8 divided by P of F. P of F is going to be 7 by 8, which is nothing but 3 by 7. Got it? Now if you want to understand it using our other developed theory, that changing the probabilities and finding out what is required, then also you can do it the same. So how can we do that? Already F has occurred. What does it mean? There is at least one tail. So all the elements which does not contain tails should be eliminated or assigned a probability 0, which means by this we get this one as 0 and all the others will get the equal probability. How many elements are there? 7 elements. Therefore each one is going to get equal probability of 1 by 7, isn't it? 1 by 7, 1 by 7, 1 by 7, so on. Now we have to choose the events in which at least 2 are heads. So how many are there? This one has to be chosen, this one has to be chosen, this one has to be chosen, this one has to be chosen. That's it, right? So out of these 4 events, one has got 0 and the other 3 has got 1 by 7 as the probability. Therefore it is going to be 3 by 7, right? So either you go by that theory or with this one, both are same. Now the other one is probability of f given e, which means if it is already known that 2 of the coins have showed up heads, then what is the probability that one of them is at least tail? There is at least one tail, in one of the in the three coins. How can you do it? Again the same one, p of e intersection f divided by p of e, right? Then what is it? Just check this. It is going to be 3 by 8 divided by, how much is it? P of e is going to be so what? How many elements are there? Here it is 1, 2, 3, 4, right? 3 by 8, which is nothing. Okay, 4 by 8, which is nothing but 3 by 4. Got it? So one thing you should observe is P of E intersection F is common, it is same, right? So what is changing? P of F is changing and P of E given F is changing, and P of E is changing and P of F given E is changing, right? Or even from these two you can also derive something. Again later I'm going to show you this, but since we are doing it here, you can observe one thing here. From these two you can see that P of E intersection F equal to P of F into P of E given F, or P of E into P of F given E, which means from these two, from this formula and from this formula, you can do like this: P of E intersection F equal to P of E into P of F given E. Also this is equal to P of F into P of E given F, right? So how, if you want to see it, you can just check this one. So in this case, what is P of E? P of E happened to be 4 by 8, right? And what is P of F given E? P of F given E happened to be 3 by 4, right? And what about this P of F? P of F happened to be 7 by 8. And what about P of E given F? P of E given F happened to be 3 by 7. Okay, you can check that both are equal. So later we shall see this. You can leave it out for now. So what I mean to say is, either you can go with this method or you can go with this method. So if this is given, you go with like this. If this is given, you go like this. So one thing you have to observe is what is given, that is going to be forming the sample space. Why is this so? See, what is given is going to form the sample space. Why is this so? Because if it is already, some event is already given, see, originally our sample space is this, right? And now if an event is already given that it has happened, then what does it mean? From the original sample space, our new sample space will be boiled down to this part. Okay, now when you are talking about the occurrence of other event, let's say other event is this is E is already happened and F, right? Now we are interested in this part, right? So now the entire probability boils down to this sample space and then finding out the probability of this part given that this part has happened. Okay, let's see one more example on conditional probability. Let us say we have 10 cards, and on these 10 cards they are numbered from 1 to 10. Okay, 1 2 3 4 so on, like this. Each card is numbered like this: 1 2 3 4 5 6 so on 10. Okay, and now all these cards are shuffled and we are supposed to draw one card from them randomly. Then let us say E is an event saying that we get the number as at least 5, right? Now the question is, given that E has occurred, which means in this experiment of drawing a card, a single card, if it is already known that the number on the card is at least 5, what is the probability that the card we draw is 10? Okay, so now E is an event that the number is at least 5, and F is an event, let us say that the card number on the card is 5. Okay, 10. Number on the card is 10. Now what is the probability of F happening given that E has already happened? So again, it is a conditional probability. Okay, so what is the question? We have 10 cards which are all numbered from 1 to 10 and they have been shuffled. We are supposed to draw one of them, and now we found out that already the number is at least 5. Therefore, what is the probability that it is actually 10? So what is F given E? Got it? Now you can do it in two ways. Change the probabilities there. Initially, if all the cards are randomly placed, and if you have to choose one randomly, then probability that any number will come up is going to be 1 by 10, isn't it? All of them are going to have the same probability of 1 by 10, 1 by 10, 1 by 10, so on, right? Now the conditional probability is that at least 5 has occurred, which means for 1, 2, 3, 4 it is zeros, because at least 5 has come, and so these numbers will never come up. That is what is already given. And which number has exactly come, we don't know that, but then they are all equally likely to come, which means from 5 to 10 they are all equally likely. How many are there? 6 are there. Therefore I am just changing the probabilities from 5 to 10 as 1 by 6. Now they are asking what is the probability for 10 coming. So after changing the probability, what is the probability that you got for 10? It is 1 by 6. You can directly answer that way, or the other way is using the conditional probability formula. Now what is the formula? P of F given E is equal to P of F intersection E divided by P of E, right? Now what about P of F intersection E? So at least 5 and 10. So what is the intersection? See, in this one we are going to have the cards 5, 6, 7, 8, 9, 10, isn't it? And in this one we are going to have only one card, which is 10. Now if I find the intersection, there is only one. So what is it? It is 10. Therefore the probability for F intersection 10 is, F intersection is 1 by 10. Don't get confused. Don't write 1 by 6 here. So when I am writing about the formula, I am talking about the original probabilities, right, which are 1 by 10. And what about P of E? P of E is containing 6 elements, therefore 6 by 10. So it is 1 by 6. Got it? You can answer it anyway. Okay. Now let's see some of the properties of conditional probability. So one is P of S given F equal to 1. So where F is an event and S is the sample space. So why is this true is, just check this. P of S given F is nothing but, what can we write? P of S intersection F divided by P of F. Now what about S intersection F? We know that F is a subset of S, isn't it? Therefore P of S intersection F is going to be P of F. So why is this true? Because S is the sample space and then F is inside it. F is an event, right? And now if we take the intersection of these two, intersection is going to be the smaller one, which is F, divided by P of F, right? So it need not always be S. I will tell you some events where we get a probability of 1. I'll just try to frame an example. Let me think about an example. Let us say we are flipping 2 coins, and what about the sample space? Sample space is going to be, both are going to be heads, or first one is going to be head and second one is going to be tail, so on. These are the 4 events that we have in the sample space of flipping 2 coins. Now let us say E is an event that both coins happen to be heads, and F is an event that one of them is head. Okay, now let's say I want to find the probability of F happening given that E has happened. Just think about it. We already know that both coins happen to be heads. Now I am asking you, what is the probability that one of them is heads? Already we know that both of them are heads. Now it is very certain that one of them is heads. Therefore, it is actually 1, isn't it? Just think about it. E is an event that both of them are heads. F is an event that at least one of them is head. Right? What does it mean? What is the probability that at least one of them is going to be head given that both of them are heads? If both of them are heads, then what is there? Definitely one of them is at least heads, isn't it? Therefore it is very certain. Or if you want to go with the formula also, you can go with it. See this. Now this P of F intersection E divided by P of E, right? So what is P of F intersection E? If you take the intersection is E itself, right? Why? Because see this, F is this and E is this. E is present inside F, right? Just like this. F is present inside S, just like that, isn't it? So now it is clear. So what is F intersection E? E, that is equal to P of E divided by P of E, right? Or you can even test it. It is 1 by 4 divided by 1 by 4, that equal to 1. So that is how sometimes we get 1 in conditional probability. And the next one is P of E complement given F is equal to 1 minus P of E given F. So what does it mean? See this. Now let us say this is the sample space and an event F has already occurred. Okay, and now there is a event E. Now what is that they are asking? They are asking that what is the probability of E not happening given that F has happened. Now given that F has happened, see, this is what has already happened. Now what is the probability of E not happening? So it is nothing but this part, isn't it? So we are worried about this part, right? So since we know that F has already happened, P of F is a new sample space which is equal to 1, isn't it? Since we know that F has already happened, P of F is a new sample space, and so P of F equal to 1, right? And now we can write P of F as sum of these two, right? So what is this part? P of F, you can write it as sum of these two. One is P of, this part is nothing but E complement given F plus P of, what is this part? This part is E given F, right? And now we can say that 1 equal to P of E complement given F plus P of E given F. Now we can get this one, isn't it? And what about the next one? Let us say F is an event which has already occurred, which means let us say this is the sample space and F is an event which has already occurred, right? And we have two events A and B like this, A and B like this. Now they are asking what is the P of A union B given F, which means they are asking about this part 1, 2 and 3. They are asking about this part. So how can you write it? It is nothing but P of A given F. What is P of A given F? This is A, this is B, okay? What is P of A given F? P of A given F is nothing but union of these two elements 1 and 2, right? Plus P of B given F. P of B given F is nothing but 2 and 3. Now if you see this 2 has been added 2 times, that is why I have to subtract it, which is nothing but P of A intersection B given F, which means this part has to be subtracted. That is why it is subtracted. Are you getting that? Okay, so it can even be extended to more than 2 events also. So Exactly the same way which we have applied for the normal probabilities, we can apply the same formulas for the conditional probabilities. Only thing is, with conditional probabilities, the sample space will change from S to the event that has happened. For example, from S to F. Even you can extend it. See, in this case, if you put S, what happens? It is nothing but A of okay. In any way, see this. What I am trying to say is, let us say P of A given S. What can you say about it? A is an event and S is a sample space. Assume that. Then it is nothing but P of A intersection S divided by P of S. Isn't it? Now, what about P of A intersection S? A is a subset of S, which is nothing but P of A divided by what is P of S? S is the sample space, it is 1, that equal to P of A, right? So given that at least one of the event will occur from the sample space, that we already know, what is the probability of A? Probability of A is A itself, isn't it? Now instead of S, if they have given some other event, then we have to divide with that, we have to normalize with that. Why? Because the effective sample space has reduced. Originally the sample space was the entire series, sample space was bigger, and then the probability of A happening is the probability of A happening itself. Now when you reduce the sample space, let us say some other event has occurred. Now instead of the original sample space, the sample space has fallen down to this. That is why you are dividing this entire probability by the probability of this, right? You are dividing this part by the probability of this, right? Okay, with examples you'll learn this. I don't know if you understood whatever I am trying to say here. Just see that you understood these three formulas, and other part is not required. You just try to remember that if you didn't understand anything else, okay? But with problems, I'll try to explain you all these concepts whichever I talked about. See, just now we started. By the time we reach Bayes theorem and then the random variables, everything will be clear. If you are not able to get anything, just keep going, just keep taking the notes, just keep going. As and when we add more problems, it will be clear. Okay, fine. Now let's see one of the applications of the conditional probability. We already know that, we have seen this one, right? P of A given B is equal to P of A intersection B divided by P of B, right? Similarly, we have also seen that P of B given A is equal to P of A intersection B divided by P of A, isn't it? We have already seen this. Now from this is called conditional probability. From this conditional probability, we derive a new theorem called as multiplication theorem in probability. Multiplication theorem, and this is a very important theorem in the sense for most of the questions from now on we'll be using this multiplication rule. Now what does this multiplication rule says is, see this, now from this formula, right? So what is P of A given B? The probability of A happening given that B has already happened. Now what is P of A intersection B? A and B are two events, the probability that both the events happening, right? So now just see this, P of A intersection B, if I multiply both sides with P of B, then what do I get? Then I get that I'm not doing anything, I'm just trying to take the basic simple formula and I'm trying to write it in a some other form. I'm trying to multiply both sides with P of B. Then what I get is, if I multiply both sides with P of B, then I get P of A intersection B is equal to P of B into P of A given B. What does it mean? The probability that two events A and B happening, the probability of these two events both A and B happening is equal to probability of B happening into probability of A happening given that B has already happened. Now similarly, if you take this formula, this one, right, and if you multiply both sides with P of A, then again we get the same thing, P of A intersection B is equal to P of A into P of B given A. Now what does it mean? The probability that these two events A and B happening simultaneously is equal to probability of A happening first and then probability of B happening given that A has happened. Got it? Now this is called as multiplication theorem, and in fact this is called as multiplication theorem on dependent events. So what is dependent events and what is independent events is, sometimes what happens is the probability of a event happening will not affect the probability of other event happening, which means sometimes it so happens that if we have already seen that an event has happened, even after knowing about that, the probability of other event happening does not change. Okay, so what I'll do is, let me explain you this one with some examples and then I'll take the independent events. Now we are talking about dependent events. So the classic example to explain this dependent event is, this is a very popular example. Okay, now let us say we have a box, and in this box let us assume that we have two green balls and three red balls. Okay, now I want to conduct an experiment. I want to draw two balls one after the other without replacement. Okay, now what is it? I have a box, and in this box I have totally 5 balls. 3 are red and 2 are green. Now I want to withdraw, or I want to draw two balls in such a way that first one I want to draw green, and second one I want to draw red. Okay, so I'll write like this. So G1, which means in the first draw I want to get a green ball, and R2, which means in the second draw I want to get a red ball, right? But then there is a glitch here. This small condition here is, I don't want to replace the ball after the first withdrawal. Got it? So what is it? The box is containing 5 balls. Now I am going to withdraw one ball from it, and I will not replace it. Without replacing it, I am going to withdraw the second one. Now in this case, what I am interested is, what is the probability that I draw green ball first and then red ball. Now if you observe it, it is a dependent event. The reason is, once I have withdrawn green ball, then the probability of getting the red ball will change. That is why they are dependent events. Now how can I write it in multiplication theorem is, how can I solve it is like this: P of probability of drawing green ball first and red ball next is equal to probability of drawing a green ball first multiplied with probability of drawing the red ball given that green ball has already been drawn, right? Now what is it? What is the probability of drawing the green ball? You totally have how many balls here? 5 balls, out of which how many green balls are there? 2 balls, right? Therefore probability of drawing the green ball is 2 by 5 multiplied with what is the probability of drawing the red ball given that we have already drawn one green ball. Now if you have already drawn one green ball, this is no more there in the box. Therefore what is remaining? Only 4 balls are remaining. Out of these 4, 3 are red balls. That is why into 3 by 4. Got it? You can calculate that. So this is the meaning of conditional probability. Are you getting this? So what is conditional probability? I mean, this multiplication theorem is, now if the events are dependent, then we can use this conditional probability formula and convert it to multiplication theorem, and we can use it, right? Okay, it can even be extended to more than one event. So here, even though here we have shown only about 2 events, it can even be extended to more than 2 events like this. Let's say I want to find out what is the probability of 3 events happening simultaneously, E1, E2, E3. Then how can I do this? It is nothing but, according to multiplication theorem, probability of E1 happening multiplied with probability of E2 happening given that E1 has already happened multiplied with probability of E3 happening given that E1 and E2 has already happened. Got it? So let's see one example for that model. Let us assume that we have 1, 2, 3 in green balls and 1, 2, 3, 4, 5 red balls, okay, in a bag. And now I want to draw 3 balls without replacement. I will draw them one by one. I will draw the first ball, I will draw the second ball, I will draw the third ball. Now what is the probability that all the 3 balls are going to be red? Okay, so now I want to find out the probability that all the 3 balls are red. So what does it mean? I am interested in this probability that first ball is red and second ball is red and third ball is red. How can we do that? Now again using the multiplication theorem. So are they dependent or independent events? They are actually dependent events. Why are they dependent is, once you have drawn one red ball and if you didn't replace it back, then the probability of getting the second red ball is going to get affected, right? And once you have drawn 2 red balls from the bag without replacing, then the probability of getting the third red ball is going to get affected, which means it is going to get changed compared to the initial chances. Initially what are the chances, and then after drawing 2 balls what are the chances? They are going to change. That is why one event is actually depending on the other event. Then in this case they are called as dependent events. Later I'll talk about independent events as well, but for now just fix for this. See this. Now what is this? P of R1 first. So probability of picking the red ball first, and then given that we have already picked one red ball, what is the probability of picking the second red ball, right? Which means given that we have already picked up the red ball in the first try, what is the probability that you pick up the red ball in the second try, into probability of P of R3 given that R1 and R2 has happened, which means what is the probability of picking the third ball also as red given that first ball is already picked as red and second ball is already picked as red. Now what is the probability of picking the first red ball? 1, 2, 3, 4, 5 red balls are there and total number of balls are 8. 5 by 8 into, now we have already picked up one red ball, then how many red balls are remaining? 4 red balls are remaining. And how many total balls are remaining? Only 7. Initially there were 8, but one of them was picked out and then it is not replaced. So the key word here is the balls are not replaced. Without replacement we are doing this. When we do it with replacement, then they will become independent, right? So if you pick a red ball and again if you leave it there, then the probability doesn't change, then that becomes dependent, but here it is independent, right? Into, now we have picked up 2 red balls. Now the third one also, if you have to pick up the red ball, then it is going to be 3 by 6, right? This is the probability. Therefore it can be used as a chain. It is a kind of chain. It is also sometimes called as chain rule, right? Because we are going to chain them all the events, right? So this is an example in which we are going to use the multiplication theorem on dependent events. Later we shall use the multiplication theorem on independent events as well. I'll show you later, but first let's do some more examples on this, then we can go to the next model. Okay, fine. So this question is very useful for you, not just for probability course in this, for GATE. Even after GATE is over, let's say you have joined masters. Oh, I think I didn't tell you how it happens in masters, right? See, we don't have anything like a classroom. In general, in BTech, what happens is you'll have a classroom and you'll generally go to that room every day, and faculty will come one after the other and they'll take the classes. That is how generally BTech classes happen. But if you go to MTech in most of the universities like IITs or IISc or IIITs, what happens is there will not be anything called a classroom. So they'll all join in one department, let's say computer science department, but they need not take all these same courses. What happens is in most of the universities I'm talking about, in NITs I think it is same still as BTech, or some of the NITs are different, but in IITs and IISc it is like this. So at least in IISc it is like this. we every semester they will just announce what are the courses that they will be offering in that particular semester and the timings. For example, they'll say that TOC will be offered by Deepak D'Souza from 10 to 11:30. So generally there will be 1.5 hour sessions. Okay, each session will be 1.5 hour, 10 to 11:30 in lecture hall number, let's say 2. There will be lecture halls, right? And now if you are interested like this, you will have course number 1, course number 2, course number 3, course number 4, course number 5, so on. Nearly there will be 20 courses or so, or even more. That varies from semester to semester. Now there is no need that you have to choose all of you have to choose the same subjects. Depending on your interest and the area that you want to get into for research, depending on that you can choose some of the subjects, right? So in like this, people what they do is they will, let us say they will register for, generally we register for 4 courses in a semester. In the first semester we do 4 courses, in the second semester we do 4 courses, and in the third semester we do 2 courses. Totally we are supposed to do 10 courses in order to finish your masters, that MTech or ME. For MSc the requirement is different. They'll be doing a lot of research work, and so coursework will be less. But for MTech and ME the coursework will be more, which means 10. So we generally break down like this: 4, 4 and 2. Some people even break it down like this, maybe 3, 3 and 4, or something like this. But whatever it is, in 4 semesters you are supposed to finish 10 courses. Now one of the deciding factor, main factor that people will use in picking up a course is what grade will that faculty give. So what they'll do is they'll take the average, they'll go and talk to their seniors, and then they'll ask how many people have taken this course, out of which how many people have got A grade, how many people have got B grade. So depending on the probability, they will register for the course. If a course is having higher probability that you might get A grade, then people will register for that more. For example, generally TOC faculty will be giving good grades. That is why most of the people they will be registering for TOC. And then generally CO will be taught by a faculty, and it will be really difficult, and so no one will register. Even sometimes I have even seen that one student will register for the course, and there will be one student in the class and one faculty. It will just be a discussion. They will just sit and discuss. There will be no teaching. They will just sit and discuss. Sometimes 2 students will be there. And for a course like algorithms, which is very easy and which is very scoring, because algorithms you have in BTech and you have in GATE, and again you will be it will be very easy comparatively. So since everyone knows that subject, everyone will try to register it. One thing is, it is important as well as it is easy. So everyone will register it. So if you want to see entire people, all the people of the department, you will register that course. For some courses, it will be classroom will be very full. That all depends on how easily how entertaining the faculty is, and how much easily he is going to give the good grades. And some faculty, if they are giving bad grades, then no one will take the course. But it should not be that way. I mean, you should not really be worrying about the grades once you get into IITs or IISc. Whatever your grade is, everyone is going to get a job, and almost more or less the salary that you draw is going to be same. And in fact, if you have a degree from IISc or IIT, and once you have one job at your hand, then getting another job is not a difficult thing. Whatever interview you go for, you'll definitely get a job. Almost all the companies will take you. Therefore you are not supposed to worry about grades. Yes, even if I say it now, still after going into those colleges, you'll still be worrying about grades, and you'll still be worrying about jobs. And everything will be based on the probability. What is the probability? What is the probability that I might get A grade if I take this course? Then what is the probability that I might take A grade if I take this course? Depending on those probabilities, you will evaluate which courses to take, right? But then what happens is, sometimes some courses are very, very important for computer science, let's say like algorithms, that they will make some of the courses to be compulsory. 1 or 2 courses you might have to take them. So one such course will be algorithms or something like that. That varies again from year to year. Okay, so anyway, this question is much related to this. So since we are talking about this question, I just wanted to tell you all these things. Okay, now let's come back to the question. See this: Ravi can either take biology or calculus. So why biology and calculus? Why not computer science subjects? Because I wanted something to start with B and something to start with C, so that when I write the formulas it will be easy for us to understand. That is the only reason. Ravi can either take biology or calculus. If he takes biology, then he will get an A grade with probability 1 by 2. If he takes calculus, then he gets an A grade with probability 1 by 3. Now which one will you take? Of course you are going to take biology, right? Even though biology is not going to be useful for us, since we are going to get a A grade with high probability, you might take it. But then still there is more here. He decides to base his decision based on the flip of a fair coin. Now he is going to take a coin and flip it, and depending on what is the output of this coin, he is going to decide whether to take biology or calculus. That is how he is going to use the coin, and the coin is fair, which means the probability of getting a head and tail is same, which is 1 by 2. Therefore probability of taking biology and calculus is 1 by 2. Now what is the probability that he will get an A in calculus? What is the probability that he will get an A in biology? Now if you read the question, it might look so trivial, very trivial. That is how the probability questions look like. They will be really difficult to understand the actual thing they are trying to ask. The language is so simple that it looks so trivial, but it is not so trivial. See this. Now they are saying that probability, if he takes biology, then the probability that he will get a grade is 1 by 2. If he takes calculus, then the probability that he will get is 1 by 3. That is directly given. And now they are asking what is the probability that he will get A in calculus, he will get A in biology. So you might say that, you might think that 1 by 2 and 1 by 3 are the answers. No, you have to think about it deeply. Now let us say P of A or P of B represents the probability with which he can choose biology. Now what is that? So when will he choose biology? He will flip the coin, and maybe he will assign either heads or tails to biology, and if anything that corresponding turns up, then he is going to take biology. Therefore probability of taking up biology is 1 by 2, because probability of getting a head or tail is 1 by 2. Similarly probability of taking calculus is again 1 by 2, right? And now even though it is clear that if he takes biology he will get a probability of 1 by 2, but he is not going to get a grade unless he takes biology. Try to understand it. They are dependent events. He will get an A in biology only if he takes biology. Without taking biology he will not get it. Therefore the given probability should be understood like this: probability of getting an A given that he takes biology is 1 by 2. That is the meaning of this statement, right? So it might not be easy to understand that right away in your first question, but with practice you will get it. Okay, and then probability of getting a given that he has taken calculus is equal to 1 by 3. This is how you should understand it. And now what is the question A? Question A is, what is the probability that he will get an A in calculus? So what does it mean? Question A is actually asking for two events should happen. One is probability that he takes calculus and he gets an A. This is what they are asking, right? He will get an A in calculus means it is actually probability of happening two events. So one is he has to choose calculus and then he has to get A. Now how can you write it? It is nothing but that multiplication theorem. Probability of taking calculus into probability of getting an A given that he has taken calculus. Now what is probability of taking calculus? 1 by 2. And what is the probability of getting A given that he has taken calculus? 1 by 2. Therefore it is going to be 1 by 4. This is the answer for the first one, right? And what about the second question, B? What is the probability that he will get an A in biology? So how to understand it? It is actually happening of two events. One is probability of taking taking biology and getting a grade, which is nothing but probability of taking biology into probability of getting an A, given that he has taken biology. Now what is it? Probability of taking biology is 1 by 2, and what is the probability of getting an A given that he has taken biology? 1 by 3, which is nothing but 1 by 6, right? Okay, now there is, okay, we can extend this question later. I'll again examine this question and then I'll again extend it. So keep this question, you write down this question, later I'll again refer to the same question. For now, for this question, this is the answer. Later I'll just extend it. Okay, see this question is again on multiplication theorem, where instead of having 2 events we are going to have more than 2, that is 3 events here. Now the question is like this: suppose that each of 3 men at a party throws his hat into the center of the room. The hats are first mixed up and each man randomly selects a hat. What is the probability that all of the 3 men selects his own hat? B, none of the 3 men selects his own hat. So try to understand this question. Now there are 3 men and they are having hats. Now they will take out their hats and throw them into center of the room. Now in the center of the room they are all mixed up, and now these 3 men, without looking at the hat, they are supposed to pick the hats at random. Now what is the probability that all the 3 men selects his own hat? Now we should say with what probability that they select their own hats, and B is none of the 3 men selects his own hat. So how to solve this question is, let's do this way. Now let's define 3 events. Now E1 is the event that person number 1 selects his own hat, and E2 is the event that person number 2 selects his own hat. Similarly, E3 is the event that person number 3 selects his own hat. Now what can we do with these events? See, first one is how to frame the first question in terms of these events. All of the 3 men select his own hat, which means we are supposed to talk about probability that E1, first person selects his own hat, and second person selects his own hat, and third person selects his own hat, right? Now are they actually dependent events or independent events? How to know about it? Simple. Now we have this collection. Once the first one chooses one hat, then the other person getting his own hat depends on what he has chosen, and the first person has chosen, isn't it? Once a person has removed a hat, now the probability that the second one will get his hat will depend on what first one has chosen. Therefore they are all dependent, or you can even think of it as a problem in which there are no replacements. So whenever there are no replacements, the events are dependent, right? And so whenever the events are dependent, we have to apply the conditional probability, not the normal probabilities. If the events are independent, then we can apply the independent events and normal probabilities. For example, if the problem would have been, let's say 3 men are there and they have just thrown the, okay, we shall see the problem later about the independent events. I'll again frame the question, but for now let's try to focus here. Now what is that we want to find out? E1, which means the first person has to pick his own hat, and second person has to pick his own hat, and the third person has to pick his own hat, right? See this. Now we have already seen how to write this in multiplication theorem or the chain rule. What is it? It is equal to probability that first person will pick his own hat, and then probability that second person will pick his own hat given that first person has picked his own hat, right? And then the probability that third person will pick his own hat given that first person and second person has picked up their own hats. Now let's try to analyze it. Now what is the probability that there are 3 hats? What is the probability that first person will pick his own hat? Out of 3, there is only one is his hat, right? Therefore the probability is 1 by 3. Why 1 by 3? Because there are totally 3 hats, out of which only one is his hat. That is why it is 1 by 3. multiplied with, now once you have picked up one hat, the first one has picked up one hat, there will be only two hats remaining, out of which only one hat is for E2. Therefore the probability that the second person will pick his own hat, given that the first person has already picked his own hat, is 1 by 2, because there are only two hats, out of which only one hat is the right hat. Okay, now what about this one? This is interesting. See this. Now already first one has picked up his own hat, second one has picked up his own hat, then definitely only one hat is remaining, which is certainly the third person's hat. Therefore if E1 and E2 has happened, which means if first person and second person has already picked up their own hats, then with 100% certainty that third person will pick up his own hat. Therefore it is 1, which means 100%. Therefore what is the probability? 1 by 6. The probability that all the three will pick up the their own hats is 1 by 6. Now look at the second one. None of the three will pick up their own hat. This is all of them will pick up their own hat. The second one is none of the three will pick up their own hat. Now by looking at this, you might feel that these two are complements, and you might try to write, or you might want to write 1 minus okay, let's try to frame this in terms of this. This is A. Let's try to frame B. None of them picks up his own hat, which means E1 should not pick, E2 should not pick, E2 complement, and E3 should not pick, and all these three events should happen, which means what is the second question? E1 should not pick, and E2 should not pick, and E3 should not pick. You might feel that these two are complements, but actually they are not complements, isn't it? So in fact this one can be written as P of E1 union E2 union E3 complement, isn't it? Therefore these two are definitely not complements, isn't it? So the complement of this one is E1 union E2 union E3. Or if you want to understand the difference in basic terms, see here all the three have to pick their own hats, here none of the three has to pick their own hats. Now what is the difference between two? Why can't I take the complement is this. So you cannot say that 1 minus all the three picks up their own hats is equal to all the three none of them pick their own hats. Actually none of them picks their own hats. Okay, let's see this one. What about the complement of this? It is a bit difficult to explain. Try to understand this. Now if I take the complement of this event, the event that all of the three men selects his own hat, if I take the complement of it, then it will contain various events. So what are they? Exactly one person picks up his own hat, and the two will not pick his own hat, and two people will pick his own hat, and one he will not pick, and then three people will not pick, all the three will not pick, which means if you take the complement of it, it is going to contain many cases. One case is exactly one picks right and two picks wrong, or two picks right and one picks wrong, and all the three picks wrong. That is why I cannot take the complement of this. I have to compute it separately. Now we can it is again looking like a intersection, and we might feel like applying the multiplication rule. Now let's see what happens if you apply the multiplication rule. P of E1 complement into P of E1 complement given E2 complement given E1 complement, and then P of E3 complement given E1 complement and E2 complement, which means the probability that first one does not pick the right hat, and then the probability that second one does not pick the right hat given that first one has not picked the right hat. Right? Now let's see this. It is clear that probability that first one will not pick the right hat is definitely going to be 2 by 3. The reason is simple. There are 3 hats and 2 of them are wrong hats, and if he picks any one of these 2, then it means that he didn't pick the right hat. That is why probability that first one not picking the right hat is 2 by 3. Fine, I agree. Now what about the probability that second one will not pick the right hat given that first one has not picked the right hat? this is a different thing, or this is difficult to answer. The reason is, if first one has not picked up the right hat, then there are two cases. First one might have picked up the second one's hat. In that case, see, what I mean to say is, you have hat number 1, you have hat number 2, and you have hat number 3. Now first one does not pick the right hat, means he will not pick this, but he might have picked any one of this. If he might have picked this second hat, then what are remaining? 1 and 3. Therefore the probability that E2 will definitely pick the wrong hat is going to be 1. It is certainly, whatever he picks, it is going to be wrong. Or the other choice is, now the first one, instead of picking up the hat 2, if he has picked up 3 and he didn't pick up 1 and 2, then for the second one the hats remaining will be 1 and 2. In this case, the probability of picking up a wrong hat for the second one is again going to be 1 by 2. Therefore if you try to analyze it using the multiplication theorem for this particular, for this type, it is difficult, because this part is not clear. This part is not only depending on the number, it is also depending on what type of hat E1 has picked up. That is why, instead of worrying about it, instead of evaluating this way, I'll take the other formula and evaluate it. See, if you can evaluate it using the first one, you can go ahead and do that, but then it is having too much complications, so I don't want to do it. I don't want to evaluate it using this. So that is why, instead of writing the multiplication theorem directly here and evaluating it, I'll take this one. This one is looking somewhat better for me. So let me see how to do this. Now how can you write about this? This is equal to 1 minus probability of E1 union E2 union E3. So how can I write this? I have already given you this, right? So I have already explained you that probability of E complement is equal to 1 minus probability of E. Similarly, if you take this entire thing as one event, E1 union E2 union E3, then I can directly write like this. So in order to solve this question, I have to solve this one. In order to solve this, I have to solve this. Now I have to solve this part. What is it? P of E1 union E2 union E3. P of E1 union E2 union E3, right? So are they mutual exclusive events? Mutual exclusive means, will there be anything in an intersection, which means, will there be a chance that both E1 and E2 will pick the same ball like this, or pick the same hat like this? Can I say that E1, E2, E3 are like this? E1, E2, E3 are like this? Or can I say that E1, E2, E3 are like this? What do you think is right? See, why should I worry about it? Yes, you should worry about it, because based on what you think E1, E2 and E3 looks like, depending on that, this formula will vary. Probability of E1 union E2 union E3, based on how these two will be looking like, you have to apply the formula. In case if they are looking like this, then probability of E1 union E2 union E3 is directly probability of E1 plus probability of E2 plus probability of E3. In case if they are looking like this, then probability of E1 union E2 union E3 is, we have to add them, and when you are adding all of them, you might have added some of the parts 2 times, right? And therefore you are supposed to subtract them, right? So that is the reason you should be knowing how it looks like. So how to find it out? Depending on the nature of the question, you can find it out. See, now if E1 represents the event that person number 1 selects his own hat, and E2 represents the event that person number 2 selects his own hat, and E3 represents the event that person number 3 picks up his own hat, then what does this part represent? This particular part represents this part. This part represents the probability that both E1 and E2 will pick up their own hats. Is there a probability for that or not? Yes, it is definitely probable. It is probable that there is a chance that E1 and E2 will pick up his own hat. Similarly, will there be this event? Yes. What is this event? All the 3 will pick up his own hats, right? Their own hats, right? So definitely all the areas are possible. So now let's expand this formula, keeping in mind that all the areas are possible. Now what is that? P of E1 union. So union is nothing but plus. So I am just applying the formula from the set theory, right? P of E1 plus E2 plus E3 minus P of E1 E2, which means E1 intersection E2, minus P of E2 intersection E3 minus P of E1 intersection E3 plus P of E1 intersection E2 intersection E3, right? Yes. Now it will be easy for me. So what about P of E1? What is the probability of first person or one person, the first person picking up his own hat? 1 by 3. What about the probability of second person picking up his own hat? 1 by 3. Third person is 1 by 3, right? These things I know. Now only thing that I have to find out is P of E1 intersection E2, E2 intersection E3 and E3 intersection E2. These parts, these three parts I have to find out, and then this part I have to find out. I'll use the multiplication theorem. See this. Now the first one is P of E1 intersection E2. Now how can I write it? Probability that E1 and E2 will have taken the right one. So it is nothing but probability of E1 happening multiplied with probability of E2 happening, given that E1 has already happened, which is nothing but, what is probability of E1 happening? What is probability of the first person picking up his own hat? 1 by 3. What is the probability of second person picking up his own hat, given that first person has picked up his hat? It is nothing but 1 by 2. So which means 1 by 6. Similarly, you can find out E2 intersection E3. P of E2 intersection E3. Now we are not interested about the first one. So now what about the probability? Now assume that second person is picking up the first. So what about the probability that second person will pick up the hat? 1 by 3. And what about the probability that third person will pick up the hat, right hat, given that second person has picked up 1 by 2, which is 1 by 6. See, when we are talking about it, don't worry about the first person, he is out of the game. Now we have 3 hats and only these 2 people, that is how we got it. And similarly, on the same grounds, you will even get P of E1 intersection E3 is equal to 1 by 6, right? So in order to understand how these are possible, you might have to watch this video once and again, over and again. So please watch this concept in this video again and again till you understand this, okay? And the next one I have to find out is this one. So what is P of E1 intersection E2 intersection E3? P of E1 intersection E2 intersection E3. Person 1 first picks up, assume that, and then given that person 1 has picked up the correct one, what about person 2, right? So I think we have already found it out. P1 of E1 intersection E2 intersection E3 is 1 by 6. This one we have already found out, 1 by 6, right? So this part is 1 by 6, this part is 1 by 6, 1 by 6, 1 by 6, and this part is 1 by 6. Now if you substitute them, I think you are going to get 2 by 3. Therefore this factor is going to be 2 by 3. So this entire factor is going to be 2 by 3, right? Therefore, what is the probability that none of them will pick up the right hat? It is 1 minus 2 by 3, which is 1 by 3. Therefore the answer for B is 1 by 3. Okay, so if you feel that I might have rushed up a bit in this question, you please watch it over and again and you try to analyze it yourself. You'll understand it, you will definitely understand it, and it is very important that you understand this question. Okay, fine. Now let's see a question on this multiplication theorem. Let us assume that there is a lock, okay, and then there is a bunch of keys. So 1, 2, 3, 4, 5, 6, 7, 8. Let us say there are 8 keys like this. There is one lock and 8 keys, and only one of them is going to be the correct fit. Now we'll conduct an experiment in which each time we'll pick up a key and we try to open the lock, and in case if you open it, we'll be happy. Otherwise we'll throw away that key and pick up the next one from the bunch, which means it is similar to the question where we are going to pick up the balls from a box and we are not going to replace the ball before picking up the next one. Got it? So it is actually a question which is similar to without replacement, right? So now whenever we are talking about the cases where we are not going to replace and we are going to conduct the experiment, then we have to get into picture the conditional probability, because the probability is going to change, right? So now the question is, what is the probability that we will be able to open the lock in the 7th try? Okay, so now we have 8 keys. What will be the probability that we will be able to open the lock in the 7th try? Let us say Li is the event in which the lock gets opened in the 8th try. If Li is the event in which lock gets open in 8th try, then how can you write this question? So you can write this like this: probability of L1 bar, which means lock should not open in the first try, intersection L2 bar, which means L2 complement, which means lock should not open in the second try, so on, right? So lock should not open in the third try, lock should not open in the fourth try, lock should not open in the fifth try, lock should not open in the sixth try, but lock should get opened in the 7th try, isn't it? Now you can open it and you can write it in the chain form in like conditional probability, right? So how can you write it? It is P of L1 complement multiplied with P of L2 complement given L1 complement multiplied with P of L3 complement given L1 complement and L2 complement, so on, right? So what will be the last term? P of L7, which means 7th try should succeed, given that first try didn't succeed, second try didn't succeed, so on, 6th try didn't succeed. That is how you should expand it. Now what is the probability that the first try will fail? So out of these 8 keys, 7 keys are going to be wrong keys. So in the first try you are going to choose any one of these 7 keys out of the 8 keys, right? And then once you try it, once you fail, then we definitely know that that key which you have chosen in the first try is wrong and we are going to throw it away. Then there will be 7 keys remaining. Let's say you have picked it up, you have thrown it out, then we have 7 keys remaining, out of which 6 are wrong keys. Now in the second try, if it has to fail, you should pick one of the 6 wrong keys, total out of 7 keys, right? Similarly, for the third try to fail, we have to pick one of the 5 wrong keys out of 6 keys, and for the next try we have to pick one of the 4 wrong keys out of 5 keys, right? So this is the first try, second try, third try, fourth try, and next we have to find out the 5th try. For the 5th try we have 3 wrong keys out of 4 right keys, right? And then for the 6th try we have 2 wrong keys out of 3 total keys, and for the 7th try we have actually 2 keys remaining, out of which one is the right key and the other is the wrong key. So this is the answer, right? So again, this is also a kind of application of multiplication theorem. Okay, fine. Now 2 events are said to be independent if the knowledge of one event happening does not affect the probability of other event happening. Okay, so what I mean by this is, see, now let us say we are talking about independent events. Now let us say we have a coin, fair coin, and it is fair, which means probability of getting a head is equal to 1 by 2, as well as probability of getting a tail is equal to 1 by 2. So equal chances that we get head or tails. Let's say that is the case, that is the kind of coin we have. Now if I toss it 2 times, what is the probability of getting 2 heads? If I toss it 2 times, what is the probability of getting 2 heads? Now I can actually think of it as if it is happening of 2 events. First event is getting a head in the first flip, and the second event is getting a head in the second flip. Now I want to find out the intersection of these two, which means we should get a head in the first flip as well as we should get a flip in the second head in the second flip. This is the probability I wanted. Now, according to conditional probability, what we can write? Already we have seen the multiplication theorem. In multiplication theorem, I told you that whenever we have any happening of two events, we could use this formula. What is it? Probability of getting ahead in the first flip into probability of getting ahead in the second flip, given that first flip has already turned out to be ahead, right? Now probability of getting ahead in the first flip will be nothing but probability of getting ahead, which is equal to 1 by 2, as well as probability of getting ahead in the second flip, given that first flip is ahead, is also equal to probability of getting ahead, which means this one is going to be 1 by 2 and this one is going to be 1 by 2. So what I mean to say is the probability of getting ahead, given that already ahead has occurred, it didn't change, it didn't increase or it didn't decrease. Therefore, such events are called as independent events. So don't get confused between mutual exclusive events and independent events. Mutual exclusive events are such events in which which actually have the same kind of sample space, but they don't have anything in intersection. That is mutual exclusive events. See this. Now, if you have a sample space, if you have two events like this and there is nothing in common, they are called mutual independent events, mutual exclusive events, sorry. And what about independent events? Independent events are those events in which we, even though if we know that one event has already occurred, that will not change the probability that other event will occur. Such events are called as independent events. So simple example, if you want to ask, then the example will be flipping a coin 2 times. Now the second time, whatever result you get, that will be completely independent of what has happened in the first time. That is how gambling runs, isn't it? In gambling, we have various tables and outcomes will be random, and the second outcome will never depend on what has happened in the first outcome. If that is the case, if you think that the second outcome depends on what has happened earlier, then it will not be gambling anymore. You will be able to predict the outcome with certainty, right? So independent events are these. What is it? Happening of one event will not tell us anything about happening of the other event, and the probability of the second event happening will not change because the first event has happened. So in order to understand it in terms of the conditional probability formula, you can think of it like this. Let us assume that A and B, these are two events. If A and B are two events, and if you know that they are independent events, then probability of A happening, given that B has already happened, will still be initial probability of A happening. Similarly, probability of B happening, given that A has already happened, will still be probability of B happening, right, initially, which means here A is independent of B and here B is independent of A. So if A and B are two independent events, then you can think of it like this. Then these two formulas will be valid. Now, under the light of these new formulas, let's now examine that multiplication theorem. In multiplication theorem, we know that if A and B are two events, then we have already seen this probability of A into probability of B given A, right? Now assume that these two are independent events. If these two are independent events, then what can we say? Since probability of B given A is equal to probability of B, I am going to substitute it, which means probability of A into probability of B. This is very important. So probability of A given B is equal to probability of A into probability of B. So this is very important formula, probability of A into probability of B, right? So when is it valid? This formula is valid only when A and B are two independent events, right? So if it is given that in a question, if it is given that A and B are two independent events, then what is the probability that A and B will simultaneously occur? Then it is probability of A into probability of B. Now it can even be extended to more than two events. For example, if A, B and C are three independent events, then probability of A, B, C combinedly happening is equal to probability of A into probability of B into probability of C. Got it? So one way to understand it is, if it is already given that A and B are independent events, then we can apply this formula. And the second way is, if you can find out that for any two events this formula holds, then we can declare that they are independent events. It is important. See, understanding this one is easy. So what is it? If any two events are independent, then we can derive this, and from that we can derive this one, right? P of A intersection B equal to P of A into P of B. But then the reverse one is even important. The reverse is, if you find out that for any two events it so happens that P of A intersection B is equal to P of A into P of B, right? Then we can say that if this is the case, if it happens, right, then we can say that the two events are independent. Okay, I'll take examples and explain you, so don't worry. Let's just try to understand only this concept first. What is the concept? Two events are said to be independent if A in P of A intersection B equal to A into B. So now what can I write here is like this. Understand this one. See, two events are said to be independent. I write if and only if, IFF, it is important. If and only if P of A intersection B equal to P of A into P of B. Two events A and B, A comma B, are said to be independent if. So what is the meaning of it? In the question, if they have already given that they are independent, then you can use this formula, or if you can derive that P of A intersection B equal to P of A into P of B, then you can say that they are independent events. Both ways we can apply it. That is what I wanted to tell you, right? So the reverse one is important. So this one is straightforward. If it is given that they are independent, you will directly say that this one is true. But then identifying that without them saying that they are independent events, identifying this one and then from that you deriving that they are independent is important. Okay, so we'll see questions on both of this. And now, what if you have more than one item is, if you have n elements, n events, E1, E2, E3, so on, En. If you have to say that all these n elements are independent events, then for every subset of this, that formula should hold, multiplication rule should hold, which means if you take probability of Ei intersection Ej intersection so on El, something like this, it should always be probability of Ei into probability of Ej so on into probability of El, which means if you are having three elements and if you want to say that all those three are independent events, it is not just enough that this one should hold, it should also be holding that P of these two, P of A intersection B should be equal to P of A into P of B, and P of B intersection C should be equal to P of B into P of C, and similarly P of A intersection C should be equal to P of A into P of C, all of them, and even this one should hold. So what I mean to say is, if you have n elements, if you take any subset of these n elements, right, you have to take two set elements, three set elements, and then four elements. Any of them if you take and if you apply the intersection, this multiplication rule should hold. Then only we can say that these n elements are independent. In general, we will not be getting questions about more than two events. Generally they will be asking us questions in GATE. If you look at it, generally they will be asking the questions about independent events given only two events. They will not give you 10 events or 3 or 4. In case if they ask you, we can still solve 3 elements. I'll just take 3 event examples and I'll explain you. Okay, let's look at the examples, that way you'll understand it better. Now let's see the same kind of examples which we have seen in conditional probability where the events were dependent. Now let's see what happens if the events are made independent. In the sense, let's check the same examples like this. Let us say in a bag there are 3 green balls and 2 red balls. Okay, and now we want to conduct an experiment, or we are going to do 2 trials in which I'll draw 2 balls from the bag. First I'll draw a ball from the bag, and then I'll place it back, and then take the next one, which means here I am going to conduct the experiment with replacement. So earlier what I did was I have taken a ball and then I didn't replace it. Therefore the probability for the next ball is definitely going to affect, because the number of blue balls or green balls or red balls, they are going to change, as well as the total number of balls are also going to change. That is why earlier the probability of the second draw is going to change or get affected based on what has happened on the first one, right? In case if you take out the ball and then again put it back, then it is not going to affect the second one, isn't it? So now let us say in this experiment I am going to draw ball 2 times. What is the probability that I get a green ball in the first draw, and a red ball in the second try? Okay, so what I wanted to know is probability of getting a green ball in the first try and probability of getting a red ball in the second try. But remember that in this question it is given that we are going to replace, which means after taking out the ball in the first time, the green ball, I'll again replace it back. Now if you do this, what is the probability of getting green ball first time and red ball second time? Now see this is now these 2 are independent events. How can you identify that they are independent events? Sometimes in the question it will be so trivial that you will be able to identify that they are independent events, and sometimes they will give you in the question the word independent, right? Otherwise we cannot answer it. So in this question it is so trivial because we are going to replace. When you are going to replace, the probabilities are not going to change, right? That is why it is so trivial here. Now it is equal to probability of getting a green ball in the first try intersection probability of getting a red ball in the second try. Now what is the probability of getting a green ball in the first try? We have totally 5 balls, out of which 3 are green. That is why it is 3 by 5, right? Intersection is nothing but here multiplication, right? I am just using that independent event formula multiplied with probability of getting the red ball in the second time. So 2 red balls will be there, total balls will be 5. Earlier it was 4, now it was 5. In the earlier question when they were dependent events, which means when I didn't replace the ball, here you might have seen that I have written 4, isn't it? Okay, now let's say what is the probability that we get 3 green balls. I'll conduct this experiment 3 times. I'll try it for 3 times, and each time I'll try to pick out a ball. Now what is the probability that first time you get a green ball and then again you replace it back, second time you get a green ball, again replace it back, and third time you get a green ball? Again here we are talking about with replacement. So whenever we are doing the experiment with replacement, remember that they are independent events. In case if you don't replace it, they are dependent events, right? But here they are independent events. Now what is the probability of getting green ball in the first trial and green ball in the second trial and green ball in the third trial? All the 3 trials are going to give me green balls. What is the probability for that? It is equal to probability of getting green ball in the first trial into probability of getting green ball in the second trial into probability of getting the green ball in the third trial, right? So what is this? Probability of getting green ball in the first trial is going to be 3 by 5. Now what will be the probability of getting the green ball in the second trial also? Now since that as we have already replaced the green ball back, the number of green balls in the bag are not going to change, as well as total number of balls are also not going to change. Therefore this probability should not change, right? That is why they are independent. Now this is equal to 3 by 5. This one is also equal to 3 by 5. The reason is we are actually replacing the balls back. That is why it is 3 by 5 into 3 by 5 into 3 by 5. right? Now let us say we have three different bags. Okay, this is bag A, this is bag B, this is bag C. Now assume that I have three red balls here and two green balls, three red balls here, five green balls, and then one red ball here and four green balls. So this is it. Now if I am trying to draw one ball from each bag, then what is the probability of getting green ball from bag A and red ball from bag B, and let's say green ball from bag C? This is what I wanted. Now understand this, we have three different bags, and from each bag I am going to withdraw the balls, right? Now what is the probability that this event happens? When I see the ball which I drawn from the bag A, it should be green, and from bag B it should be red, and from bag C it should be green. What is it? So how can we do it? It is nothing but probability of getting a green ball from bag A intersection probability of getting a red ball from bag B intersection getting a green ball from bag C. Now what is it? It is equal to, all these are independent events. Why are they independent event? Because the probability of getting, even though if you know that I got a green ball or red ball here, it does not affect the probability of getting a green ball or red ball here, right? Which means the probabilities which will happen here will not affect the probability of event happening here, or this one will not affect the probabilities here. That is why they are all independent, right? So that is what you should identify. Now that equal to probability of getting a green ball from bag A. So what is it? 2 by 5, isn't it? Into, okay, so you can write this formula also. Probability of getting a green ball from bag A multiplied with probability of getting a red ball from bag B multiplied with probability of getting a green ball from bag C. Now what is the probability of getting a green ball from bag A? It is 2 by 5, because 2 green balls are there out of 5 balls, multiplied with red ball from bag B, so it is 3 by 8. 3 red balls are there out of total 8 balls, multiplied with green ball from C, so green ball from C is 4 by 5, right? So this is the probability that you should be getting. Okay, and now let us say, instead of I'll just mix up the question. There is nothing new that you will be learning from this model, but just for the sake of practice I want to do one more. You are not going to learn anything anyway, okay, from this again solving the same question, but let's do it for the practice. Now let us say, instead of saying that we get a certain ball from each bag, let's say the question is, I'll draw 3 balls, one from each bag, then what is the probability that we get 2 green balls and 1 red ball? So they didn't give you from which bag we'll be getting it. Are you trying to find it? See, now they are saying that we have 3 bags. Now we have to draw 1 ball from each bag. So totally we will be drawing 3 balls. What is the probability that this event happens? Which means after that, if you see it, we should get 2 green balls. I don't care from which one you have drawn it. Later I'll change the question. See, why am I doing this? Later I will even change the question and I'll ask you, if you got 2 green balls and 1 red ball, what is the probability that you might have got red ball from bag A? Later I'll do that also, but for now fix your attention here. Now what I wanted is, the question is, we have 3 bags and I want to draw 1 ball from each bag. Now after having 3 balls, if you see them, what is the probability that you have picked up 2 green balls and 1 red ball? So how to answer it? Now if you have to get 2 green balls from and 1 red ball, any of these 3 events can happen. What are the 3 events? See this, if we have A, B, C, these are the 3 bags. Now if you want 2 green balls and 1 red ball, it might so happen that red might come from A and these two might come from this, right? or it might so happen that green might come from this, red might come from this, and green might come from this, or green might come from this and red might come. This is the total probability, isn't it? The total probability that this event happening is this one. Got it? So now let's try this. Now what about this one? What is the probability that this one will happen? So red from here, green and green, all these three are independent. So what about this? Red from here is 3 by 5, and green from B is 5 by 8, and green from C is 4 by 5, right? Plus, why am I doing plus? Because these three are three different events. Now what I wanted to do is let us call it E1, let us call it E2, let us call it E3. Now I want to find out E1 union E2 union E3, and moreover these three are mutually exclusive events, right? So that is why I have to add the probabilities of each one. Got it? Now what about the probability? See, they are independent events, and then I am adding up three mutual exclusive events by using the union formula. Got it? So what I am effectively trying to do is I am actually writing this event of getting two green balls and one red ball as sum of three events in which I get a red ball from A, green ball from B, green ball from C. For that I am going to evaluate the probability, and plus, because the second case will also lead us to the same event where I get two green balls and one red ball, right? Now what about the second one? One green ball, one red ball and one green ball. So first one I should get green ball from A, which is nothing but 2 by 5, and then red ball from B, which is nothing but 3 by 8, and then green ball from C, which is nothing but 4 by 5. Now what about the third one? Green ball and red ball. So one green ball from A is 2 by 5, and one green ball from B is I think 5 by 8. These numbers you can work out, I am not sure. Even if I do something wrong here, you can see it, they are easy. So what I am interested is not showing those exact answer, I just want you to understand the method. I hope you are getting this, right? So what is that? What is the meaning of it? So whenever, if you know that one event has happened, and then the next event, if you are talking about, if the result of the next event does not depend on what has happened in the first event, then they are called as independent events. And remember this, whenever you are talking about such experiments, withdrawing something or doing something, if you are replacing the whatever has happened back, if you take out a ball and replace it back, then it is going to lead us to independent events. If you take out something and if you don't replace it, definitely it is going to alter the probabilities for the next event. Therefore in that case you have to be careful, and in that case it is going to be dependent events. Got it? So earlier we have seen such kind of questions for the dependent events. Now this is the same question for independent events, right? Where we have modified the multiplication theorem in such a way that instead of using conditional probabilities, I am directly using the normal probabilities. Got it? Okay. Now let's see a real life example. So even though we have been seeing the examples of drawing balls from the bag, we generally don't do that in real life, isn't it? We generally don't sit and pick out the balls from a bag. So let me take a real life example. Let us say you want to marry a girl, and in order to marry a girl you have to convince her parents and then her brother. So you have to convince her dad first, and then her mom, let's say, and then her brother. These are the three people you have to convince. This is what happens in India, right? It is not just enough that you convince the girl, you have to convince everyone in their family as well. You'll understand it gradually. So now you have to convince her dad first, and then her mom, and then her brother. If any one of them doesn't like you, then you will not be able to marry her, right? So let us say the probability with which you will be able to convince her dad, which means the probability with which he might like you, is, let us say, 1 by 2. and the probability with which she might like you, her mom, is 1 by 3. So how will you know the probabilities? Maybe based on what inputs you got from her, from your would be, let's say you have collected all this information, like your dad wants all these qualities, and let us say you have half of them, and your mom wants all these qualities in a boy, and let's say you have got 1/3 of them, and then let's say her brother 1/4, right? So now what is the probability that you will eventually marry this girl? So you have to go through all these phases, right? If any of them fails, you will not be able to marry her. Now let us say in the question they have used the word that all the 3 family members think individually and independently and will not base their decision based on what others have decided. So they are independent events. So the event of dad liking you will be independent of the event of mom liking you. Then it is going to be independent events, isn't it? So what is when can you marry her? The probability that you marry the girl will be equal to probability that dad likes you and mom likes you, and let's say this marriage is m is probability of a, because here I am also using m. So dad likes you, mom likes you, and brother likes you, right? And since all these 3 are independent events, how will you know that they are independent events? How will you know that, how did you come to know about it? Because I'm just saying that in the question it is given that all of them think independently and will not base the decisions based on what others have decided. So they are completely independent events. So this will be equal to probability that her dad likes you into probability that her mom likes you into probability that her brother likes you. Now what is it? So this should be equal to, what is the probability that her dad likes you? 1 by 2 into probability that her mom likes you is 1 by 3 into probability that her brother likes you is 1 by 4. Got it? So you can sum it up. So that is how you can answer this question. Okay. There are some interesting kind of problems you can solve if you know that 2 events are independent. I'll take some examples. Okay, before taking the example and explaining you, let me explain you some properties here. From that we can take the example. Okay, now let us assume that 2 events A and B are independent, right? Which means we know that P of A intersection B equal to P of A and B, P of A into P of B. So if A and B are independent, then we can say that, what I mean to say is like this: if A comma B are independent events, then if A and B are independent events, if we can find it out, then A comma B complement, B complement comma A, and A complement comma B complement. So what I mean to say is, if you somehow found out that A and B are independent events, then we know that P of A intersection B is P of A into P of B. Okay, that leaves that part. If A and B are independent events, then A and B complement are independent, B complement and A are independent, as well as A complement and B complement all are independent. That is what I mean to say. So it is very easy to prove. You can remember them directly, or okay, let me prove it. If you want to prove it, I'll just prove it also. Let's see this. If you have to prove that A and B complement are independent, then what should I prove? I should prove this: P of A intersection B complement is equal to P of A into P of B complement, isn't it? That is what we talk about independent events. 2 events are said to be independent if this formula holds. A and B complement are going to be independent if P of A into P of B, P of A intersection B complement is equal to P of A into P of B complement, isn't it? Now let's try to prove this one. Now let us say we have A here and we have B here. Now what about A intersection B complement? A intersection B complement is nothing but this part, isn't it? See, I'm just proving it from the set theory rules. So A intersection B complement is going to be this part, isn't it? So how can you write A intersection B complement? I'm just taking LHS. Left hand side is P of A intersection B complement. Now that equal to P of, if you see this, now this part is nothing but P of A minus P of A intersection B. If you can write like that, this part is whatever is present in A minus whatever is present in A intersection B. So this is equal to P of A minus P of A intersection B, right? Now since we know that A and B are independent, we already know that P of A intersection B equal to P of A into P of B. So I'm going to write like this: P of A minus P of A into P of B. Now what do you get? If you take P of A as common, you are going to get 1 minus P of B. Now I already told you that 1 minus P of B is nothing but P of B complement, that equal to P of A into P of B complement. Got it? Okay. And now next we have to prove that this B prime and B complement and A are independent. If I have to prove that, I should prove this: P of B complement intersection A, it is equal to P of B complement into P of A. This is what I should prove, right? Now what can you say about this? Oh, it is same, is it? So I have to write it in a different: A complement and B. So I have to take it as A complement and B. I have to prove this one, right? Now if you take the set theory diagram and if you analyze it, this part is nothing but P of B intersection A complement, right? Which means it should be present in B and it should not be present in A, which means this part. Now how can you write it? It is nothing but P of B minus P of A intersection B, isn't it? Now if I take left hand side, I can write the left hand side of P of A prime intersection B as P of B minus P of A intersection B. Now we already know that P of A intersection B is equal to P of A into P of B, that equal to P of B minus P of A into P of B. Now if you pull out P of B as common, then we are going to get 1 minus P of A. Now it is nothing but P of B into P of A complement, right? So therefore we got it. So they are actually independent. Now what about the third one? We have to prove that A complement and B complement are independent. How can we prove it? P of A complement intersection B complement should be P of A complement into P of B complement. This is what should happen. Now let's try it. Now I can write this one as, this entire thing as P of A union B LHS, right? P of A union B whole complement. Now we know that it can be written as 1 minus P of A union B, isn't it? And now we know that P of A union B is equal to P of A plus P of B. See again, how did I write this? This is again from the set theory only, right? So we know that A prime intersection B prime is nothing but A union B whole complement, and we know that P of E complement is equal to 1 minus P of E. That is where I'm taking it from, and minus P of A intersection B. So whatever it is, ultimately we should write it in terms of P of A intersection B, because that is what we know. P of A intersection B equal to P of A into P of B, right? Now how can you write this? 1 minus P of A minus P of B plus P of A into P of B. Why? Because we already know that since A and B are independent, P of A intersection B is going to be P of A into P of B. Now what is this one? So 1 minus P of A minus, if you take P of B, it is going to be 1 minus P of A. Now if you pull out 1 minus P of A as common, then you are going to get it as 1 minus P of A into 1 minus P of B, which is nothing but P of A complement into P of B complement. So that is how we can say that A complement and B complement are independent. Got it? So if A and B are independent, then we can prove that all these are independent. It is not just for two events, you can prove it for more than two events also. If you can find out that E1, E2, so on, En are independent, then you can just use that formula. Like you can say that I'm talking about this. If you see that E1, E2, so on, En, there are n events, all these n events are independent, then you can take complement of any one of them and you can say that all these events will be independent, or you can take complement of all and you can say that all are independent, which means you can play with the complements as well. So why should this result be used, or where is it useful is, I'll just take an example in order to show how we can use it. Okay, in the next video I'll take an example. Now let's say we are having an interview, and in that interview we can select any number of people and assume that there are two people who are being interviewed, A and B. A and B. The probability that A will get the job, let's say P of A, the probability with which person A will get the job is 1 by 2, and let the probability with which B will get the job is 1 by 3. So 1 by 2 is the probability with which A will get selected in the job, in the interview process, and 1 by 3 is the probability that B will get selected in the interview process. And moreover, selection of A is independent of selection of B, and selection of B is independent of selection of A, which means let us assume that even though if A has been selected for the job, still there will be vacancy and there is a chance for B to get selected, which means these two are independent events. Let us say that is already given in the question. If they didn't give you in the question, then it will not be able to, you will not be able to answer. They are not trivial things. Got it? So in most of the questions they will directly give you the word that they are independent in the exam. Otherwise, if they talk about trivial questions like flipping a coin, if they say that we are flipping a fair coin for 10 times or we are rolling a dice for 10 times, then in that case they are independent, right? Or if they talk about replacing, if they are talking about the experiment with balls and a bag, then if they talk about replacing, then they are independent. Otherwise, other than that, they should use the word independent. Let us say in this question they have given you the word independent. So what is it? There is an interview and two people A and B are getting interviewed, and the probability that A gets selected is 1 by 2 and B getting selected is 1 by 3, and assume that A getting selected is independent of B getting selected. Both are independent events. Now we can frame some questions on that. Now the first question is, what is the probability that both of them will get selected? So which means they are asking about it, right? And one thing is A and B are independent. Since A and B are independent, we can say that P of A intersection B is P of A intersection P of B, which is this one, right? So which is 1 by 2 into 1 by 3. So how am I able to write it? Because they have already given that they are independent events. Fine, it is not interesting, it is simple, right? So the second question is, what is the probability that exactly one of them will get selected? So if you want exactly one of them to be selected, either A should get selected and B should not get selected, right? Exactly one should get selected. Then what is that I want? I want A to get selected and B should not get selected, plus A should not get selected and B should get selected. So these are the two events in which we are going to have exactly one person selected. Now since A and B are independent, we can say that A and B complement are also independent. How can we say it? Because we have just proven it right in the previous video. And since A and B are independent, A complement and B are also going to be independent. Therefore, what can you say about it? It is equal to P of A into P of B complement plus P of A complement into P of B. Now what about P of A into P of B complement? So P of A is equal to 1 by 2. What about P of B complement? It is nothing but 1 minus P of B, which is equal to 2 by 3. If P of B equal to 1 by 3, P of B complement is going to be 2 by 3. Anyway, I am not worried about the numbers, you check it. Now what about P of A complement? It is going to be 1 by 2 and it is going to be 1 by 3. Got it? So this is the probability with which exactly one person will get selected. Now what is the probability that no one gets selected? If you want both of them not to be selected, then it is going to be P of A should not get selected and B should not get selected. Now we know that already we have seen that if A and B are independent events, then A complement and B complement are also going to be independent, right? Then what can we say about it? P of A complement into P of B complement, which is equal to, how much is this? 1 by 2 into 2 by 3. This is the probability that none of them get selected. So if you want to see what is the probability that at least one getting selected, so at least one getting selected is nothing but you have to take exactly one getting selected or both of them getting selected, which means to this one if you add this one, this is, this is two of them getting selected, this is exactly one of them getting selected, you are going to get at least one getting selected, right? What about at most one getting selected? All these you can play with them, right? So at most one getting selected is, you can take this one, exactly 1 and 0, you can sum these two, then you are going to get at most 1. If you sum these two, then you are going to get at least 1. Okay, now let's see the same question which we have seen earlier in case of that dependent events conditional probability. Let us assume that we have a lock and we have 8 keys, 1 2 3 4 5 6 7 8 keys, bunch of 8 keys. Earlier what we did was we were trying to open the lock, this lock with a key. We'll select a key at random and we try to open it, and if you are not able to open that, we are going to throw the key away. But now let us say we'll take a key, we try to open it, and even if you are not able to open it, we let this key stay in the bunch, and next time when you try to pick the next key randomly, there is a chance that you'll pick the same one, right? So which means we'll take the bunch, we'll take a key and we try to open it, and then we put it back in the bunch and again we jumble them so that we don't remember which one we have picked earlier. Now given this scenario, what is the probability that we'll be able to open the lock in the 7th try? What is the probability that we open the lock in the 7th try? Earlier also we have seen the question in which there was no replacement of the key once you find out that it is wrong. But here, even though you found out that the key is wrong, you are going to let it stay in the bunch. Now how will it be different from the earlier question? In the earlier question, the probabilities were changing because the number of keys were changing. After each try, the number of keys were changing. Therefore, the probability of getting a success or failure in the next attempt is changing depending on what has happened in the earlier attempt. Now here, since we are replacing back, the number of keys are not changing. Therefore, every time when you try, the probability of success or the probability of failure, it will remain constant, right? So now let us say Li is the event that you open the lock successfully in the 8th try. Then what should this question be? Now this question is, you should fail for 6 times and then finally in the 7th time you should be able to open it, right? Now how can I write it? It is L1, first try I should fail, second try I should fail, third try I should fail, fourth try I should fail, fifth try I should fail, sixth try also I should fail, but then in the 7th try I should pass. So this is what should happen, right? And now this is equal to probability of this. These are all independent events, right? Probability of failing into, these are all multiplication. Since they are all independent events, I am just multiplying them. Probability of failing in the 4th trial into probability of failing in the 5th trial into probability of failing in the 6th trial into probability of passing in the 7th trial, right? So what about the probability of failure? Every time the probability of failure is going to be same because the number of keys are same. Now we know that out of these 8 keys, only one key is the right key and all the remaining 7 keys are wrong. Therefore, what is the probability of failing? It is 7 by 8, which is high. 7 by 8 into 7 by 8, because out of 8 keys available, 7 keys are wrong keys. Now you will fail when you pick one of the 7 keys, and even after knowing that you have failed one, since you are adding the key back to the bunch, it is going to be same. 7 by 8 into 7 by 8 into 7 by 8 into 7 by 8 into 7 by 8. We have to do it 6 times. 1 2 3 4 5 7 by 8, and finally in the 7th try it should be a success. So what is the probability of success? It is going to be 1 by 8. So this is the answer. So just compare this question with the question we did earlier. It is a bit different. Okay, fine. Now 90% of the questions which will be asked on independent events will be like this. They will give that 2 events are independent, and then they will ask you what is the probability that these 2 events will happen simultaneously, that is P of A intersection B. Then we can directly say that P of A intersection B equal to P of A into P of B. That is what is standard model. 90% of the questions will be like that, but another 10% of the questions will be bit different. So one way is they will directly give you that the events are independent, and now you are going to use the formula. Other way is they will just give you the numbers, the probabilities. They will give you the probability of P of A intersection B, and then they will give you the probability of P of A and P of B, or they will give you somehow to calculate this, which means they will give you this probability P of A intersection B, and then they will give you this probability of P of A and P of B, and now or they will directly give you these numbers, or they will give you some means by which you can calculate these numbers. After calculating these numbers, you are supposed to verify that this formula is satisfied. P of A intersection B is equal to P of A into P of B. And if you can verify that this formula is satisfied, then you can conclude that A and B are independent. Then they will ask you whether A and B are independent. Are you getting this? One way of asking the question is A and B are independent, it will be given, and you are supposed to use this formula, right? Second way is they will not say that they are independent. You are supposed to find out that this formula is valid, and from that you are supposed to find out that A and B are independent. Okay, so these 2 ways questions will be asked, but mainly questions will be asked on the first model. Now let's examine the second model as well. How can we conclude that 2 events are independent? Let's see that. For that, I'll take some examples. They are not very, see, one way is if you understand everything, they look so trivial that you might feel, why am I explaining all this? Second thing is they might take up a lot of your intuition that you might not understand it at all. Okay, try to please focus here, they are very important. Now let us say we are tossing 2 coins. When we flip 2 coins, what is the sample space? The sample space contains either both will be heads, or head and tail, or tail and head, or both will be tails. This is the sample space when you flip 2 coins, right? And now let us define 2 events. First event is, event E1 is getting a head on first coin, and let us define second event. E2 is getting a head on second coin. Now tell me, what can you derive about this? What is P of E1. So what does E1 contain? In fact, E1 will contain getting a head on first coin, which means E1 will contain these two, isn't it? This is E1, right? Now what about P of E1? Out of 4 events, 2 events are favoring E1, therefore it is going to be 2 by 4, which means 1 by 2, right? What about P of E2? P of E2 is getting a head on the second coin, so this is E2. Getting a head on second coin, oh, this one, right? So this event and this one is E2. These two are E2, right? First one and third one. So anyway, again there are 2 events favoring it, so it is 2 by 4, which is going to be 1 by 2. Now what can you say about P of E1 intersection E2? What is E1 intersection E2? Getting a head on first coin as well as getting a head on second coin. So which means getting a head on both the coins is E1 intersection E2, right? Getting a head on first coin and getting a head on second coin is E1 intersection E2. So what is it? It is only one event out of 4, therefore it is 1 by 4. Got it? So now if you observe this, using these numbers you can actually derive this. Using these numbers are actually satisfying this formula. What is it? P of E1 intersection E2 is equal to P of E1 into P of E2. Now what can you say about it? So E1 and E2 are independent. E1 and E2 are independent. So what does it mean? Getting a head on the first coin is independent of getting a head on the second coin, isn't it? So why should that be true? Because we are actually flipping 2 fair coins, and so when you are flipping the first coin, whatever output that comes on the first coin is completely independent of what happens into the second one. Even if you know that first one has turned out to be head, it does not mean that on that particular day everything that you flip is going to turn on head, isn't it? It is not that way. Therefore whatever output that you get on the first coin is actually independent of what you get on the second coin, and that is how we can prove it even from the reverse model. See, one way of asking this question is, given that 2 fair coins are tossed, what is the probability that we get 2 heads? Then what is it? P of E1 intersection E2 they are asking, and since they are directly saying that there are 2 coins are tossed, you can apply this formula directly because we know that they are independent events. And the other way is, even by using this method we can show that they are independent because this formula is satisfied, right? Just try to understand it a bit. It is not very easy. You might have to think a bit. Okay, see, what I mean to say is, now E1 is the event in which first one is going to get head. Now what are the elements that will be present in E1? First one is head, means head, first one is head, or head tail. These are the 2 events that are favoring E1 out of 4. That is why it is 2 by 4, 1 by 2. And similarly, second one is head, means either it is head, which means second one is head, or it is tail head, second one is head. And again it is 2 by 4, which is 1 by 2. Now P1 intersection P2 is nothing but we are to get both heads. In this case, P1 intersection P2 is this one. Only one event is favoring out of 4. That is why it is 1 by 4. Got it? Now it so happened that it is satisfied. Why do you think that it is satisfied? Because E1 and E2 are independent. So since it is satisfied, from that you can derive the fact that they are independent, isn't it? Now what are independent? Whatever happens on the first coin is independent of whatever happens on the second coin, right? So you can take any of such models, which means, for example, you can say first one is getting a head, second one is getting a tail. Then what about it? Again you will get the same thing. Both are independent. Whatever you take, you will end up getting the conclusion that both are independent. I hope you understood this. Okay, let me take one more example and make this point clear. I'll take few more examples and I'll make it clear. Right? This is not a very important model, but it is very important that you understand this. Now let's see one more example in which you have to derive that the events are independent, or you have to say whether the events are independent or not. Okay. Now let us say the experiment is about rolling 2 dice. When you are rolling 2 dice, what is the sample space? Sample space is going to contain 36 events, isn't it, or 36 elements. What are all the elements? 1 1, 1 2, 1 3, so on, 1 6, and again 2 1, 2 2, so on, 2 6. Similarly, you are going to have 6 1, 6 2, so on, 6 6. These are the 36 elements that will be present in the sample space. Got it? And now let's define one event, event E1. Now event E1 is getting a 4 on first die. What is the probability of E1? What is the probability of getting a 4 on the first die? Out of these 36 events, you will have 6 events or 6 elements with 4 in the first die, 4 1, 4 2, so on, 4 6. So out of 36 we have 6, that is 4 by 31, 6 by 36, which is 1 by 6. 1 by 6 is the probability of getting E1. Now let us say E2 is an event in which sum on the 2 dice, sum of 2 dice is, let's say, 6. So if you want sum to be 6, then what are the possible outcomes that we should expect on the dice? So what are the possible elements? One is 6 means 1 comma 5 and 5 comma 1, right? And similarly 2 comma 4 and 4 comma 2, and similarly 3 comma 3. Therefore, what is the probability? Probability of E2, it turned out to be how much? 5 by 36, isn't it? Now what about E1 intersection E2? So what is E1 intersection E2? The E1 is getting a 4 on the first die, and E2 is sum of the 2 dice is 6. So it is nothing but E1 intersection E2 is nothing but getting a 4 on the first die. So what is getting a 4 on the first die? This one, and getting a 6. So only this is intersection, this is present in both of them. If you want to see what will be present in E1, you can see it, 4 comma 1, 4 comma 2, right, 4 3, 4 4, 4 5 and 4 6. Got it? Now we have 4 to here and 4 to here. So what about both of them? So intersection is going to be 4 comma 2, and so probability of getting E1 intersection E2 is equal to 1 by 36. Now observe these numbers. Probability of getting E1 is 1 by 6, probability of getting E2 is 5 by 36, and probability of getting E1 intersection E2 is 1 by 36. Now clearly it is very clear that probability of E1 intersection E2 is not equal to probability of E1 into probability of E2, isn't it? You can check it. Why? Because left hand side happened to be 1 by 36 and the right hand side happened to be 1 by 6 into 5 by 36, right? Clearly they are not equal. So since this formula is not satisfied, we can now declare that they are not independent, which means E1 and E2 are dependent. So these two events are actually dependent. Now try to use your intuition and find out why. Now we are interested in getting a sum of 6 and the first die turned out to be 4. They are actually dependent. You should be happy. Why? If the total that you wanted is 6 and the first die turned out to be 4, therefore there is still a chance of getting a sum of 6, isn't it? In case if the first die turned out to be 6 then you should, you will never get a chance of getting a sum 6, isn't it? See, now let us say you are just rolling the dice. Instead of 4, if a 6 turned up, if for 6 has turned up, then what happens? You will never get a sum of 6, you will at least get a sum of 7. So still, even though you got 4 on the first die, since you are going to have since you still have the probability of getting a 6, you should be happy. Therefore they are dependent, right? Intuitively you should think about it. Intuitively you should have that feel. Okay, if you are not getting that feel, try to think about it and try to understand it. What I'm trying to say here is, you should be happy that the first die turned out to be 4, because still there is a chance of getting a 6, right? In case if the first die doesn't turn out to be 4, then the sum might not be possible to be 6. Therefore the event of getting a 6 as the sum is actually dependent on what happens on the first die, isn't it? If the first die happens to be 4, yes, you have the chance of getting the sum as 6. If the first die happens to be 6, you don't have a chance of getting the sum as 6. Got it? Therefore events, these two are dependent, they are not independent. Are you getting this? The sum of getting a 6 depends on what happens on the first die. Clearly, if it happens to be a number less than 6, you will be happy, and there is a probability that you might get a you will get something as 6, isn't it? If you get a number which is not less than 6, which is exactly 6, then you will not get it. Are you able to get it? Okay, so I'll just take one more example in case if you didn't understand it. Let's say E3 is an event that sum on the dice is 7. Okay, so what is the probability of E3? Now find out what are all the possibilities for E3. One possibility is 1 6 6 1. This is going to give us a sum of 7, and the other possibility is 2 5 5 2, right? And the other possibility is 3 4 and 4 3. Got it? So these are all the possibilities. So one possibility is are you getting all the possibilities? Now what about probability of E3? Out of 36 events, 6 elements are favoring us. So 6 by 36, which is nothing but 1 by 6. Now think about E1 intersection E3. So what is E1 intersection E3 here? So the event of getting a 4 on the first die and the sum of both the dice is equal to 7. So only one event will be favoring, which is 4 by 3, and so the probability is again 1 by 36. Now if you observe this, P of E1 equal to 1 by 6, P of E3 equal to 1 by 6, and E1 intersection E3 equal to 1 by 36. Now clearly you can clearly say that P of E1 intersection E3 is equal to P of E1 into P of E3. Why? Because left hand side turned out to be 1 by 36, this one is 1 by 6 and 1 by 6. Therefore these two are equal. So what can we say now? We can clearly say that E1 and E3 are independent events. Now you think about it intuitively. Why? The reason is, if you want a sum to be 7, then the sum event of getting a sum as 7 is independent of what happens on the first die, because whatever happens on the first die, still there is a chance of getting a 7. Either the first die is going to give you 1 or 2 or 3 or 4 or 5 or 6. You can think about it. Anything, either the first die is 1 or 2 or 3 or 4 or 5 or 6, whatever the first die is, still there is a chance of getting a sum of 7. Therefore we really don't depend on what happens on the first die. That is why these two events are independent, and this formula is clearly stating that. Got it? So since this formula is true, we can say that E1 and E3 are independent, and here E1 and E2 are dependent. Are you getting the idea? See, earlier in the event of getting 6 the first die can be either 1 or 2 or 3 or 4 or 5, but it cannot be 6. Therefore the event of getting a sum as 6 depends on what happens on the first dice. If it happens to be 1 to 5, there is a probability of getting the sum as 6. If it happens to be 6, there is no probability of getting the sum. Therefore they are actually depending on each other. But in this case, the probability of getting a sum as 7 is independent of what happens on the first die. Whatever number comes up, either it is 1 or 2 or 3 or 4 or 5 or 6, always there is a probability of getting, always there is a chance of getting the sum of 7. Therefore the event of getting a sum 7 is independent of what happens on the first die. So both are independent events. Got it? So that is how, even though they are not directly saying that they are dependent or independent, you can verify these numbers, and from there you can draw the conclusion that they are dependent or independent. Got it? Okay. Now let's say we have 4 balls in a bag, and all the 4 balls are equally likely to be drawn, which means when I try to draw a ball, it is equally possible that any of the 4 balls will come up. Now all the balls are numbered 1, 2, 3, 4. Okay, so 4 balls are there in the bag, all of them are numbered 1, 2, 3, 4. Then we have defined some events E, F, G. E is the event of getting ball number 1, ball number 2. F is the event of getting 1 and 3, and G is the event of getting 1 and 4. Now we are asked whether these 3 events E, F and G are they independent or not. So whether to find out whether if you have to find out whether they are independent or not, use that formula. So if there are only 2 events, and if you have to find out whether they are independent or not, then this one should be satisfied. What is it? Probability of E intersection F is equal to probability of E into probability of F. If it is satisfied, it is enough. But if you have 3 events E, F and G, and if you have to tell that they are all independent, then we have to take every 2 possible events, and you have to verify this one, and then you have to take all the 3 and you have to verify this. For example, in this case, if we have to find out whether E, F and G are independent or not, then we have to take them pairwise, which means E and F together, and then F and G. F intersection G is equal to P of F into P of G. You should verify this one is valid or not, as well as P of E and G. E intersection G, it should be E into this one. So you have to verify this pairwise, as well as you have to verify all the 3 events taken together, which means P of E intersection F intersection G, it should be P of E into P of F into P of G. So all these 4 should be satisfied. In case if you are having four events, and if you have to verify all the 4 are independent or not, then we have to take pairwise first, which means let us say E1, E2, E3, E4, right? Let us say we have 4 events E1, E2, E3, E4. Now if you have to verify whether these are independent events or not, then first you have to test for the pairwise, which means pairwise independence, like this, P of E1 into P of E2, right? Like this you have to test for all the 4, and then you have to test 3 taken together, which means E1 intersection E2 intersection E3. You should test whether it is satisfied or not, P of E1 into P of E2 into P of E3, right? So likewise you will get, I think, three equations, or 4C3 is how much? 4C3 is 4C1, which means 4 equations you will get. Here you get 6 equations, you have to verify all the 6 equations. Here you will get 4 equations, you have to verify all the 4 equations, as well as you have to verify this one also, all the 4 taken together. So that is why, since it is so much tedious, they might not ask you such questions in the GATE exam. They might ask you about 2 events, or at max 3 events. They will not go beyond that. Okay, so all of these have to be verified, and if all of them are satisfied, then only you can say that 4 events are independent. Here we are given only 3 events. Let's see whether they are independent or not. So if the 3 events have to be independent, then all these 4 equations have to be satisfied. Now let's take individual probabilities and then go ahead. We know that since there are 4 balls and all the 4 balls are having equally likely chances, so P of 1 is equal to P of 2 is equal to P of 3 is equal to P of 4, which means probability of getting ball number 1 is equal to probability of getting ball number 2 is equal to probability of getting ball number 3 is equal to probability of getting ball number 4, and all are equal to 1 by 4. And then P of E, probability of getting E event is nothing but 1 and 2, which means we have to sum of 1 2. So this has to be taken as if it is union of getting this one and this one, right? So it is not actually drawing 2 balls, it is what is the, independently we have to take event of getting 1 and event of getting 2, and we have to apply the union. So probability of getting this one is E is 1 by 2, because 1 by 4 plus 1 by 4, are you getting this? Right, this is what they are talking about. See, in our experiment, the sample space is containing 4 events, 1 2 3 4, and all the 4 are having equal probabilities of 1 by 4 1 by 4 1 by 4 1 by 4. Now they have taken 2 events together, which means 1 and 2 are taken. Then what do you get? 1 by 4 plus 1 by 4, which means 1 by 2. This event is nothing but, when you are drawing a ball, what is the probability that the ball happens to be either 1 or 2. So for 1 the probability is 1 by 4, and for 2 probability is 1 by 4, and when you sum them up it is going to be 1 by 2, right? And similarly probability of F is equal to 1 by 2. Similarly probability of G is equal to 1 by 2. Got it? Now let's verify whether these are possible or not. Now what about probability of E intersection F? If you look at E and F, in the E intersection F there is only one event, which is 1, which is nothing but, E intersection F is nothing but the probability of getting the ball number 1 when you draw a ball. What is the probability for that? It is 1 by 4. Therefore the probability for left hand side is nothing but probability of getting ball number 1, which is nothing but 1 by 4. Now what about right hand side? The right hand side probabilities are, for P of E it is 1 by 2 and P of F it is 1 by 2. So it is 1 by 2 into 1 by 2, which is equal to 1 by 4. Are you getting this? I am not deriving this probability from this formula. I am verifying whether this formula is valid or not. How am I doing this? E and F, if you take this, we have these 2 events in E and these 2 events in F. Now if you take the intersection, it is going to be 1 by 4. The reason is probability of getting ball number 1. So I am computing this independently, right? I am not computing it from this. Then I am computing this independently and I am just checking the numbers. Yes. So this particular property or this particular formula got satisfied, but then we cannot declare that everything is independent. But what we can say here is E and F are independent. That is what we can declare here. Okay. Now see this one. What is the probability of F intersection G? Check that. F intersection G is going to contain intersection in their intersection 1. Therefore it is 1 by 4. And what about P of F and P of G? If you look at P of F and P of G, P of F is containing 1 by 2 and P of G is containing 1 by 2. Therefore it is again 1 by 2. Therefore these two are equal, and so it is again satisfied. Formula number 2 is also satisfied. 1 is satisfied and 2 is satisfied. So what can you say from 2? F and G are independent. What can you say from 1? E and F are independent. But then let's see the third one also, the third formula. So what is it? E intersection G. So what is present in E and G? In E and G, the common intersection part is 1. Therefore left hand side is nothing but when you are drawing a ball, the probability of getting 1, which is equal to 1 by 4. And the right hand side is P of V into P of G. So P of E is again 1 by 2 and P of G is 1 by 2, which is equal to 1 by 4. So it is again valid. So the third formula is also valid, right? So what can you say about this? E and G are independent. But then even though these 3 formulas are satisfied, you cannot directly declare that E, F and G are independent. You have to even verify this, right? So how can you verify this one? See this. So what about E intersection F intersection G? In intersection we have only one element, which is 1. Then what is the probability of getting a 1? It is 1 by 4. Therefore for left hand side we got 1 by 4, and for right hand side here it is 1 by 2 into 1 by 2 into 1 by 2, so which is going to be 1 by 8. Therefore this formula is not satisfied. so they are not independent events. So what can you say? They are pairwise independent, but when all the three are taken together, they are not independent. Therefore the answer should be they are not independent. Got it? So which means they are dependent events. Okay, so how can you understand it? Whenever we are talking about more than two events, we are not just, it is not just sufficient that these three equations are satisfied, you have to satisfy all the remaining equations, right? So in case of three equations, three events, we have to check these four formulas. In case of more than 3, which means for 4 events, we have to check how many 6 plus 4 plus 1, 11 formula, right? So likewise, as the number of events increase, the number of formulas you might have to verify are going to increase to test whether they are independent or not. For that reason, you will not see a lot of questions in GATE about 4 or more events. At most you can see 3 events. That is why I am taking this example. Got it? And this example is very important because even though all the events are pairwise independent, but they are not independent taken all together. Got it? Okay. Now let's assume that a bag is having 150 good bulbs and 50 defective bulbs. Okay, so 50 bulbs are good and then 50 bulbs are defective. Now we'll conduct an experiment in which we'll draw the first bulb and then see whether it is defective or good, and then we replace it back, and then we take the next one and we do this at random, and the probability of getting any bulb are all equally likely. Okay, then what is the sample space? Let's first define the sample space. Okay, so what is the problem? We are having 50 good bulbs and 50 defective bulbs, and now we are going to draw 2 bulbs with replacement, which means we'll take the first bulb, put it back, and then take the second one. Then what is the sample space? Now the sample space will contain 4 events. What are they? Both the bulbs may be good, or first bulb may be good and second bulb may be bad, or first bulb may be bad, second bulb may be good, or both the bulbs may be bad. So these are the 4 events which are possible in the sample space. Now what is the probability of each event? See this. Now if you have to get a good bulb, it is going to be 50 by 100, and since you are replacing, the second good bulb will also have the same probability of 50 by 100, which means 1 by 2 into 1 by 2, which is nothing but 1 by 4. Therefore the probability for this good is going to be 1 by 4. Similarly, the probability for this one is also going to be 1 by 4, and the probability of this one is also going to be 1 by 4 and 1 by 4. All are equally likely. Got it? Fine. And now let's define 3 events. Let's say A is an event in such a way that the first bulb is good, right? Then what do you get in A? The first bulb is good means it is going to be good or good bad, and we know that the probability of this one is 1 by 2 and the probability of this one is 1 by 2. Then what is the probability of A happening? If the probability of A happening is equal to sum of these two, so which is nothing but 1 by, it is 1 by 4, right? 1 by 4 plus 1 by 4, which is 1 by 2. So probability of A equal to 1 by 2. Now let's say we define one more event B in which second bulb is good. Then what are the events you have in that? Good and then bad good. This probability of this one is 1 by 4 and the probability of this one is 1 by 4. Then what about probability of B? Probability of B is going to be 1 by 2, adding these two. Got it? And what about C? Let's define one more event C in which both the bulbs are either good or both the bulbs are either defective. See, in this one I think you got it right. G means good bulb, B means bad bulb. Okay. Now what about this? Both are going to be good bulbs or both are going to be defective. Again, this one has the probability 1 by 4, this one has got probability 1 by 4, therefore P of C is equal to 1 by 2. Now the question is, out of about these 3 events A, B, C, are these 3 events A, B, C independent or not? So we have to find out whether they are independent or not. So again, how can we find out when three events are given? We have to verify those four formulas. What are the four formulas? P of A intersection B, you should verify whether it is equal to P of A into P of B, right? And similarly, P of A intersection C, we should verify whether it is equal to P of A into P of C or not. And then P of B intersection C, we should verify whether it is equal to P of B into P of C. And similarly, we have to verify one more formula, P of A intersection B intersection C, it should be equal to P of A into P of B into P of C, right? Now what about P of A intersection B? Now if you look at this P of A intersection B, it is going to contain one event which is good bulb, right? Then what is the probability of that event happening? 1 by 4. Therefore left hand side probability, it is going to be 1 by 4. And what about right hand side? P of A into P of B. P of A equal to 1 by 2 and P of B equal to 1 by 2. Therefore here it is 1 by 2 and 1 by 2. So what can you say? A and B are independent. A and B are pairwise independent. But then we cannot say A, B, C are independent as of now, because we have to verify all of them. As of now we can say that A and B are independent. Now what about A and C? P of A intersection C. Now if you see A and C, the intersection is again good and good, right? Good bulb and good bulb. Now what is that? It is going to be, probability is going to be 1 by 4, which means this left hand side turned out to be 1 by 4. Now let's look at the right hand side. In the right hand side, P of A into P of C. P of A is 1 by 2, P of C is 1 by 2. So here I get 1 by 2 and 1 by 2. Now again this is also verified. So what can we say now? A and B are independent from this, as well as A and C are independent. That is what we can say. Now let's see this P of A, B intersection C. Now if you see B and C, if you see B intersection C, the intersection is going to be good and good, which means the probability for this event has to be 1 by 4, right? And what about P of B into P of C? Now if you see P of B, it is going to be 1 by 2, P of C is going to be 1 by 2. So 1 by 2 and 1 by 2. Again this is also verified. Therefore we can say that B and C are independent. Now if you see them, all the three events are actually pairwise independent, but then you cannot say that they are all independent events, because you have to verify this last formula as well. Now what about P of A intersection B intersection C? If you see A intersection B intersection C, it is going to contain the event good and good, right? So the probability of having two good bulbs is 1 by 4. Now what about this 1 by 2, 1 by 2, 1 by 2? Right hand side is 1 by 8, left hand side is 1 by 4, and both are not equal. Therefore this formula is not satisfied. So what can we say? These three events taken together are not independent, but any two events taken together are dependent. So if the question is whether all the three events are independent or not, no, they are not independent. If the question is if they are pairwise independent, yes, they are pairwise independent. Got it? Okay. Let's say we are going to flip a fair coin 5 times. So fair coin, which means probability of getting head is equal to probability of getting tail equal to 1 by 2. Now we are going to flip it 5 times, 1 by 1. So first time, second time, third time, like that 5 times. Then what is the probability that we don't get any two heads or any two tails consecutively? So which means we should never get head in the first trial and head in the second trial, or like that, which means two heads should not be consecutive and two tails should not be consecutive. Now see this. So if you don't have to get two heads or two tails consecutively, then it should be like this: head, tail, head, tail, head. This is one way. Or tail, head, tail, head, tail. So these are the two choices we have. Now we are going to toss the same coin 5 times, and it is a fair coin, right? And now we know that when you are tossing a coin any number of times, then all the events are independent, which means if you want the probability of having a head in the first trial, intersection having a tail in the second trial, intersection having head in the third trial, if you want the probability, it is nothing but multiplication. Got it? So whenever you take this, either you flip a coin, or you roll a dice, or you draw a card with replacement, or you draw a ball with replacement, or bulbs, whatever, if you are doing it with replacement right? Or if you are playing with a fair coin, then the probability of getting the head in the next trial is independent of the outcome of the first trial. Got it? So these are all independent events. Always remember this. When we are conducting a random experiment over and again, the outcomes of the experiment is going to be independent of what happened earlier. Okay, now see this. What is the probability of getting head in the first one, tail, and then head, tail, head? We know that since it is a fair coin, probability of getting head is 1 by 2, and probability of getting tail is 1 by 2. Again, getting head is 1 by 2, getting tail is 1 by 2, getting head is 1 by 2. Got it? Plus again same, getting tail is 1 by 2, head is 1 by 2, tail is 1 by 2, and head is 1 by 2, tail is 1 by 2. Got it? So this is how we can do it. So what is the main principle that I used here? Again, independent events model. Now let's see one more example where again we take independent events like this. If a person has to pass in an exam, he has to take 3 tests. Exam A, exam B, and exam C. Okay, let's take a real model. Let us say you are in +2 again. Go back to +2, and then we have 3 subjects, right? Physics, mathematics, chemistry, right? I think if you go back to +2 now, you will do much better and try to get into IITs, because now you know how important it is to get into IITs, right? Since you are already trying. So now let us say we have 3 subjects: physics, mathematics, and chemistry. Assume that the probability that a person A will pass the exam physics is 0.5 and will pass the exam mathematics is 0.6, let us say, and chemistry is 0.7. Now if it is given that all these 3 events are independent, which means the probability of a person passing in physics will not depend on whether he has passed in mathematics or chemistry. Similarly, the probability that he passes the mathematics will not depend on what happened in physics and chemistry test. So he is psychologically free. Now passing in one exam will not psychologically affect him or depress him in passing the other one. Therefore all the events are independent. Now these are the probabilities. Assume that. Now what is the probability that he will pass the that year +2? So in order to pass +2, he has to plus all these 3 events, right? Then again it is independent events, right? So the probability that he will pass +2 is equal to probability that he passes all the 3 courses. What are they? Physics, mathematics, and chemistry. Now since they are independent events, then we can directly write it as probability that he passes physics into probability that he passes mathematics into probability that he passes chemistry. Now what is it? It is equal to 0.5 into 0.6 into 0.7. Got it? And now what is the probability that he fails exactly one subject? If he has to fail exactly one subject, then it is going to be he might fail in physics, or he might fail in mathematics, or he might fail in chemistry. So these are the 3 cases, right? And since physics, mathematics, and chemistry are all independent, physics complement mathematics and chemistry are also independent. We have already proven it earlier, right? In one of the proofs I did it. So whenever you have 3 events which are independent, now if you take complement of any one and if you combine with the other events, it is going to be independent. Or if you take complement of any 2 events and combine with the other event, they are all going to be independent. Or you take complements of 3 events, they are all going to be independent. Now what is this? So it is equal to probability that he fails in physics into probability that he passes mathematics into probability that he passes chemistry, plus probability that he passes physics into probability that he fails mathematics into probability that he passes chemistry, plus probability that he passes physics into probability that he passes mathematics into probability that he fails chemistry, right? And what can you say about it? What is P of P complement? If P of P is 0.5, it is going to be 1 minus 0.5, which means 0.5, and then you can substitute other numbers. And what about this one? P of M complement is nothing but 1 minus P of M. So here you have to substitute 0.4, and these two can be substituted directly from this. And what about P of C complement? It is P1 minus P of C, which is nothing but 0.3. right? And you can substitute these two and you can get it. Now what is the probability that he fails in all the 3 courses? Then we have to write this. Probability that he fails in 3 courses is going to be this one, right? And again, if a P, M and C are independent events, then P complement, M complement and C complement are also going to be independent. So it is going to be like this, into P of C complement. Now what about each one? It is 0.5 into 0.4 into 0.3. Got it? So this is how you can answer this question. Okay, let's see this. If A, B and C are 3 independent events, so what do you mean by independent event? They are pairwise independent, as well as all of the 3 taken together are independent, like this. If A, B, C are independent events, then we know this. P of A intersection B, if you take any 2 of them, it is going to be P of A into P of B, right? And then P of B intersection C is going to be P of B into P of C, and similarly P of A intersection C is going to be P of A into P of C, right? So this is about pairwise independent. Now since it is given that A, B and C are independent, which means they are pairwise independent, as well as all of the 3 taken together should also be independent, which means P of A intersection B intersection C is going to be P of A into P of B into P of C. Okay, so these are all what we can draw if it is given that A, B and C are independent. Now we are supposed to prove that if A, B and C are independent events, then we have to prove that A and B union C are independent. Similarly B and A union C are independent. Similarly C and A union B are independent. So I'll prove this one, you can prove these two. Okay, not just this, you can even prove that A, B prime, C are independent, or A, B, C prime are independent, or A prime, B prime, C prime are independent. You can prove a lot of them, but I'll just show you one example and you can follow this lead and you can prove all the remaining. Okay, so now always remember that these results will be useful in solving some of the questions. Sometimes they'll say that 3 events are independent, and then they'll ask you the questions which might require that you know these results, right? If you don't know these results, you need not by heart them. You can even derive them in the exam. If you don't know the result, you should guess it, derive it, and then apply it to the question. Now let's see this example. We have to prove that the event A and the event B union C, both are independent. How can you prove it? If I have to prove this, let me see what happens with this P of A intersection B union C, right? So if we can prove that this one is equal to P of A into P of B union C, then I can say that these 2 events are independent. Got it? So I'll take the left hand side, LHS, and I'll try to get the right hand side. Now what is LHS? P of A intersection B union C. This one we already know. Now I'll use from the set theory distributive law. So what is distributive law say? Intersection is distributive over union, and union is distributive over intersection. So using the set theory concepts, I can rewrite like this. So it is going to be P of A intersection B union A intersection C, right? And then I'll use the union rule from set theory. So what is P of A union B from probability? Okay, what is P of A union B? It is going to be P of A plus P of B minus P of A intersection B. Now using that rule, I am going to expand it, assuming that this is one event and this is one event, right? Let us say this is E1 and it is E2. Then what is this formula? P of E1 union E2. Then how can I rewrite it? P of E1 plus P of E2 minus P of E1 intersection E2. I'll just expand it. Say this. P of E1 is nothing but A intersection B plus P of E2 is nothing but P of A intersection C minus P of intersection of these two. What is it? A intersection B intersection A intersection C. Right? Now we know that P of A intersection B is nothing but P of A into P of B. How do we know this? Because they are independent. So since A, B, C are independent, they are also pairwise independent. Therefore, P of A intersection B is going to be P of A into P of B. So it is going to be P of A into P of B plus P of A intersection C is going to be P of A into P of C minus, if you observe this event, it is P of A intersection B intersection A intersection C. Therefore, if you take the intersection of these two events, it is going to be A intersection B intersection C. See this. If you didn't understand this, let us say there is event A, there is event B, and assume that there is event C. Right? This is A, this is B, and this is C. Now what is A intersection B? A intersection B is going to be this entire part. Right? And what is A intersection C? A intersection C is going to be this part. Right? And now if you see it, what is the intersection of these two areas? It is going to be A intersection B intersection C. Got it? Therefore, it is going to be P of A intersection B intersection C. Right? And now we know that since A, B, C are independent, P of A intersection B intersection C is going to be P of A into P of B into P of C. So it is going to be P of A into P of B plus P of A into P of C minus P of A into P of B into P of C. Alright? So now from these three, you can clearly pull out P of A as common. Isn't it? It is a common factor. So I'll pull it out. Then what is remaining? P of B plus P of C minus P of B into P of C. Right? Then we know that since B and C are independent, P of B into P of C is going to be P of B intersection C, isn't it? So it is going to be P of B plus P of C minus P of B intersection C. Now what can we say about it? It is nothing but P of B union C. It is P of A into P of this entire thing is going to be P of B union C. Got it? So now if you see this, we have taken the left hand side, which is nothing but P of A intersection B union C, and we got that it is equal to P of A into P of B union C. Right? From these two we can say that A and B union C, these two events are independent, given that A, B, C are independent. Right? A and B union C, these two are independent, given that A, B, C are independent. Similarly, these two are independent. Similarly, these two are independent. Got it? Okay. Now, based on the rules that we have just proven earlier, we can even see this. Check this one. Let us say probability of an event A is given as 1 by 2. Probability of an event B is given as 1 by 3, and probability of an event C is given as 1 by 4. And if it is given that all these three events are independent, then they will ask you some questions like this. What is the probability of the event that A union B complement intersection C will happen? Right? Or they will give you some question like this. Is A complement union B union C complement. what is the probability of this, or they'll give you some question like this: what is the probability that A complement intersection B complement intersection C complement will happen. Now in order to answer these questions, you should know certain formulas like this. See, one thing is, if A, B and C are independent, you can prove that A union B complement and C, these two events are independent, right? We have earlier proven that A union B and C are independent, but you can still prove that A union B complement and C are independent. Also you can prove this one also, right? A complement union B complement and C, these two events are also independent, right? So now knowing such things will help you in answering these questions easily. So the reason is, see this, now if you want to find out the probability of this event P of this, right? So how are you going to write this? This one is nothing but two events. Now you know that these two events are independent and now there is an intersection between them. So how can you solve it? Just the multiplication rule, right? So P of A union B complement into P of C, and we know about this P of A union B complement. So what is P of A union B? It is straightforward: P of A plus P of B complement minus intersection of these two, P of A intersection B complement. Now P of A intersection B complement, since we know that A and B complement are already independent. Why? If A and B are independent, then A and B complement will also be independent. Now here we have to write P of A intersection B complement. We know that it is nothing but P of A into P of B complement. So when you are writing this intersection formulas, knowing that they are independent will be helpful. And finally multiply it with P of C. Got it? And similarly here we are having union, right? So we know that when you have union of three events, then you can write like this: P of this one is nothing but P of A complement plus P of B plus P of C complement minus, you have to take two events each, P of A complement intersection B minus P of B intersection C complement minus P of A intersection C complement plus P of A complement intersection B intersection C complement. Now these three probabilities are given, but in order to derive these four probabilities, you should know that all the events are independent. Since A and B are independent, A complement and B are independent. Since B and C are independent, B and C complement are independent. Since A and C are independent, A and C complement are independent. Since A, B, C are independent, A complement, B and C complement are independent. Therefore, you can evaluate it by taking the multiplication rule, right? And now check this one. If you want to find out the probability of this, how can you do that? Same way. Since A, B, C are independent, A complement, B complement and C complement will also be independent. And since it is intersection, you have to just take the product, which means P of A complement into P of B complement into P of C complement, right? And how can you answer this one? Same way. This is an event and this is an event. Since A, B, C are independent, we can prove that A complement union B complement and C, these two events will also be independent, and we can expand it the same way. How? If you want to find the probability, you have to apply the multiplication rule because these two events are independent, which means P of A complement union B complement into P of C. Now what is it? Now you have to evaluate P of A complement union B complement, which is nothing but P of A complement plus P of B complement minus P of A complement intersection B complement. Since A and B are independent, we know that A complement and B complement are also independent. Therefore, I can apply the product rule here. What is it? P of A complement intersection B complement is equal to P of A complement into B complement. Now you multiply with P of C. So any questions they might ask like that, you can just apply this rule and find it out. Okay, and there are one important interesting property here. Let us say A and B are two events which are mutually exclusive. Mutually exclusive means if you have the sample space, then A and B, there will be no intersection, which means if A happens, then B will not happen, and if B happens, then A will not be, A will not happen. Got it? Now if they are mutually exclusive, then what can you say about this independence, or the independent or dependent events? Let's try to find out. P of A intersection B, if it happens that P of A intersection B is equal to P of A into P of B, then we can say that these two events are independent. Now let's see this. In case of mutually exclusive events, there will be nothing in intersection, right? So P of A intersection B is going to be 0, which means left hand side is clearly going to be 0, but then right hand side will never be 0, because there is the probability for A is some positive number and probability for B is some positive number, because they are definitely going to happen, isn't it? Right? And now the product is never going to be 0. Therefore, if A and B are mutually exclusive events, then A and B will be dependent events, because this formula is not satisfied. It is very important to remember that if A and B are mutually exclusive, then they are dependent events. Why are they dependent? Because happening of A is depending on B and happening of B is depending on A. Why? If A happens, then B will not happen. If B happens, then A will not happen. That is how you can check it. Okay. Even though these two concepts are different in some sense, because mutual exclusiveness is related to set theory and independent events related to probability, but we can somehow combine them and get this result, right, from this formula. And also you can also derive this one. See this, if you have an event A and if the probability of A is 1, which means it is very certain that A will happen, definitely happen, then A is independent of any event B. Why? See this. Now P of A intersection B, if you try to find out, that will be P of A into P of B, right? That will simply be P of B, isn't it? Now what will be this P of A intersection B? Now since A is definitely possible, it must definitely be sample space, right? And then B must be something here. Therefore P of A intersection B will be equal to P of B itself. And also we got that it is equal to P of B. See, what do you mean by P of A equal to 1? A is the sample space. Sample space is the only event which is going to have the probability of 1, isn't it? When you are conducting the experiment, P of A equal to 1 is, P of S equal to 1. By saying that, what we really mean is one of the possible outcomes is definitely going to come out. That one anyone can say with 100% probability, isn't it? When you are flipping a coin, what is the probability that you will get either head or tails? 100%, which means 1, right? So if you take the entire sample space, the sample space is independent of any other event, because I don't care what event happens, always sample space happens, which means it is independent, isn't it? Similarly, you can also prove that if P of A is an event with probability 0, if A is an event with probability 0, which means if A is never possible, right, then A is independent of any other event. Why? If A is never possible, which means P of A intersection B, you can verify this formula, equal to P of A into P of B. Now A is never possible, then what is the intersection with B? It will never be possible, right? Which means if A happening is not, if A itself is never going to happen, what is the probability that A and B will happen? Never, which means it is 0. And already we know that P of A is 0, therefore 0 multiplied with anything here you write, it is going to be 0. Therefore this property is again satisfied. And so if P of A is equal to 0, then A is independent of any event. So, and similarly if P of A equal to 1, it is independent of any event. You can remember them. Okay. So this is how we can apply the independence formula in order to solve various questions. Okay, now let's see an example. Assume that the random experiment that we are going to conduct is like this. We have 3 bags. Let's call this as bag A, bag B and bag C. In bag A, let's say we have 2 green balls and 3 red balls, and in bag B, let's say we have 1 green ball and 4 red balls, and in bag C we have 3 green balls and 2 red balls. So assume that this is how the bags are containing the balls, and now the experiment is, first we'll choose a bag randomly, and then after choosing a bag we'll pick a ball from the bag. So the experiment is like this. Try to understand this. Now we have 3 bags and we are going to choose a bag randomly, which means, and all the bags are equally likely to be picked up. So therefore the probability of choosing a bag A is equal to probability of choosing bag B is equal to probability of choosing bag B, bag C, and all of them are equal, and since we have 3 bags, the probability is going to be 1/3 because we are going to have equally likely probability. That is the first one. We are going to pick one of the bags, and after picking one of the bags we are going to pick a ball from that bag chosen. Got it? Now what is the probability that the ball which we have picked up happens to be a green ball? Okay, so are you getting the picture? Now the experiment actually contains 2 events, and these 2 events have to occur in an order, one after the other. First thing is I am going to pick up a bag, and second thing is I am going to pick up a ball from the chosen bag. Got it? And now the probability is, now what they are asking is, what is the probability that you have picked up a green ball? Now in order to answer this, the probability of picking a green ball actually depends on what is the bag you are talking about. So try to understand this wording carefully. The probability of getting a green ball depends on the type of the bag you have chosen. Depends on, right? So what do I mean by that? Depends means they are not independent, they are dependent events. And whenever we have dependent events, when you are talking about intersection, remember that we have to apply conditional probability. In case if they are independent events, we can multiply them directly. So in this example is actually an example of dependent events and conditional probability, because the probability of getting a green ball depends on which bag you have chosen, right? Okay, to put it in words, or in numbers, let's see this. So probability of picking up bag A is equal to probability of picking up bag B is equal to probability of picking up bag C is equal to 1/3. Okay, and now what about probability of picking a green ball? That actually depends on which bag you are talking about. Probability of picking a green ball, given that you have picked up bag A, is going to be in this one, right? So you have already picked up bag A. Now what is the probability of picking up a green ball? So probability of picking up a green ball is nothing but, see this, 2 is green and total number of balls is 5. It is 2/5. And similarly, what is the probability of picking up a green ball given that bag B has been chosen? Now one green ball is there and total number of balls is 5. And what about probability of picking up a green ball given that bag C has been chosen? If bag C has been chosen, 3 green balls out of 5 balls. These are the probabilities, right? Okay, now what I want is, we want the probability of picking the green ball. P of G equal to how much? Here P of G is not directly given, but then we know that P of G is given A, P of G given B, and P of G given C. These probabilities we know it. Now how to analyze it? So this is called as total probability. These are called as individual probabilities, and now this is called as total probability. Now this total probability depends on all these individual probabilities in some combination. Now how to find it? Let's analyze this one. See this? So one other way of analyzing this is, let's try to find out the sample space for this experiment, for any experiment I told you that there will be sample space, right? And in this case the sample space is finite. Now what are the events that we are talking about? First thing is we'll pick up one of the bag and then we'll pick up one of the ball, isn't it? Therefore when I pick up the bag first, the bag could happen to be A, right? And then when I pick up the ball from A, it could be green, right? Or the bag could be A and the ball could be blue, what is it, red, okay? Try to understand this. Now I am talking about the sample space. What is the experiment we are conducting? We'll pick up a bag and then we'll pick up a ball. Therefore first the bag could be A, and in case if bag happened to be A, then the ball when we pick up, it could be either green or red. Therefore these two events are possible. These 2 points will be present in the sample space. Similarly, the bag could be B and the ball could be green, or bag could be B and the ball could be red. Similarly, bag could be C, ball could be green, bag could be C, ball could be red. These are all the events. Now what is that we want? We want the probability that the ball happens to be green, which means we want the probability which is equal to sum of these 3 probabilities. Now how do you analyze it? In order to analyze it, you can understand one thing. Look at the sample space. Now based on the bag, we can divide the sample space into 3 exclusive events, isn't it? Now based on the bag could be A, bag could be B, bag could be C. It is very important that you understand it. Just watch it carefully, because later even Bayes' theorem will depend on this total probability only. So try to understand it carefully. Now based on the event of choosing the bag, I could divide the sample space into three disjoint events, 3 mutual exclusive events. Got it? This is the event of choosing bag A, this entire first part, and the second part is event of choosing bag B, and the third part is event of choosing bag C. Now the required event is actually present in this one as well as in this one as well as in this one, right? Now try to understand this in the other way. What I am trying to say is, if we have a sample space, now we divide into 3 parts. Okay, let's call it event E1, event E2, event E3, and now the event that we actually need, let's call it event A, is present in all these parts, some part, okay? It is present like this. Let's say this is event A. Now I want to find out what could be the probability of event A, right? So try to understand this. E1, E2, E3 are 3 disjoint events, which means there is nothing in intersection between E1 and E2, there is nothing in intersection between E1 and E2 and E3, there is nothing in intersection between E1 and E3. Here also, see this, what are the events? One event is picking up bag A, one event is picking up bag B, one event is picking up bag C, and now there is no dependency between, there is no intersection between all these 3 parts, right? Now how can I write event A? See this, event A can be written as this part plus this part plus this part. In set theory we use union, isn't it? Now event A can be written as E1 intersection A, which means this part, right? Union E2 intersection A, which means this part. Union E3 intersection A, which means this part. Got it? Now what we want the probability of A. Now I am applying probability on both these sides. Probability of A. Now when E1, E2 and E3 are mutually exclusive, definitely E1 intersection A and E2 intersection A and E3 intersection A are also mutually exclusive, which means there will nothing be common in between this part and this part, and there will be nothing in common between this part and this part, nothing be common in between these 2 parts. Likewise, these 3 events are also going to be mutually exclusive. Now P of E1 intersection A union E2 intersection A union E3 intersection A. This is what is A, right? Then what does it mean? That implies P of A equal to, whenever you have three disjoint events or any disjoint event, whenever you are trying to take the union, it is nothing but the sum, right? So it is going to be P of E1 intersection A plus P of E2 intersection A plus P of E3 intersection A. Got it? Are you getting this one? Try to understand this. Now, how did I write this? It is nothing but P of A union B union C. We know that P of A union B union C is equal to P of A plus P of B plus P of C minus P of A intersection B minus P of B intersection C minus P of A intersection C. But then I am not going to write them because anyway those probabilities are zero because they are mutually disjoint, and we have to add even plus P of A intersection B intersection C. Even that part is also zero. That is why that original formula will now become this formula. I hope you are following this, right? Okay, now how to analyze this? So in order to evaluate this, it now depends on two things. One is whether E1 and A are independent or dependent, whether E2 and A are independent or dependent, whether E3 and A are independent or dependent. Now that actually depends on various factors, like what is the experiment we are talking about. In this case, E1 and A are dependent. What is E1 here? Probability of picking up the bag A. And what is A here? Probability of getting a green ball. Now these two are dependent events because probability of getting a green ball depends on whether we have picked up bag A or bag B or bag C. That is why in this particular case I can evaluate it this way, right? So let's keep it this way, and now here let's try to analyze this. P of A is probability of getting A, P of B is probability of getting B, P of C is probability of getting C. Now in terms of this one, probability of getting a green ball is equal to probability of getting bag A and a green ball from bag A plus probability of getting bag B and a green ball from bag B plus probability of getting bag C and a green ball from bag C. Now we know that getting a green ball is actually dependent on A. Which should happen first? A should happen first, right? See, in this one it is actually dependent events, and moreover the order is also important. What is the order we are talking about? We are talking about P of A happening first, right? So we'll pick up bag A and then we'll get a green ball given that we have picked up bag A, right? So how did I write this? This is from conditional probability. I hope you remember that. In conditional probability, when I was explaining it, P of A intersection B equal to P of A into P of B given A in case they are dependent. In case they are independent, P of A into P of G. Later I'll show you one independent example also, but for now just focus here. Next one, what about this? Probability of getting a bag B into probability of getting a green ball given that we have picked up bag B. Similarly, probability of getting a bag C and then probability of getting a green ball given that we have chosen bag C. And now we can just simply replace the numbers and we can get it. So what is it? 1 by 3 into, what is this one? P of G given A, it is 2 by 5 plus 1 by 3 into, what is P of probability of getting a green ball given B? It is 1 by 5 plus probability of C. Probability C is 1 by 3 into, what is probability of getting a green ball given C? 3 by 5. Got it? So this is called total probability. Got it? This one is called as total probability, right? In case if the events are dependent, right, then this one. Got it? So whatever we have written here, this formula is called as total probability. Now in this case A and G happen to be dependent. I'll give you one example where A and G will not be dependent. Okay, just watch it. Try to correlate these two. I think you understood this one, right? So what is the experiment? We are taking a bag, 3 bags, and then we are choosing one ball from one of the bags, right? And this is what we got. Now let's try to change it to a different experiment, and then I'll show you the difference here. Okay, let us say the experiment is about rolling 2 dice, and we know that sample space will contain 36 points, right? Because we can get any of 6 events on the first one and any of 6 numbers on the second one. Therefore, let us assume that this is the sample space. Now we are going to roll 2 dice. So the numbers on the 2 dice can be 1 1 or 1 2 or so on, 1 6, similarly 2 1, 2 2, so on, 2 6, similarly 3 1, 3 2, so on, 3 6, 4 1, 4 2, so on, 4 6, 5 1, 5 2, so on, 5 6, 6 1, 6 2, so on, 6 6, right? Now I want to find out the probability that the second dice will give me a number 2, right? Which means I am interested in this particular event, right? Now according to this total probability theorem, see, we can either solve it directly. You know how to solve it. What is the answer? There are 36 points and the probability of each point is 1 by 36, and 6 points are there, therefore 6 into 1 by 36, which is nothing but 1 by 6 is the answer. That is the probability of getting a 2 on the second dice. We know that, but then I just want you to explain this total probability using this example. In order to understand this total probability, always remember that we have to divide the sample space into mutually exclusive events, and then we have to get the event as if it is an event which is occurring across all these events, right? So in order to do that, we can do this question in some other way. See this, what is the way is, now let's talk about the dividing this sample space based on what happens on the first dice. Depending on what happens on the first dice, I could divide this sample space into 6 parts. Now on the first die, it can be 1, or on the first die it can be 2, or on the first die it can be 3 or 4 or 5 or 6, right? So depending on what happens on the first dice, I am able to divide this sample space into 6 parts. Now the required event is actually a event which is spread across all those 6 events, right? So again we can use the same formula, right? So what is it? E1, E2, E3, so on, E6 are there, and then we have an event A which is spread across all of them. Then how can I write that event A? Event A equal to event E1 intersection A union E2 intersection A, so on, union E6 intersection A. Then what do I get? P of A equal to E1, this entire thing, union E3 intersection A, so on, E6 intersection A. Now we know that since they are disjoint events, I can write it as if it is P of A equal to E1 intersection A plus E2 intersection A, so on, E6 intersection A, right? So I'm just writing that. So probability of getting a 2 on the second dice, let me call it, that is event A, is equal to probability of getting E1, which means first one, 1 on first dice intersection 2 on second dice, plus 1 on first dice intersection, 2 on first die intersection 2 on second die, plus 3 on first die intersection 2 on second die, plus 4 on first die intersection 2 on second die. Plus 5 on first die intersection 2 on second die, 6 on first die intersection 2 on second die. Got it? This is called as, again, total probability, right? So how did I derive this? Simple. I have divided the sample space into mutually exclusive events, and then I have spread the required event across all these events, and then the total probability of getting that event is equal to union of all these parts. That is called as total probability theorem. Now this is the formula we get. Now how did I get this formula? Because I divided the sample space into 6 mutually exclusive parts. That is why I'm getting 6 parts here. Got it? And now in this example, in this particular example, the probabilities are independent, in the sense whatever happens on first die is independent of whatever happens on the second die. So given the knowledge that 1 has occurred in the first die doesn't change the probability of getting a 2 on the second die, isn't it? Given that 2 has occurred on the first die, it doesn't change anything on the second die. Therefore all these are independent events, which means getting probability of getting 1 on first die is independent of probability of getting 2 on second die. So this is an case in which independent events are used. Therefore we can directly write it as P of E1 into P of A plus P of E2 into P of A plus P of E3 into P of A plus P of E4 into P of A plus P of E5 into P of A plus P of E6 into P of A. This is not the best way to solve this question, but then I just wanted to explain what is total probability by taking 2 examples. First one is the example in which dependent events are used, and here the example in which independent events are used. Therefore total probability can be applied for both the cases. That is what I mean to say. And now what is it? Probability of getting 1 on first die is nothing but 1 by 6. What is the probability of getting 2 on second die? 1 by 6 plus 1 by 6 into 1 by 6 plus 1 by 6 into 1 by 6 plus 1 by 6 into 1 by 6, right? So on. So you are going to get 1 by 6. Okay, you can solve it. Now you have to understand one thing here. So whenever we can divide the sample space into mutually exclusive events and we can spread an event across all these events, then we are going to call this total probability theorem in order to find out this total probability of the event, right? And second thing is, this total probability can then be evaluated, or we can find out the total probability of an event either by using conditional probability like this or by using independent events like this. It depends on what type of events you are talking about, right? But then you are not going to see such kind of questions or such kind of examples anywhere, right? Therefore people generally think that total probability is going to be useful or applicable only when the events are dependent. But then it is false. It can be used even when the probability it is independent, but since we have other ways of solving it, we generally don't use it. That's the case. Got it? So from now on we'll be discussing about only the examples in which we are going to use total probability and also the events are dependent, because these are the cases which are interesting, and later I can even use those examples to explain you the Bayes theorem. In case of independent events, applying this total probability is not very meaningful. Just now we have seen it, right? In case of independent events you can directly compute the probabilities without using this, but in case of dependent events it becomes very interesting, and even later in Bayes theorem it will be even more interesting. Okay, so try to remember this. We can apply total probability theorem whenever we can divide the sample space into mutually exclusive events or disjoint events, and then we can spread an event across all these events, and I don't care whether the events are dependent or independent, I can still use the total probability theorem. But most of the examples or all the examples which I am going to take up from now on are going to be exactly on this independent events. Like this, conditional probability is going to be used. They are not going to be on independent events. If you want more examples, you can create your own examples, but they are not going to be asked in GATE or anywhere. They are not very interesting, but these questions will be interesting. Okay, fine. Let's see one more example on total probability. Assume that we have 2 bags, bag A and bag B, and say there are 2 green balls here and 3 red balls, and here there are 3 red balls and 2 green balls. Okay, and now the experiment is like this. We'll first draw a ball from A bag A and we add it into bag B. That ball can be either green or that can be red. And next we draw one ball from blue. Now we want to see what is the probability that the ball which we draw is red. Okay, so try to understand the question again. We have two bags. We'll draw a ball from A and we'll add it to B, and after adding it we'll draw one ball from B. Now what is the probability that the ball is red? That is what we wanted. Now again, this you can do it using total probability. So in exam you can directly do it directly by writing the formula and then you can do it, but here I'll go slowly. All these examples, even though you understood it, I'll go bit slow and explain you everything, but in exam you can do it fast, but here I'll go slowly. Okay, now what is the sample space? Now this experiment actually contains two things. First thing is drawing a ball from here and then drawing a ball from there. So now when you draw a ball from bag A, it can be either green ball or red ball. Therefore now initially we might get red ball initially from the bag A, and then we might get a red ball from bag B, which means first ball is red and second ball is red. That case is perfectly possible. Similarly, first ball can be red and second ball can be green, right? Or first ball can be green and second ball can be red, or first ball can be green and second ball can be green. These are the four possibilities we have. Now what is that we wanted? We want the probability or total probability that second ball is actually red. This is what we wanted. Now again, in order to solve it, based on what happens to the first ball that is drawn, we can divide the entire sample space into two parts, right? So this part and this part, both are mutually exclusive, and we can apply the formula like this. So what is it? Now we have two events, E1 and E2, and the event that we require is actually spread across these two events. This is E1, let's say this is E2, and let's say this is A. Now earlier with the total probability, we have seen that probability of A happening is equal to probability of E1 intersection A plus probability of E2 intersection A. Now how did I write it? Because they are mutually exclusive events. Got it? And then what about this probability? That depends on whether E1 and A are dependent or independent. In case if they are dependent, we are going to use conditional probability. In this case, can you just tell me, are they dependent or independent? Which means the probability of getting a red ball here depends on what is the event that happened here. In case if the event that happened here is, if we get a green ball, then the probability will be something. In case if it is a red ball, then the probability will be something. Therefore these two events are dependent, which means the probability of getting a red ball here depends on what happened, or which ball we have drawn from bag A. Therefore they are actually dependent events, and so when you are doing this, we should use the conditional probability, right? Which means we should use the formula like this: probability of E1 into probability of A given E1 plus probability of E2 into probability of A given E2. Got it? So this is how I am going to get the total probability here, right? And now coming to this example, let's do this. Now probability of getting a red ball second time is equal to probability of getting a green ball first time into probability of getting a red ball second time, given that we got a green ball first time. Now why are they dependent? Because once we pick green ball from here and add it from there, the probability of getting a red ball is going to change, and it is going to depend on green ball first, right? Plus probability of getting a red ball first into probability of getting a red ball second time, given that first time we have drawn the red ball. Now let's see this. What about probability of G1? Probability of getting green ball first, that depends on only this one, right? So which is nothing but 2 green balls are there, totally 5 balls are there, therefore 2 by 5. That is the probability of getting a green ball. What is the probability of getting a red ball? Given that green ball has drawn, now once we have drawn green ball here, then the green ball will be added here. Therefore, there will be 3 green balls and 3 red balls. So totally 6 balls will be there. Out of which, what is the probability of getting a red ball? 3 by 6. Are you getting this? Totally 6 balls will be there because one more ball is added and that new ball is green ball. Therefore, number of red balls doesn't change. That is why 3 divided by total number of balls now will be 6. Got it? Plus, what is the probability of getting a red ball? Probability of getting a red ball from A is equal to 3 by 5 multiplied with, what is the probability of getting a red ball in the second try, given that we have got a red ball from the first try. Now since we got a red ball from here, when we add it, then we are going to get 4 red balls and 2 green balls, which means totally 6 balls are there, out of which 4 are red. Therefore it is going to be 4 by 6. This is the total probability of getting a red ball. Got it? So in exam you can directly write it, and then you can directly write this one and easily solve it. But here I wanted to go slow, explaining you everything. That is why I am going bit slowly. Okay, so the intention of explaining this is just to give you a much clearer idea about how the concept is working. So anyway, this question can be answered using total probability this way. Okay, let's see one more question on total probability. So assume that we have a bag, and in the bag there are 3 balls. Assume that it is known that one ball in the bag is definitely red, and we don't know the colors of the 2 other balls. They can be either red or they can be non-red. Now if I pick a ball from this bag, what is the probability that it is going to be red ball? It need not be this red ball. In case if any one of these happens to be red ball, it can even be that. Okay, this question is a bit difficult to understand. I'll try to focus here. The question is like this: given that there is a bag and then 3 balls are there, one of the ball is known to be red, but the status of other 2 balls or the colors of other 2 balls are unknown. They can be either red or non-red. Then what is the probability that if you draw a ball from this bag, it turns out to be a red ball, right? And it need not be this red ball, it can be any of the red balls in case if they were also red balls. Then how are you going to do it? So this actually depends on various assumptions, which means, so first assumption can be these 2 balls may be non-red, or one ball is definitely known to be red and other ball might be red and other one may be non-red, or the other case is all the 3 balls may be red. Got it? So since it is unknown, we have to take into consideration all the possible chances. Getting this? Now they have given that one ball is red, 2 balls are unknown. Now what can be those 2 balls? Either both of them can be non-red, or one of them can be non-red, or all of them can be red. Now all these 3 are possible. Got it? Therefore our sample space can now be divided into 3 mutually exclusive events. One event is back can be this one, or back can be this one, or back can be this one. And now our event of getting a red ball is actually across, right? Spread across these 3 events. Now you can use the conditional probability, right? Okay, total probability first of all, and then after using total probability you might have to use conditional probability, because the probability of getting a red ball actually depends on what is right in all these 3, which one is right. Are you getting this? See, now the sample space is actually divided into 3 mutually exclusive events. Back can be of this type or this type or this type, right? And then If the bag is of first type, this is the probability with which we can get a red ball. If the bag is of second type, this is the probability with which we get a red ball. If the bag is of third type, this is the probability with which we get a red ball, which means the probability of getting a red ball depends on what type of bag it is. Therefore, they are actually dependent events, and so we have to get into picture conditional probability again, right? So let us say this is event E1, this is event E2, this is event E3, and this is event A, right? Then what does the total probability say? Total probability says that P of A is equal to P of E1 intersection A plus P of E2 intersection A plus P of E3 intersection A. Got it? And now what about P of E1 intersection A? Now you can use the conditional probability. The reason is the probability of getting a red ball actually depends on what type of bag it is. Let E1 denote that the bag is of this type, E2 denotes that the bag is of this type, E3 denotes that the bag is of this type. And since there are three possibilities and every possibility is equally likely, P of E1 can be 1 by 3, P of E2 can be 1 by 3, and P of E3 can be 1 by 3. And then P of A given E1, that depends on number of red balls in it, right? Just check this. How can I write it? P of E1, which means probability that the bag happens to be of this type, into probability of A given E1, which means if the bag happens to be of this type, what is the probability of getting a red ball from that bag, plus P of E2, which means probability that the bag happens to be this type, and P of A given E2, which means probability of getting a red ball given that the bag happens to be of this type, plus P of E3 into P of A given E3. We have to add these three. Now what is the probability that the bag can be of this type? All these three are equally likely because we don't know which one, therefore we assign the same probabilities. 1 by 3 into P of A given E1, which means if the bag would have been of this type, which means 2 are non-red balls and 1 is red ball, then what is the probability of getting the red ball? 1 by 3, right? Plus P of E2. What is the probability that the bag is of this type? It is 1 by 3 into P of A given E2, right? In case if 2 balls are red and 1 is not red, then what is the probability of getting a red ball? 2 by 3, isn't it? 2 balls are red, that is by 2 by 3. Now what about this? 1 by 3 into all the 3 balls are red, then what is the probability of getting red ball? It is 100%. 3 by 3 is 1. Got it? So this is how we can answer it. Again we have used the total probability and also we have used the conditional probability, both of them. Got it? Why conditional probability? Because the probability of A depends on probability of E, or happening of these events. That is why. Okay. Now assume that we have a bag, and again one more question on total probability. Assume that we have a bag, and in this bag we are having 1, 2, 3, 4 fair coins. All these 4 coins are fair. What do you mean by fair? Probability of getting a head or the probability of getting a tail when I flip a fair coin is going to be 1 by 2. That is what is called fair coin. And 1, 2, 3 unfair coins. In this unfair coin, let us say probability of getting a head is equal to 1 by 3 and probability of getting a tail is equal to 2 by 3. You can understand why it is called unfair coin, because probability of getting a head is lesser compared to probability of getting a tail. Got it? So that is why they are unfair coins. Now in all these 3 unfair coins, this is the probability of getting a head and tail, and in all these fair coins, the probability of getting head and tail are same, which means probability of getting a head equal to 1 by 2 and probability of getting a tail equal to 1 by 2. This is given. Now in this situation, what we do is we take a coin, we pull it out and then we flip it. Then what is the probability that we get a head? Got it? Are you getting this? In this we are going to perform two experiments, or in this experiment we are going to do two things. First we are going to choose a coin at random and we are going to flip it, and then we are going to we want to find whether it is a head or tail, or what we want is what is the probability of head. Got it? Again, a total probability question. So whether to understand, in order to understand such question, you have to understand that probability of getting a head will actually depend on what is the event that has happened first. Did you choose fair coin or did you choose unfair coin? In case if both are possible, then you have to find out what is the probability of getting a head given that you have chosen fair coin, plus what is the probability of getting a head given that you have chosen a unfair coin. That is how you should solve it, right? If you can understand it, it is okay. Otherwise, let's see the sample space. See, I am going slowly, but in exam you can do it fast. Don't think that these questions are difficult. They are very easy given that you understand these concepts. That is why I am going slowly. Now there are two events. First thing is you have to pick a coin randomly. Now when you pick a coin, it can be either fair or unfair, isn't it? Now it can be fair coin, and when you flip it you can get a head, or it can be fair coin when you pick the coin and when you flip it you might get a tail. Similarly, when you take the coin, it can be unfair coin, but when you flip it, it can be a head. Similarly, when you take the coin, it can be unfair coin when you initially choose it, and when you flip it you might get a tail. Now what is that they want is what is the probability of getting a head, which means these two events will be included. That is what we wanted. Now we can go into total probability theorem and we can try to apply it. How? Depending on what happens in the, when we pick the coin, we can divide the sample space into two parts. When you pick the coin, the sample space, the coin could be either fair or unfair. Are you getting this? When you have flipped the coin could be fair, these two cases, or it could be unfair, these two cases. Therefore, now the sample space is divided into two mutually exclusive events, and our required event is actually spread across these two events. Alright, so now you can apply so this is the fair and this is unfair, and this is probability of getting a head. Now you can apply total probability theorem. What is it? Probability of getting a head is equal to probability of getting a fair coin in the beginning and probability of getting a head when I flip it, plus probability of getting an unfair coin in the beginning and probability of getting a head when I flip it. Now how can I expand it? Are they dependent or independent? See this, the probability of getting a head actually depends on what type of coin it is. Therefore, the initial event actually determines the probability of the next event, so they are definitely dependent. So when you are trying to expand this intersection, you have to apply the conditional probability formula, that is equal to probability of getting a fair coin, right, into probability of getting a head given that the coin is fair, plus probability of getting an unfair coin into probability of getting a head given that the coin is unfair. Now what are the probabilities? What is the probability of getting a fair coin? Out of these 7 coins total, 4 coins are fair. Therefore 4 by 7 is the total probability of getting a fair coin. Now what is the probability of getting a head given that it is a fair coin? We know that since it is a fair coin, probability of getting a head is equal to probability of getting a tail is equal to 1 by 2. Got it? Plus probability of getting a unfair coin. In this, out of the 7 coins, 3 are unfair, which means 3 by 7 is the probability of getting an unfair coin, into probability of getting a head given that you have chosen an unfair coin. Now since you have chosen an unfair coin, probability of getting a head is equal to 1 by 3. Alright, so this is the probability of getting a head. Okay, now let's say I want to extend this question a bit. What is the probability of getting 2 heads? Which means instead of choosing one coin, let me say I have chosen 2 coins, then what is the probability of getting 2 heads? So understand the question. Instead of choosing 1 coin from this, let us say I want to pick 2 coins, right? Once I pick 2 coins and I want to flip these 2 coins, what is the probability that I get both the coins as heads, right? So how can I do that? Just see, probability of getting 2 heads. Okay, let me do it in the next video. Fine. Now let's talk about 2 coins. Now when I am talking about 2 coins, sample space is actually going to change. In the earlier case, sample space was different. Now the sample space is different. Now when you choose 2 coins, those 2 coins can be either both can be fair or both can be unfair, or one can be fair and other can be unfair, isn't it? When I choose 2 coins simultaneously, either both can be fair or both can be unfair, or one can be fair and other can be unfair. These 4 cases are possible, right? Now these 2 cases I can combine, because I am not interested in knowing exactly which one is fair and which one is unfair. I just want to know that one of them is fair and one of them is unfair. Therefore the position here doesn't really matter in this question. So now either this one can happen or this one can happen and this one can happen. So by using this conditional, total, if I have to apply the total probability theorem, then you are supposed to divide the sample space into disjoint events. Now one event can be getting 2 fair coins, other event can be getting 2 unfair coins, other event can be getting 1 fair and 1 unfair coin, right? And now getting 2 heads is actually an event which is spread across all these 3 events. Got it? Let us say getting heads is given by HH. Now what I want to know is what is the probability of getting 2 heads. Now how can you write it? It is equal to probability of getting 2 fair coins and getting 2 heads when I flip those 2 fair coins, right? Plus probability of getting 2 unfair coins and getting 2 heads when I flip them, plus probability of getting 1 fair and 1 unfair coin and getting 2 heads when I flip it. Got it? See, exactly if you want to know how many events are there in the sample space, then you will get 4 events here, 4 events here, 4 events here. Why? If I take 2 fair coins and when I flip them, one is I can get head head and other is I can get head tail, other is I can get tail head and other is I can get tail tail. Got it? So instead of doing this cumbersome exercise, I was just trying to cut it short. I hope you are understanding it. If you don't understand it, just follow our regular model, where initially I was just writing all the events possible and then dividing the sample space and then taking this. You can go with that model as well. But since we are done with these many examples, I just wanted to do it fast. That is why I taken this. Now see this. Now probability of getting 2 heads actually depends on what type of coins they are. Therefore just observe the terminology. Probability of getting 2 heads actually depends on what kind of coins they were, which means they are dependent events, not independent events. Got it? So it is going to be probability of getting 2 fair coins into probability of getting 2 heads given that both the coins are fair, right? Plus probability of getting 2 unfair coins into probability of getting 2 heads given that both the coins are unfair, plus probability of getting 1 fair coin and 1 unfair coin into probability of getting 2 heads given that both the coins are one coin is fair and other coin is unfair, right? Now understand this one. What is the probability of getting 2 fair coins? Now there are 4 fair coins out of 7 coins. Therefore probability of getting 2 fair coins is equal to 4C2 divided by 7C2. Right? This is nothing but in permutations combinations we have seen this. And then what is the probability of getting 2 heads given that both the coins are fair? From one fair coin we get 1 by 2 and from other fair coin we get 1 by 2. I hope you understood how I wrote it, because these two are independent events. Probability of getting head is equal to probability of getting head and into probability of getting head, because when I toss 2 coins they are actually independent events. That is why I am multiplying it. Okay, plus probability of getting 2 unfair coins. Totally there are 3 unfair coins out of 7 unfair coins. It is going to be 3C2 divided by 7C2 into probability of getting heads from the unfair coins. Now check that. In unfair coin, probability of getting head is given as 1 by 3. Since both are unfair, it is going to be 1 by 3 into 1 by 3. Plus, what is the probability of getting 1 fair and 1 unfair coin? Now, 4 coins are fair and 3 coins are unfair. Therefore, 4C1 into 7, how much is this? 3C1 divided by 7C2. This is the probability of getting 1 fair and other unfair coin. See, now to understand this, you might have to watch permutations and combinations first. So you please watch that topic and then come back to this. You will understand this one. Why am I writing 7C2 and this? Okay. And what about getting 2 heads given that 1 coin is fair and other coin is unfair? From fair coin you will get 1 by 2 and from unfair coin you will get 1 by 3. Therefore, this is the total probability. Got it? This is the total probability of getting 2 heads. You can even extend, if you want to extend it, you can even extend it to, let's say you are drawing 3 coins, and then what is the probability of getting 3 heads when you flip them, right? But anyway, here my main intention is to explain you what is the concept of total probability. Okay. See this question. In answering a question on multiple choice test, so which means the question is having multiple choice, just like GATE exam, option A, option B, option C, option D, and one of them is the answer. In answering such a question, a student either knows the answer or guesses. So let us assume that there are no negative marks. If there are no negative marks, obviously you are going to guess all the questions, right? You will be answering the 60 marks which you know, and the remaining questions you can obviously guess and you can win. But then assume that there are, in our GATE there are negative marks, but here assume that there are no negative marks. Okay. Now, either he knows the answer or he guesses. Let P be the probability that she knows the answer, and 1 minus P be the probability that she guesses the answer. Assume that a student who guesses at the answer will be correct with probability 1 by m, where m is the number of multiple choices. Which means if you have 4 options, if you don't know the answer and if you are picking one at the random, then the probability that your answer is right will be 1 by 4. Similarly, here they are saying that if there are m options, right, and assume that there are m options. If there are m options, then it is going to be 1 by m. What is the probability that she answers correctly? Again, we have to apply the total probability. So why say this? Because now our sample space will contain actually 4 units, 4 events, but then we can actually, okay, see this. Either she knows the answer or she guesses, right? She knows the answer or she guesses. In case if she knows the answer will always be correct. She will always answer the question correctly. In case if she guesses the answer, she may be correct or she may be wrong. Correct? Therefore, based on this, you can divide it into 2 parts. You can divide the sample space into 2 parts based on this factor, whether she knows or whether she guesses. See, Why am I not writing the other one where she knows the answer and she writes it wrong? Because she is not crazy, right? If she knows the answer, why will she answer it wrong, isn't it? So this option is not there. So if she knows the answer will be right. If she guesses the answer, it can be correct or it can be wrong. Now they are asking this probability, right? What is the probability that she answers it correctly? Now how can you answer it? See, this probability that she will answer it correctly is equal to probability that she knows the answer and answers it correctly plus probability that she guesses the answer and answers it correctly. Now what is the probability? What about this one? It is probability that she knows the answer into probability that she answers it correctly given that she knows it, plus probability that she guesses the answer into probability that she answers it correctly given that she has guessed at the answer. Got it? And now it is already given that the probability that she knows the answer is 1 by p and the probability that she guesses the answer is 1 minus 1 by p. And we have to find out these two. These two are also given actually. Now what is the probability that she will answer correctly given that she knows 100%, right? So probability is 1. Probability of this event answering it correctly given that she knows is 1, because it is 100% possible that if she knows the answer, she will definitely answer it correctly. And what about the probability that she guesses the answer and it is correct? If you are having m multiple options, m options for the question, then it is going to be 1 by m, right? See this. Now probability that she knows the answer is already given, which is p. P is the probability that she knows the answer, right? Into probability that she answers correctly given that she knows is 1, plus probability that she guesses the answer is 1 minus p into probability that she answers it correctly given that she has guessed is 1 by m, right? Where 1 by, say this, the probability, assume that the student who guesses at the answer will be right with probability 1 by m, where m is the number of multiple choice alternatives, right? Therefore probability that she answers it correctly is equal to this one. Got it? So how did I solve it? Again using the total probability theorem. Just remember this question. I'm not going to write the entire question again. Later I'll just explain the question and I'll use it in the Bayes theorem, in solving the Bayes theorem questions. So we just note down the question and remember it. Later I'll just refer to this question again. Okay. Now let's see a problem. Let us say there's a person A, and it is some tournament. Let's assume that it is a wrestling tournament, and he has reached the finals, and he is waiting for the other opponent. And the semi-finals, one of the semi-finals is still going on. There is a person B and a person C competing in this semi-finals. The probability that B will win the semi-finals, assume that it is 1 by 3, and the probability that C will win the semi-finals, assume that it is 2 by 3. Okay. In case if A fights with B, the probability that A will win, in case if A fights with B, the probability that A will win is 2 by 3. In case if A fights with C, the probability that A will win is, let us say, 1 by 4. Okay, try to understand this question. So it is like this: A is already in the finals and he is waiting for his opponent. Now either B or C, both who are actually competing in the semi-finals, either one of them is going to fight with A. The probability that B will win this fight is equal to 1 by 3, and the probability that C will win the fight is equal to 2 by 3. In case if B won the fight and if B fights with A, then A will win over B with probability 2 by 3, and the same way A will win over C with probability 1 by 4. Now we have to say what is the probability that A wins the game or A wins the trophy, which means even in the final match also A has to win. What is the probability that he will win? So now if you see this, you can think of it like this. It is, you can find out all the entire sample space, and maybe if possible you can see if you can put it in terms of the total probability theorem, right? So let's say this. So first thing is, what is the probability or what are the events that are going to take place here? So this entire trophy thing, it is going to have two matches. First match is between B and C, and the second match will be between A and the winner of this, right? Therefore in the first match B can win. In case if B won the first match, in the second match A might win, or in the first match B might win and in the second match also B might win, or in the first match C might win and in the second match A might win. What is the second match? Are you getting this? In the first match if B wins, the second match will be between A and B. That is why second match either A will win or B will win. Getting this? Similarly, in the first match in the semi-finals C might win, and in the second match in the finals, who will be fighting in the finals? C and A. Either A will win or C will win. Now what they wanted is, what is the probability that A will win the trophy, right? Which means in the second match, which means the final, what is the probability that A will win? Now again, if you can see this, based on who wins the semi-finals, you can divide the sample space into two parts. Therefore you can go with this total probability theorem. So probability that A will win is now equal to probability that B will win the semi-finals and A will win the final, plus probability that C will win the semi-final and A will win the final. Now what about them? Are they independent events or dependent events? Now probability that A will win is actually independent of whether B wins or not, isn't it? Probability that when A and B fights, the probability that A will win is equal to 2 by 3. When A and C fights, the probability that A will win is 1 by 4. Now these probabilities are not depending on these probabilities, which means it is not that this B or C winning is going to change these probabilities. Those probabilities are not going to change given that B wins or C wins. That is why probability that B will win into probability that A will win given B has 1. So why am I writing like this? It doesn't mean that the probability is changing. I am writing like this because this will indicate that A is fighting against B. Okay, so that is why I am writing it. It doesn't mean that these two probabilities are depending. Okay, plus probability that C will win into probability that A will win given C has 1. It doesn't mean that A and B are actually dependent in the other sense, which means the probability of A will not change. But then why am I writing this? Because there is a difference in A winning. Got it? So what is it? Probability of B winning is equal to 1 by 3 into probability of A winning given that B has 1. So this means that A and B are fighting. That is why this case is different. So which means 2 by 3 plus probability that C has 1, which is equal to how much? 2 by 3 into probability that A will win given that C has 1, which means A will be fighting with C. In case if A fights with C, I told you that he wins is with the probability 1 by 4. So this is the total probability that A will win. Got it? Probability that A will win is this. Again we have used the total probability theorem here. Okay. Now let's see Bayes' theorem with an example. So I'll take the example and I'll try to explain you this entire concept instead of giving you the formula. Let's take the example first. So I'll be using the same examples which I have used for total probability. We will revisit all the examples. Let us say there are three boxes, box A, box B, box C, and in box A assume that there are 2 red balls and 3 green balls, 1 red ball and 4 green balls, 3 red balls and 2 green balls. Okay, now there are various questions that can be asked on this example. One question that can be asked is, what is the probability of getting A? So again, the experiment is like this. We'll first choose a box randomly and then we'll pick a ball from that box, whatever box is chosen. Now one question we have solved is, what is the total probability of getting a red ball, right? So that is, what is the P of R, what is the total probability of getting a red ball. And now other question they can be asked is, what is the probability of getting a red ball given that A has been picked, which is nothing but 2 by 5, isn't it? And other question, okay, let me write it down better. So the reason why I'm emphasizing on this is, all the questions will exactly look like the same, but then the answers will be different, so you have to solve them differently. Now one question is, question number A is, what is the probability of getting a red ball given that A is chosen, right? So now in this question, not to answer it, you should be very careful while reading the question, and you should give importance to some words here. So here the important word is given that. So whenever given that is given, it means that they are talking about the conditional probability. So they are exactly talking about this probability of getting a red ball given that A has been chosen. So which is nothing but, what is the probability of getting a red ball from this box? So which we know is 2 by 5. This is what we have discussed in conditional probability, right? And the other kind of question they will ask is, just focus on the terminology. What is the probability of getting a red ball from bag A? These two questions look exactly similar right now, but then they are different. What is the probability of getting a red ball from bag A? Before this question, they will even give you the entire experiment. We are conducting a random experiment in which we will choose a bag and then pick a ball. Now what is the probability of getting a red ball from bag A? Which means they are actually talking about this event, probability of choosing the bag A and probability of getting a red ball from bag A, which is nothing but probability of choosing bag A into probability of choosing red ball given that bag A has been chosen. You might think that both are actually exactly sounding the same, but both are different. What is the probability of getting a red ball from bag A means bag A should be chosen first and then the red ball. But here if it is already given that already A has been chosen, then you have to continue with the remaining part. If already A has been chosen, now this one will become 1. Already A has been chosen, that is why you will get this. Got it? And now the other question is, what is the probability of getting a red ball? So before asking all these three questions, there will be the statement saying that we are conducting a random experiment where we'll choose a box and then a ball from it, right? So what is the probability of getting a red ball means they are asking about P of R, probability of getting a red ball, which is nothing but the total probability theorem, isn't it? Here there we are going to use total probability theorem. Got it? So now what does it mean? Now we know that total probability theorem P of R is probability of choosing bag A and then red ball from it plus probability of choosing bag B and red ball from it plus probability of choosing bag C and red ball from it. Got it? Since they are all mutually exclusive events, I am just adding them and I am not considering the intersection of these events because they are all mutually exclusive. A, B and C are mutually exclusive and therefore A intersection B, B intersection A intersection R, B intersection R and C intersection R also mutually exclusive. Got it? Okay, now these are some of the questions that we can answer by whatever concepts we have learnt till now. Now let's answer a different question, very important question. This will combine all the concepts together. What is the conditional probability that bag A is chosen given that red ball is drawn? So this is very important question. Now what are all the things we know about this question? What are all the factors we know is, one is we know about, let me write here, what are all the factors we know, what are all the elements? We know that P of A is equal to P of B is equal to P of C. What is this? Probability of choosing a bag. This is equal to 1 by 3. And we know that P of R given A, which means probability of choosing red ball given that bag A has been chosen. We know this number. And then P of R given B, probability of choosing a red ball given that bag B has been chosen. P of R given C, probability of choosing a red ball given that bag C has been chosen. So we know all these six things, but then we don't know exactly what this question is asking is, what is the conditional probability that bag A is chosen given that red ball is drawn, which means they are asking about P of A given R. Got it? This is called reverse probability. Now what exactly they are asking is, an event has occurred, now we are supposed to find out the cause or the source, right? So we know that red ball has been drawn. Now what do you think about the source, or what is the chance that the source has been bag A, right? So that is what they are asking. It is really interesting. See now in order for the red ball to be chosen, there are actually three ways. Either red ball could be chosen from bag A, which means source could be bag A, or source could be bag B, or source could be bag C, isn't it? Now when there are three sources, now what is the probability that it would have been source A? That is what they are asking. Therefore P of probability that A being the source given that R is already known, or already has happened, is total number of sources, right? Which means like this, P of A intersection R, P of B intersection R plus P of C intersection R, P of A intersection R. Try to understand this one. Now they are asking, see, for the event R to occur, there are three sources, A, B and C, right? And now out of these three sources, what is the probability that the source would have been A? Now you take the source A and you divide with the total number of sources. Got it? Now I'll tell you why this is right. See this one. Now P of A given R is equal to, okay, let's expand it out. So we know that A and R are dependent, right? So what we know is P of A intersection R can be written as P of A into P of R given A divided by P of A into P of R given A plus P of B into P of R given B plus P of C into P of R given C. Now this entire formula, this is called as Bayes formula, right? And this is given by the scientist Bayes, mathematician Bayes, and so that is named after him, right? So Bayes formula says this. So we are going to use Bayes formula to find out this reverse probability. Why is it reverse probabilities? Because we know these probabilities or given A, or given A, or given B, or given C, and now we are trying to find out the reverse of it, which means A given R. That is why it is called as reverse probability. Got it? So why is it right? See this. If you watch this entire denominator, if you look at this entire denominator, this one. See, in case of dependent events, I am doing like this. In case of independent events, it is going to change, right? In case of independent events, you are going to replace P of A into P of R, P of A into P of R, P of B into P of R, P of C into P of R. We are going to write like this. Now, this entire the sum of these three probabilities, these three terms, is actually probability of getting a red ball, right? Isn't it? So this is the total probability of P of R. So which means P of A given R is equal to P of A into P of R given A divided by P of R. Now you just multiply them, both of them, I mean both the sides with P of R, then what do I get? It is equal to P of R into P of A given R is equal to P of A into P of R given A. Now we know that left hand side is equal to P of R intersection A, as well as right hand side is also equal to P of R intersection A. So that is why this formula is valid. This is the proof, isn't it? Check this. This is nothing but P of R intersection A. This is also nothing but P of A intersection R. Both are one and the same, right? Now let's see one other way of deriving the same fact. Let us say, how did we get this reverse probability? See, initially we know that we have divided this sample space into three events, isn't it? Initially we divided this sample space into three events. One is event A, which means picking up bag B, bag C, and then bag A, right? And then our required event of getting a red ball is actually spread across these three events. This is R, right? And whenever they said that, when they have declared that the event R has already happened, which means the red ball has already been drawn, then according to the conditional probability in this sample space, we have to change the probabilities, which means to all the elements which are present here in this region, we have to give the full probability, and to all the elements which are outside this, we have to make the probability 0, which means in effect the new sample space is actually present only in this region. The new sample space is this. See, old sample space, in case if they didn't talk anything about R, or if they didn't give that R has already happened, then the old sample space was this entire rectangular box. Now given that event R has happened, our new sample space has now changed, and our new sample space is going to be this one. I told you about conditional probability. So one way of evaluating conditional probability is change the probabilities. So whenever an event has occurred, or they said that some event has occurred, we have to reassign the probabilities for all the points. Now in this case, since they said that R has occurred, it means that nothing outside R is going to happen, right? Which means probabilities are all going to be zeros. Therefore our new sample space is going to be this, right? This is our new sample space, and in our new sample space we have three parts: first part, second part, and third part. Now they are asking what is the probability that this is the case, which means given that R has occurred, what is the probability that this would have been from bag A? Then how can you find out? You have to divide this part divided by total part. That is the total probability, right? Isn't it? So you have to take this part divided by total probability. This part is nothing but P of R intersection A divided by P of R intersection A plus P of R intersection B plus P of R intersection C. And we know that since they are dependent events, P of A intersection R is expanded like this, and P of A intersection B, A intersection R, B intersection R, and C intersection R are replaced like that. Got it? So likewise, you can know the causes of all the outcomes. So this Bayes theorem is mainly useful in finding out the source or the cause of an event. Similarly, they can even ask this question, that what is the conditional probability that bag B is chosen given that R has happened. So what is the main thing that you should see here? What are the main types of words that you have to catch in order to answer this question is, they'll give you this word, what is the conditional probability, right? And also they will give that given that. Then you should identify that it is a problem related to conditional probability. And then you have to find out whether it is direct conditional probability or reverse probability, which means are they asking the cause or they asking the event. Got it? Sometimes they will say what is the conditional probability that ball R is chosen given that bag A is chosen, something like that, which means it is probability of R given A. And sometimes they will not give you this word conditional, they will just ask what is the probability that bag A is chosen given that. Now again, given that is the keyword. Using that word given that, you can find out. Or other way of asking the question is, they will say that it is known that red ball has come out, then what is the probability that bag A is chosen? Again, whenever they said that it is known that means it is given that. So whenever the word is known that or given that or conditional probability, you should guess that the question has to be solved this way. Okay, so in case if the question is about what is the probability that bag B is chosen given that red ball has been drawn, then how can you solve it? It is nothing but probability of this one, B given R. This is what they are talking about. So it is nothing but probability of B intersection R, which is nothing but probability of B, right? So in order to understand this concept better, we'll take all the questions in which we solved about the total probability theorem, and we'll solve them again for the Bayes theorem. Okay, fine. Let's see this question. We have already seen this question in total probability. Again, we shall see it here. Let us assume that we are having a bag, two bags. Let's say this is bag A and bag B, and bag A is containing 2 red balls and 3 green balls, and bag B is containing 3 red balls and 2 green balls. Now we are conducting an experiment in which we first draw a ball from bag A and we add it to bag B, and then we draw a ball from bag B. Earlier we have seen what is the total probability that the ball that we draw from the second bag happens to be a red ball. That is what we have already seen. Now we shall see the reverse probability. Now what I wanted is, given that we have drawn red ball from the second bag, what is the probability that the first bag also, from the ball that we have drawn from the first bag also happened to be red ball? Okay, so now what is that I am asking? See, in this one we are conducting this experiment. Earlier also we have seen the question, right? So we are going to have an experiment conducted, and in which we are going to draw one ball from this and we are going to add to this one, and again we are going to draw one ball from that one, right? Therefore, what are all the events that will be present in the sample space? From the first one we might draw red ball, and from the second one we might draw a red ball, or from the first one we might draw a red ball, and from the second one we might get a green ball, or from the first one we might draw a green ball, and from the second one we might draw a red ball, and from the first one we might draw a green ball, and from the second one we might draw a green ball as well, right? And earlier, while finding out what is the probability of getting a red ball, which means this one, probability of R2, getting a red ball from the second bag. We have used the total probability theorem, in which we divided the sample space based on what happens for the first ball, and then we have applied this total probability formula for this event. That is what we did earlier, right? So earlier, if you remember, the formula that we have used is probability of getting a red ball from the second bag is equal to probability of getting red ball from the first bag and probability of getting red ball from the second bag, plus probability of getting green ball from the first bag and probability of getting red ball from the second one. Got it? And in order to solve this, we have used the total probability theorem, so which is probability of getting a red ball from the first one and then probability of getting the red ball from the second one, given that we have got the red ball from the first one, plus probability of getting the green ball from the first bag into probability of getting the red ball from the second bag, given that we have got the green ball from the first one. Got it? And these numbers we can easily get. So what is the probability of getting red ball from the first one? It is nothing but 2 by 5, right? So what is the probability of getting the red ball from the second one, given that we have got the red ball from the first one? In case we got the red ball from the first one, we are going to add it to this bag. Therefore, the number of red balls are going to be increased by 1. So total number of balls is going to be 4 plus 2, and the total number of red balls is going to be 4. Therefore, it is going to be 4 by 6 plus probability of getting a green ball. So what is the probability of getting a green ball from the first bag? 3 green balls are there, which means 3 by 5, and we are going to take this green ball and we are going to add it there, which makes 3 red balls and 3 green balls in the second bag. And so what is the probability of getting the red ball from that? It is going to be 3 by 6. So this is the total probability of getting the red ball in from the second bag, isn't it? Now assume that the question is about the reverse probability, which means if it is already given that we got a red ball, then what is the probability that the first ball is also red? Which means they are asking the reverse probability, the probability of first ball being red given that the second ball happened to be red. This event has already occurred, right? Which means, see this, now the entire event of getting a red ball actually comprises of 2 events. One is getting a red ball from the first one or getting the green ball from the first one. Now they are asking what is the probability of this, right? So since it is already given that the red ball has already occurred, which means earlier sample space was divided into 2 mutual exclusive events, and then our event was scattered like this, right? And now because of the conditional probability, the new sample space is going to be this part. Therefore, we are supposed to work on this new sample space, right? So we want to find out the probability of this event. So what is it? Probability of getting red ball and first time and second time, and this is the probability of getting green ball first time and red ball in the second time. Out of these 2 events, I want the probability of this one happening, and now the new sample space is this entire thing. How can you solve it? The same way, right? So what is it? It is equal to probability of red ball first and red ball second divided by probability of red ball first and red ball second plus probability of green ball first and red ball second. Alright, this denominator is nothing but this one, this entire thing. You can substitute there. Alright, so that is nothing but the conditional probability. You can apply it. So what is it? Probability of R1 into probability of R2 given R1. These numbers we already know, isn't it? Divided by probability of R1 into probability of R2 given R1 plus probability of G1 into probability of R2 given G1. You can substitute these numbers there and you can get this reverse probability. Again, it is an application of Bayes' theorem. Got it? So one thing you should observe is what should be in the denominator. That depends on what is the event they are talking about. Let us say the question is, let us assume that what is the probability of getting a red ball in the first draw given that we got a green ball from the second one. Then if you observe this, it is nothing but, see, one other way of writing it is it is equal to, I'll just tell you one more way. See this. Now we know that probability of first red ball intersection green ball is equal to probability of green ball into probability of red ball given green ball, isn't it? Now this is what they are asking. So you can just divide both sides with P of G2. See, the same way, the same one, don't get confused. I am trying to derive it from some other way. So it is nothing but probability of red ball intersection green ball divided by probability of green ball. Now what should you do here? You should substitute in this place the total probability that the second ball is going to be green. Now how can you do that? The total probability that the second ball is going to be green is equal to sum of these two events, right? So probability of R1 intersection G2 plus probability of G1 intersection G2. Again they are dependent events, and so you are supposed to apply conditional probability while expanding. Therefore denominator is going to change based on what is given, and numerator is going to be intersection of these two. Got it? So this is where from this formula we got this. And how did I expand this one? Using the total probability theorem. Using the total probability theorem I get this, right? And then from this, using the conditional probability, I am getting this. I hope you are getting everything right. Using the total probability theorem, I'll expand this one, and then these intersections I'll expand using the other one. So what is the other one? Is the conditional probability. Okay, this is how you can solve it. Now let's try this example. Earlier we have seen this. Let us say there is a box, and in the box we have 1 2 3 4 5 fair coins and 1 2 3 4 unfair coins. So in unfair coin, probability of getting a head is equal to, let's say, 1 by 3, and probability of getting a tail equal to 2 by 3. Total is 1. And in fair coin, probability of getting a head equal to probability of getting a tail equal to 1 by 2. And now various questions can be asked on this. So earlier we have solved a question that, see, I hope you remember the experiment. We are going to choose one of the coins randomly, and then we are going to flip. Now earlier question was, what is the probability that you will get a head, or what is the probability that you get a tail? Which means we wanted the total probability of getting a head, and we wanted the total probability of getting a tail. How did we do that? So the total probability actually depended here on two cases, right? See this. Probability of getting a head actually depended on two cases. One is probability of drawing the fair coin, and when I flip it I get a head, plus probability of drawing the unfair coin, and when I flip it I get a head. This is nothing but probability of getting the fair coin into probability of getting head, given that we have the fair coin, plus probability of getting the unfair coin into probability of getting a head, given that we have chosen the unfair coin, right? And similarly, what is the probability of getting a tail? Same thing. Probability of getting it depends on probability of getting a fair coin intersection probability of getting a head, plus getting an unfair coin and a tail. This is a tail, which is nothing but probability of getting a fair coin into probability of getting a tail when that fair coin is flipped, plus probability of getting an unfair coin into probability of getting a tail when that unfair coin is flipped. Now these are the total probabilities which we already know, right? So if you want, what does this evaluate to? We know that probability of getting a fair coin is nothing but 5 by 9 here, right? And what about probability of getting a head, given that it is a fair coin? For fair coin it is 1 by 2, plus probability of getting an unfair coin is 4 by 9. And what is the probability of getting a head for unfair coin? See, for unfair coin it is given that probability of getting head is 1 by 3. See, this probability of head and this probability head of different. This is probability of head given that it is unfair coin, right? Conditional probability. And similar way you can even evaluate this. What is the probability of getting a fair coin? It is 5 by 9 because there are totally 5 fair coins out of 9 total coins. And what is the probability of getting a tail given that it is a fair coin? It is 1 by 2. And what is the probability of getting an unfair coin? It is 4 by 9 because there are 4 unfair coins out of total 9 coins. And what is the probability of getting a tail given that it is unfair coin? It is 2 by 3. So these things, total probabilities, we can evaluate. Now let's talk about the reverse probability using Bayes' theorem. So what are the various questions they might ask is, one is, what is the probability that the coin happened to be fair coin given that we got a head? I'm listing down all the possible questions. Okay. Similarly, what is the probability that the given coin happens to be drawn coin happens to be a unfair coin given that we got a head? Similarly, what is the probability that the coin which we have drawn happened to be a fair coin given that we got a tail? Similarly, what is the probability that the coin happened to be unfair given that we got a tail? Now how can we do this? Again, by using Bayes' theorem, we know that whenever we have to do this one, it is P of F intersection H divided by P of H. This is one way of doing it. Now what is P of H? P of H is nothing but probability of total probability of getting a head, which is this one. So you substitute this entire thing in P of H, and in place of P of F intersection H, so F intersection H is going to be this part. Got it? So denominator is going to be this part which we evaluated, and numerator is going to be this one. Got it? And what about this one? What is the probability that the coin happens to be unfair given that a head is we got a head, is equal to probability of U intersection H divided by probability of H. Now what is P of H? It is the total probability of getting a head, which means this entire thing. What is U intersection H? Again, it is nothing but P of U into P of H given U, right? You can evaluate it. And similarly here also, what is probability of getting what is the probability that the coin which we have drawn happens to be a fair coin given that it is a tail? Then it is nothing but F intersection T divided by P of T. Now we know the total probability for tails. Total probability for getting a tail is this one. And what about F intersection T? F intersection T is this one, right? What about this? Again the same way, P of U intersection T divided by P of T, and we know that P of T is nothing but total probability which we have evaluated here, and U intersection T is nothing but this factor. Got it? You can substitute those factors here and you can get these reverse probabilities. In exam they might ask you only one of them, and this can be evaluated using Bayes' theorem like this. Okay, let's solve one more question on this. Assume that we have a bag, and in this bag there are M red balls and N green balls. So now we'll conduct an experiment in which we are going to draw a ball, and if the ball happens to be green, we are going to add, along with this originally drawn green, plus K green balls into the bag. If the ball happens to be red, along with this K withdrawn red, we are going to add K red balls into the bag, and then we are going to draw the second ball. Okay, did you understand the question? Question is, we are going to conduct an experiment in which we draw a ball from the bag, and then after drawing the ball, if the ball happens to be a green ball, we'll place that original ball back, which means the total number of balls will remain unchanged. Along with that, we add K green balls if the originally drawn ball is green. In case if the ball which we have drawn happen to be red, we place the red ball back, which means the number of balls here will remain unchanged. Along with those balls, we are going to add K red balls into the bag. Therefore, depending on the ball that you have drawn, either the red balls are going to increase or the green balls are going to increase by a number K. And after this, we are going to draw the second ball. So the experiment contains of drawing ball 2 times. First time we draw a ball, add it back, along with that we are going to add k balls, and second time from the total balls we again draw a second ball, right? So now what does the sample space contain? The sample space contain 4 events basically. So you might draw green one first, and the second one can be a red ball, or you might draw green one first and the second one might be a green ball, or you might draw a red one first and the second one may be a red ball, or you might draw a red one first and the second one might be a green ball. Now what are the various questions that can be asked on this? So first thing is, before asking, if you want to solve any question on reverse probability, you should first analyze the total probability, and after finding the total probability we shall go for the reverse probability. Okay, so one kind of question they can ask is, what is the probability that the second ball happens to be red, which means this is what they are asking. Got it? So in order to solve this, again using total probability theorem, you have to divide the sample space into 2 events based on what happens in the first ball. If the first ball happens to be green or the first ball happens to be red. Got it? And our required event is actually spread across these 2 mutually exclusive events. So we can apply the total probability there, right? So what is the probability of getting the red ball when I draw it for the second time? It is equal to probability that we get the green ball first and red ball second, plus probability that we get the red ball first and red ball second. Now how can you evaluate it? Again by using conditional probability, because these 2 events are dependent. The reason is, initially drawing green ball or drawing red ball are independent. I mean, they don't depend on what happens, but later second time when you're drawing it, that depends on what happened in the first time. Okay, see this? For that reason, let's write all the probabilities. Probability of getting green ball first is equal to, out of m plus n balls, the number of green balls happen to be how many? N balls. That is equal to n by m plus n, right? And probability of getting a red ball, which means R1, is equal to m by m plus n. Now what happens is, if I draw a green ball, then I am going to add the green ball back, along with that I am going to add k green balls. Therefore the number of green balls will be n plus k and the red balls will be same. If I draw a red ball, I'll add the red ball back, along with that I will add k red balls, which means m plus k red balls will be there and n green balls will be there. These are the 2 cases, right? So now let's analyze this one. What is the probability of getting a red ball given that we have drawn a green ball in the beginning? This is equal to how much? So what is the probability of getting a red ball given that we have drawn a green ball in the beginning? So if you have drawn a green ball in the beginning, you are going to add the green ball back, along with that we are going to add k green balls, but the red balls doesn't change. So red balls are going to be m itself, but the total number of balls are going to be m plus n plus k. Got it? Why? This is going to be green balls and this is going to be red balls. Got it? Similarly, probability of getting a red ball given that we have drawn the red ball first. In this case, the number of red balls are going to increase by k, which means m plus k divided by m plus k plus n. This is the number of red balls now. Given that red ball is drawn, the number of red balls are going to increase. Given that green ball is drawn, the number of green balls are going to increase. Depending on that, I have evaluated it, right? Similarly, you can even find out what is the probability of getting a green ball given that we have got the green ball first. In this case, the number of green balls will increase. The number of green balls are going to be n plus k. Total number of balls are going to be n plus k plus m. This is the green balls and this is the total balls, right? And similarly, probability of getting a green ball given that we got a red ball first, is going to be the number of green balls doesn't change, but the number of total balls will change because the number of red balls are increased by k now. This is the number of red balls. So these are all the probabilities that we got now, right? And using this we can directly get, substitute them in this formula. Now what about this one, P of G1 intersection R2? It is nothing but probability of getting a green ball first into probability of getting a red ball second, given that we got the green ball first, plus probability of getting a red ball first into probability of getting a red ball second time, given that we got the red ball first. And we can substitute all these values in them, and we can get the required answer. Alright, and similarly we can even think about this probability of getting green ball second time is equal to probability of getting this one, right? This is the event that we are talking about. Probability of getting green ball first and green ball second time plus probability of getting red ball first and green ball second time, which is equal to probability of getting green ball first into probability of getting green ball, given that green ball has come first, plus probability of getting red ball first into probability of getting green ball, given that we got red ball first. So we know this one, this one, this one, this one. We know this one, this one, this one, this one. Just now I have written all of them, right? And that is how we can find out the total probability. So total probability theorem can be used to evaluate this. And now let's say I want to find out the cause, which means given that we have already got the red ball, okay, what is the probability that the ball originally drawn first time happens to be red? It is reverse probability. Got it? Now I want to analyze the cause, and also given that red ball has come out, what is the probability that original drawing gave me a green ball? And given that green ball has come out second time, what is the probability that red ball has come out first time? Given that green ball has come out second time, what is the probability that green ball has come out first time? Now how can we answer it? By using the conditional probability formula or base, right? So what is it? P of R1 intersection R2 divided by P of R2. Now what is P of R2? Total probability of getting R2, which we have already evaluated. And what is P of R1 intersection R2? It is nothing but this factor. Using conditional probability, using total probability we evaluate it, using conditional probability we evaluate it, right? What about this one? It is P of G1 intersection R2 divided by P of R2. What about this? P of R1 intersection G2 divided by P of G2. I think you know how to evaluate it. This is total probability and this is the factor which we know already. Total probability is this one and this factor is nothing but this one, conditional probability. And what about this one? Using total probability P of G2, which means this one, this entire thing, and R1 intersection G is nothing but this one, which means this one. Alright? And what about this one? P of G1 intersection G2 divided by P of G2. P of G2 is total probability and P of G1 intersection G2 is this one. Got it? So this is how we can evaluate the reverse probabilities. So given these events, given these I think 6, right? Given these 6, we can find out the total probability as well as all the reverse probabilities. In GATE they will ask you any one of them. Okay. So earlier we have seen a question, if you remember, that there is a multiple choice question and a student knows it by probability P and she guesses it by probability 1 by P. In case if she guesses it, the answer will be right with probability 1 by M. I hope you remember that. Earlier we have seen in the total probability example, that question was really big, that is why I am not writing it, I am just explaining orally. So the question is like this. A student knows the answer by probability P, and if she knows it, she will answer it correctly, and she guesses the answer with probability 1 minus P, right? If she guesses, the answer will be right with probability 1 by m, and it will be wrong with probability 1 minus 1 by m. Earlier we have found out what is the probability that she answers it correctly. Probability that she answers it correctly is equal to probability that she knows the answer and answers it correctly plus probability that she guesses the answer and she answers it correctly, which is equal to probability that she knows the answer into probability that she answers it correctly given that she knows the answer, plus probability that she guesses the answer into probability that she answers it correctly given that she has guessed the answer, right? And we know that it is nothing but P, she knows the answer, and once she knows the answer, she knows it, which means with 100% certainty it will be correct. In case if she doesn't know it, in case if she guesses with 1 minus P, then the probability that it is correct is 1 by m. This is the probability that is correct, right? Now let's talk about reverse probability. Now assume that while correcting the question paper, you have found out that the answer is correct. Now what we want is probability that she might have guessed given that the answer is right. Now you want to know whether she has guessed or not. What is the probability that she might have guessed? Again, this is a reverse probability, right? So in order to solve it, you might have to solve this probability of G intersection C divided by probability of C, and this probability of C is nothing but the total probability of answering it correctly, which is nothing but this factor. And what about probability of G intersection C? G intersection C is where is it? The probability that G intersection C is this one, yeah, which means this factor. So this factor, got it? So you can answer it directly like that. It is also an example of reverse probability. Or they might ask you, what is the probability that she knows the answer given that she has answered it correctly, right? So I want to find out whether she has guessed it or she knows it. Now how can you do that? Probability that K intersection C divided by P of C, and P of C is nothing but the total probability, and P of K intersection C, this part is equal to this one, which is nothing but P, that equal to P by P of C. Got it? Okay. Now earlier, if you remember, we have seen this question. There is a person A and he has reached the finals and he is waiting for the opponent, and now the opponent will be one of these two, B and C, and they are going to fight in the semi-finals, and whoever wins in the semi-finals will fight with A. Let us say, I don't remember the numbers, I'm just changing the numbers, but anyway the concept is same. Let us say the probability that B will win the semi-final is equal to 1 by 3, the probability that C will win the semi-final is equal to 2 by 3. Got it? And in case if A fights with B, if he fights with B, A will win with probability 2 by 3, and if A fights with C, A will win with probability 1 by 3. Now what is the probability that A will win? This is total probability, which we have already seen. Probability that A will win is equal to probability that B wins the semi-final and A wins the final, plus probability that C wins the semi-final and A wins the final. Now it is equal to probability that B wins the semi-final into probability that A wins the final given that B won the semi-final, plus probability that C wins the semi-final into probability that A will win the semi-final given A will win the final given that C has won the semi-final, right? So this one we have already evaluated. It is nothing but 1 by 3 is the probability with which B will win, and A will win it 2 by 3, and C will win with 2 by 3, and A will win it 1 by 3. This we have already known this. Now let's say we want the reverse probability, that if we know that A has won the match, right, what is the probability that he fought with B in the finals? Are you getting this? A has won the match. Now what is the probability that he fought with B in the finals? Which means, what is the probability that B might have won the first match? Given that A won the finals, what is the probability that B might have won the semi-finals? It is equal to P of A intersection B divided by P of A, and P of A we already found it, right? P of A we have already found it, this one. And what is P of A intersection B? P of A intersection B is equal to P of A, P of B into P of B given A, this factor. We know that, so we can find it directly. Also the reverse probability can be asked like this: given that A won the trophy, what is the probability that C won the semi-finals? Again we can do it using the Bayes theorem this way: probability of C intersection A divided by P of A. Now what is P of C intersection A? This factor, and P of A is total probability, which we have just computed, and we have all the factors required to compute P of A. Therefore we can do that. Got it? So this is how we can answer this reverse probability question, right? Now let's say we are conducting an experiment, and in this experiment I want to toss two fair coins, and when I toss the coins, the sample space, when I toss two coins, the sample space is going to be either both the coins are going to be heads, or first coin is going to be head, second coin is going to be tail, or first coin is going to be head, or both of them are going to be tails. Got it? And now I'll create a new variable. Let us name it as X. Okay. Now what is the purpose of this variable is, it will count the number of times head turns up. When I flip two coins, what is the number of times the head turns up? So that is counted by this variable. Then we can call such a variable as random variable. A random variable is nothing but a function which will take the events or the possibilities of the sample space, and then it will give us some number. Okay, so just see this, I'll explain you. Now if X represents the number of heads that can be possible when I toss two fair coins, then what are the possible values that X can take on? When you flip two coins, either both of them can be heads, or only one of them can be head, or none of them can be heads. Got it? Therefore the random variable X can take 2 or 1 or 0. And then if you talk about the probability with which X can take the value 2, X can take the value 1, or X can take the value 0, then it is called as probability distribution. Are you getting this? We are conducting an experiment as usual, like earlier, random experiment, and then we are not exactly interested on the exact output, like what is happening on the coins. We are not interested in that. Rather than that, we are interested in a function of the output. What is the function here? We are interested in the count of the number of heads, isn't it? Therefore such a variable X is called as random variable, and when we try to assign the probabilities for each possible value of X, then it is called as probability distribution of the random variable. I'll show you with few examples. See this one first. Now what is the probability that X can take the value 2? What is the probability that X can take the value 1? What is the probability that X can take the value 0? Now in order to find it out, we have to see what are the events that are favoring X equal to 2. If you have to get two heads, right? So first of all, what about the probabilities of each of the occurrence here? Since the two coins are fair coins, probability of getting a head is 1 by 4. This is 1 by 4, this is 1 by 4, and this is 1 by 4. This you already know, either by using that intersection, which is independent events, or by seeing that there are 4 events which are all equally likely possible, we are assigning 1 by 4. I think you know how I am assigning this, so I am not going to take that again. But then see this one. What is the probability that x is going to be 2? For this one, the favorable event is head. Therefore, the probability is 1 by 4. Got it? What is the probability that x is going to take 1? So either this event or this event, both are favoring the x equal to 1. Therefore, this is equal to probability of this one plus probability of these two events, which is going to be 1 by 4 plus 1 by 4, that equal to 1 by 2. What about this? It is nothing but probability of the event of getting 2 tails, which is 1 by 4. Got it? Let's see one more example. Let us assume that I am flipping a coin which is having, I am flipping 3 coins, okay, 3 fair coins. Then what are the various outputs possible? All 3 can be heads, or head tail, or head tail head, or head tail tail, or tail head, or tail head tail, or tail head, or tail tail. Got it? Now all these events are equally likely because all the coins are fair. So for all these events we are going to give 1 by 8 as the probability. All are equally likely. Okay. Now assume that we are interested in finding out, let's say a new random variable x is defined, and x counts number of tails that come out. Okay, so let me call it y. You might get confused because I have already used x there. So x is the number of tails that may come out. Now when I am tossing 3 coins, how many tails can come up? Sometimes 0 can come up, or 1, or 2, or 3. Therefore, there is a chance that y will take a value 0 with certain probability, 1 with certain probability, 2 with certain probability, and 3 with certain probability. And y is called as, again, a random variable. Got it? Why is it a random variable? Because it is not a normal variable. It can take any of these values randomly. Got it? And we can assign probabilities to each one of them. So see this, what is the probability with which capital Y can take a value 0? Right, such questions can be asked. Now if you want 0 number of tails, what is the event that is going to be favorable? Only this one, so which is nothing but 1 by 8. What is the probability that Y is going to take a value 1? So what are the events in which you get only one tail? So 1, 2, 3, only 3 events, right? You can check it. Yeah, only 3. So it is going to be 3 by 8. What is the probability that it can take value 2? So value 2 is going to be 2 tails. So 1, this is 1, and this is 1. 2 by 8. What is the probability that we are going to get 3 tails? So 3 tails is going to be 1 by 8, right? Did we miss out anything? Just see about 2 tails. 2 tails is going to be 1 here, and then 2. Oh, this one is also has to be counted. So there it is going to be 3. Okay, now check this. 3C1, 3C0, 3C1, 3C2, 3C1, 3C3. Okay, fine. So now again, this is the probability distribution for this random variable, right? Now if you observe this, there are certain interesting points about these random variables. Now if you see this, random variable is going to take each occurrence here and it is going to assign some value to this. For example, if you want to find out what is y of HHH, it is going to say it is 0. The reason is, in this HHH, even 3 heads are going to occur, the number of tails are going to be 0. Now if we take this HHT, then what is the y of HHT? It is going to be 1, right? So which means your random variable will actually is a function, it is actually a function, right, which will take sample space as input and give you some number. It can sometimes be an integer or it can sometimes be a range, but in this case it is going to take a sample space, yes, and in this case it is going to give us one of these 3 numbers, 0, 1, 2, 3. Got it? It is going to take sample space and it is going to give us one of the numbers, which means we can take any point from this and we are going to assign one number to that. You can even think of it here as well. So that is the first point. And the second point is, when you add up all the probabilities that are being assigned to the random variable, it will again be 1. So if you see this, you add these 3, 1 by 4 plus 1 by 2 plus 1 by 4, it is going to be 1. Similarly, you add these 4, right, it is going to be 1. Got it? So that is how we can think about random variables. Now let us say when I am going to roll 2 dice, so how many outputs will be possible? Totally S equal to 1 1 1 2 so on 6 6, which means 36 outputs will be possible, and the probability of each output will be 1 by 6, right? And then we can define a new random variable z. Okay, 1 by 36. We can define a new random variable z in such a way that z is the sum of whatever comes on two dice. So if z represents the sum of values on 2 dice, right, then what is z? Z is a random variable again. Then what are the possible values for z? So z can give you either values 2 or 3 or 4 so on 12. So why is this so? Because when I roll 2 dice, when I add the whatever comes up on these 2 dice, it can either be 2 or 3 or 4 or 12. It cannot be less than 2, because minimum value possible on the dice is going to be 1. When I add 1 and 1, it is 2, and maximum value that is possible on dice is 6. Therefore it cannot be more than 12, because I am rolling 2 dice. Got it? And then you can find out what is the probability that z can take the value 2. So it is nothing but, how many cases will this 2 will come? Only one case, whenever the dice are showing 1 1. Therefore it is 1 by 36, right? In case if you want to see what happens for z equal to, let's say, 3, then what are the favorable cases for this? All the favorable cases are nothing but 1 comma 2 and 2 comma 1. Only 2 favorable cases, and each case is having a probability 1 by 36. Therefore for this one the probability is 2 by 36. What about the probability that z equal to 4? So what are the cases we have? So all possible cases are 1 3, 2 2 and 3 1. Therefore it is going to be 3 by 36. So on, what is the probability that you are going to get 12? So what are the events that we have here? 6 comma 6, only this is the favorable event, right? So it is going to be 1 by 36. So again we can apply, or we can give numbers, probabilities to each of the possibility. This is called as probability distribution. Now we have seen the examples on random variables. In general, random variables can be classified like this. They can be majorly of 2 types. One is discrete random variable and other is continuous random variable. So what is discrete random variable is, all these examples are actually discrete random variables, which means the value that a random variable will give us will be a point, will be discontinuous point like this, 1 2 3 4 like this. There will be some finite set or countable set. Countable set means something like natural numbers, and from which your random variable can take the values. And what about the continuous cases? So sometimes random variable need not be giving you a single value, it might give you a range. For example, if you assume that, let's say, x is a random variable which denotes lifetime of a car. If you are talking about that problem, then lifetime of a car may not be exactly 2 years, it can be anywhere in the range of 2 to 4 years, then we are going to represent lifetime of the car to be 2 to 4, like this, right? So in this case it is not a discrete event, it is a continuous event, because we are talking about anywhere between 2 to 4 and there will be infinite number of points possible between this, right? So random variables can be divided into two types: discrete random variables and continuous random variable. And even after that we can again divide discrete into many types and continuous into many types. Okay, we shall discuss about all these types, and then once we discuss it, this topic will be over. Okay, fine. Now let's see one example. In general, let's talk about random variables in a shortcut first. See, if you want to observe what is happening here, simply put, we'll have a sample space, right? And then random variable is nothing but it will take each point in the sample space and it will map it to a number, some real number, right? In some case what happens is, random variable, depending on what type of values this random variable can take, we are going to define it as discrete as well as continuous. I'll show you those examples later. And then what happens is, with some probability, random variable will get the values in this real number set. And now when I assign these probabilities to these numbers, then that is called as probability distribution. Got it? So simply put, there will be sample space and a random variable will take each point in the sample space and will give us some number, some real number. And then if you try to find out what is the probability with which each number in this set can occur, then that is called as probability distribution. And random variables can be of various types, discrete and continuous. I'll show you the examples later. Now we shall see. So what is that I wanted to prove is, once you find out all these probabilities, if you add them all up, then the sum is going to be 1 always. For example, in the earlier example, what is the probability tossing a coin 2 times? Let's say x is the variable which is counting the number of heads that might occur when we flip a coin twice. X can be 0, or x can be 1, or x can be 2. Now the probability that x can be 0 is 1 by 4, the probability that x can be 1 is 2 by 4, and the probability that x can be 2 is 1 by 4. When I add them all up, the sum was 0, right? And similarly we have even seen the other example. In that also, when we sum all the values, then we got it is the sum of all probabilities as 1. Let me show you one more example in which the number of points are not actually finite, but they are countable. I hope you know the difference between finite and countable. If you didn't know that, please watch the TOC videos where we have discussed about finite sets, countable sets, uncountable sets, all those. Okay, so for now let's see. Okay, if you want to know what is countable in simple ways, if you can put a set in 1-to-1 correspondence with the set of natural numbers, then they are called countable. Okay, fine. Now let us say we are conducting an experiment in which the probability, I'll be flipping a coin first, and the probability of getting a head is P. Okay, what is it? Probability of getting a head is P. Now what does it mean? Probability of getting a tail will be 1 minus P. If P happens to be 0.5, then the coin is fair. If P is not 0.5, then the coin is unfair. But we need not worry about what type of coin it is already given. So the probability of getting a head is P and the probability of getting a tail is 1 minus P. Then what I do is, the experiment is about, I'll keep on flipping the coin until I get a head. I'll keep on flipping it till I get the first head. Let us say this is the experiment. Then the question is, now let's try to define the random variable. Okay, let's say random variable capital N denotes the number of times I'll have to flip the coin so that I can get the head. Are you getting this? See, experiment is simple. I have a coin and the probability of getting a head is P and the probability of getting a tail is 1 minus P. This is very easy, right? And the next step is, experiment is simply flipping the coin until I get a head, and let capital N denote a random variable which indicates the number of times I'll have to flip the coin until I get the first head. Okay, now what are the various values possible for n? N can be 1, which means sometimes when I flip the coin, immediately I can get the head in the first try, or n can be 2, which means first time there might be a tail and second time there may be head, or n can be 3, which means tail tail head, like that. Therefore n can take any value till infinity. Now what is the probability that we want to assign to each value of n? Now let's see this. Probability of capital N equal to 1. What do you mean by this? This is nothing but the event. If you flip the coin, if first time itself if you get the head, then n will take the value 1. So what is n here? The number of times we will have to flip the coin in order to get the head, right? So n equal to 1 means directly I flip the coin and I got a head. So whose probability is p, isn't it? Similarly, what about p of n equal to 2? What does it mean? Now in order to get the head for the first time, I'll not get it for the first time, but I'll get it in the second time, which means first time I'll get a tail and second time I'll get a head. And we know that these are independent events and it can be written as p of t intersection h, and since they are independent events we can multiply them, which means probability of getting a tail followed by a head equal to probability of getting a tail into probability of getting a head, because they are independent events. When I flip a coin 2 times, both times the outputs are independent, they are not going to depend, right? Therefore it is equal to probability of getting a tail, which means 1 minus p, into probability of getting a head, which is p. And similarly, p of n equal to 3. What does it mean? Now I'll be getting the head in the third trial, not in the first one, not in the second one. Therefore this event is same as getting a tail followed by getting a head, which is nothing but 1 minus p into 1 minus p. Are you getting this? This 1 minus p is related to getting the tail followed by p, right? And similarly so on. What is p of capital N equal to n? So small n. Now what is the probability that you get the head in the nth time, where small n is some number? Then what can you say about it? P of tail so on, n minus 1 times you should get tail followed by a head, so which is nothing but 1 minus p power n minus 1 into p. Got it? Now when I sum them all up, so what is the sum of all this? Sigma small n equal to 1 to infinity p of capital N equal to n. So what do I mean by that? I'm just adding them all up from 1 to infinity, because in this experiment I don't know whether I'll get a head or not, right? I'll keep on flipping it. So when I sum them all up, then what is it? It is p plus 1 minus p into p plus 1 minus p square into p plus 1 minus p cube into p plus so on infinity. Now what is this? This one is equal to, if you pull out p as common, 1 plus 1 minus p plus 1 minus p square plus so on, right? So if you see this is infinite geometric progression with a common difference of 1 minus p, right? And we know that in infinite geometric progression the sum of all terms is going to be a by 1 minus r, in case r is less than 1, and in this common difference r 1 minus p is of course less than 1. The reason is always the probabilities are less than 1, right? See, probability of getting a head and this is the probability of getting a tail, 1 minus p, that is obviously going to be less than 1, because sum of these two is going to be 1, isn't it? Therefore it is going to be a into 1 minus 1 minus p. Then what is this? It is going to be 1. Got it? Therefore we have again seen that even if the number of values we are going to take is infinite, when I sum them all up, the probabilities is going to be 1. For any random variable, you can we'll always get this. With examples I'll show you all this. Okay, fine. Just for the sake of definition, I have given you the exact textbook definition about Bernoulli random variable, but what I'll do is I'll take examples and in simple words I'll explain you this concept first. So in this particular random variable, this random variable will take two values, either 0 or 1. So simply put, let us say you are playing, you are at a gambling, okay, and you are at a table, and the this game is like this. Someone will throw a die, and you are supposed to pick a number, and if the number you picked up, if it turns up, then it means that you won it, right? Then that particular number, I call it as a success, and the other numbers I call it as a failure, right? So for example, what I mean to say is, now we are talking about the dice. You are rolling the dice. Now you have picked up, okay, what is the sample space? Sample space is going to be 1 2 3 4 5 6, right? Let us say you have picked up number 1, right? What does it mean? If you pick up this number, and if this number comes on the dice, then it means that you get a success, and if any of these other numbers comes up, then it means that it is a failure, right? Then the probability of this event is 1 by 6, and the probability of all the remaining events is 5 by 6. Therefore, according to this experiment, the probability of success is 1 by 6 and the probability of failure is 5 by 6. Therefore, probability of success we denote like this: P of capital X equal to 1, right? So what do you mean by P of capital X equal to 1 means, see, these two ones are different. What I mean here is, it is denoting the probability of success. Probability of success equal to 1 by 6, and P of capital X equal to 0. It is nothing but failure. It is 5 by 6. Now here this random variable capital X is called as Bernoulli random variable. So what does it mean? In any experiment, you should be able to divide the outcomes into two parts. One is success and other is failure. Now capital X equal to 1 means you have succeeded. Capital X equal to 0 means you have failed. For all these, for this entire event of getting all these numbers, we are assigning the random variable will take the value 0. For this value, the random variable will take the value 1, right? Probability that X equal to 1 is called as probability of success, and probability that X equal to 0 is called as probability of failure, which means in any experiment, if we can divide the sample space into success and failure, and if we can find out the probability of success and give it as the probability that X will take it as 1, and the probability of failure and give it as the probability that X will take it as 0, then such a random variable is called as Bernoulli random variable. Therefore, Bernoulli random variable will take only two values, one is 0 and other is 1, isn't it? So what is the difference between the earlier ones and this one? Nothing is different here, just the number of values it can take has changed, and in fact it is again a discrete random variable. Why? It can take only discrete values 0 and 1. It is not taking a continuous range, isn't it? You can see one more example. Assume that people are flipping two coins, right? And the experiment is people are flipping two coins. Then what are the events? Head head, head tail, tail head, and tail tail. Now you have decided that if you get two heads, you will win, otherwise you will lose. Then in this case, the success is nothing but this one, and the failure is nothing but this one. So what does it mean? This is the entire probability of failure, and this event is completely failure event, and this event is success event. Therefore, what is the probability that you will win? Probability for X equal to 1 is nothing but probability of HS, which is nothing but 1 by 4. What is the probability of a failure? Probability of X equal to 0 is 3 by 4. Got it? And since we have defined a random variable for just two events, success and failure, and we have divided this entire sample space into two events, success and failure, and we have given these probabilities, it is called as Bernoulli experiment, right? Or you can simply take like this: maybe your experiment may be flipping one coin, then what about sample space, head and tails? Then you might have picked up head as success and tail as failure, right? Then what is the probability of success? if it is a fair coin, probability of success is going to be 1 by 2. Probability of failure, if it is a fair coin, it is going to be 1 by 2. Since again you have divided the sample space into two events, success and failure, and you have defined a random variable x in such a way that x takes a value 1 whenever there is success and x takes a value 0 whenever there is a failure, and you have assigned these probabilities, you can call this variable x, this random variable, which is of course a discrete random variable, as Bernoulli random variable. Now let's see the definition. See this: in an experiment whose outcome can be classified as either a success or a failure, let capital X equal to 1 if the outcome is success and capital X equal to 0 if it is a failure. Then the probability mass function, okay, there is a term called as probability mass function, which is nothing but assigning probabilities to the values of random variables, which means this one, right? So what is the probability that capital X equal to 1? It is 1 by 4. Capital X equal to 0 is 3 by 4. This is called as probability mass function, right? The function which is assigning probabilities for all possible values of a discrete random variable in general is called as probability mass function. So that is the standard terminology. You need not by heart it, you can just think of it as a probability function. That is also fine, but I have taken exact words from the textbook, right? Say this: in an experiment whose outcome can be classified as either a success or failure. In this case, this entire thing is classified as success and this entire thing is classified as failure. In this case, this is success, this is failure, this is success, this is failure, right? Either as success or a failure, let capital X equal to 1 if outcome is success. Say this: capital X equal to 1 if outcome is 1 in this case, if outcome is 1 1, if outcome is head, right? So is success, and capital X equal to 0 if it is failure. Then the probability mass function of capital X is given by P of X equal to 0 is equal to 1 minus P, and P of X equal to 1 equal to P. So what they mean to say is, if you add these two up, you are going to get 1. Check this: add these two, you are going to get 1, add these two, you are going to get 1, add these two, you are going to get 1. Got it? Then X is a Bernoulli random variable. So simply put, in any experiment, if you have only two possible outcomes, even though the outcomes are many, if you can divide them into two broad classes, one is success and other is failure, and if you can assign a random variable denoting success and failure, then such a random variable is called as Bernoulli random variable. Okay, let's see binomial random variable. So a binomial random variable, you can think of it as if it is a collection of all or many Bernoulli random variables. Earlier we have seen the Bernoulli random variable, right? Binomial variable is actually a combination of Bernoulli variables, right? So since there is a very little difference between them, that is why people don't really give much weightage to Bernoulli random variables. Even in GATE, they didn't mention in the syllabus Bernoulli random variable. Actually, there is nothing to talk about it. That is why they didn't mention in the syllabus. But about binomial random variables, there will be some questions possible on that. So one way to think about binomial random variable is, it is a collection of Bernoulli experiments. Okay, to put in other simple words, just think about it. Let's say we are having an experiment. In that experiment, we are going to flip a coin. If you get a head, it is a let's say it is a success, and if you get a tail, let's say it is a failure. And assume that we are taking n coins and we are going to flip them, n coins. Then each of them can result in a success or each of them can result in a failure. Then if we count the number of successes using a random variable, then that random variable is called as binomial random variable. Are you getting this? Let us say we are flipping n coins, and when we flip a coin, head is a success and tail is a failure. And if you are flipping n coins, out of these n coins, some of them may come up as successes and some of them may come up as failures. And if you count the number of successes using a random variable, that random variable is called as binomial random variable. Got it? Let us assume that we are flipping 4 coins, and the probability of getting a head is 1 by 2 and the probability of getting a tail is 1 by 2. Assume that this particular probability is success, getting a head is success and getting a tail is a failure, and you are flipping 4 coins in total, then what is the probability that you get exactly one success, right? So what is the probability that you get exactly one success? If that is asked, how can you answer it? See this. So exactly one success means out of these 4 coins you should get exactly one head. So that one head can be first one, or that one head can be second one, which means, or that one head can be third one, or that one head can be fourth one, right? So if you add all these cases, the probability of all these cases, then we'll get the probability of that getting exactly one success. How to do that? See this. If you see any of these cases, all these cases will have same number of successes and same number of failures. Therefore, if probability of head is p and if probability of tail is 1 minus p, all of them individually are going to have probability of p into 1 minus p cube, right? Here it is p multiplied with 1 minus p into 1 minus p into 1 minus p. Here it is 1 minus p into p into 1 minus p into 1 minus p. Here it is 1 minus p into 1 minus p into p into 1 minus p. Anyway, it is going to be p into 1 minus p power this one, right? And how many such events we have? That is nothing but how many ways you can arrange them, right? So we know that since it is a repetition, right, we can know the arrangements. So it is what is the arrangements here? You can see it is 4c1 or 4c3 you will get. Okay, so 4 factorial by 3 factorial, that is what you get. So total number of arrangements, total number of items is 4, therefore 4 factorial divided by repetitions are 3 factorial, which is nothing but 4c1. Alright, so this is how we can find out. And since here we are counting the number of successes, so what is this exact probability? The probability that number of successes equal to 1, equal to this, right? Similarly, if you want to count the number of p of x equal to 2, which means if you want to count the events that the number of successes is equal to exactly 2, then it is nothing but how many ways we can get 2 heads and 2 tails, right? So again that we can do with, if you have to have 2 heads, it is going to be p square. If you have to have 2 tails, it is going to be 1 minus p square, right? And then these 2 heads and 2 tails have to be arranged. We know that totally there are 4 values, that is why 4 factorial divided by 2 heads and 2 tails are repeated, 2 factorial into 2 factorial, which will turn out to be 4c2 into p power 2 into 1 minus p power n minus 2, right? So this is what is called as Bernoulli random variable. So again, simply put, what is Bernoulli random variable? If you are going to conduct n experiments, and every experiment there can be either a success or failure independently, which means every experiment individually taken is going to be Bernoulli experiment. Now we are combining all these n experiments, right? And now when we perform them, then if we try to count the number of successes we might get out using a random variable, that is called as Bernoulli random variable. Got it? So see this one. Suppose n independent experiments, each of which results in a success with probability p and a failure with probability 1 minus p. So which is nothing but Bernoulli event, each one, isn't it? So it need not be just a flipping of a coin, it can even be rolling a dice, but you have to define clearly what is success and what is failure. You might define that success is getting 1 and failure is getting any other number other than 1, or success is getting an even number and failure is getting an odd number. Whatever it is, you should be able to divide the sample space into 2 parts, that one part is going to be success and other part is going to be failure. Then you should find out what is the probability of success and what is the probability of failure. Of course, if you add both of them, it is going to be 1, right? So once you have such an event, then if you combine experiment and if you combine n such experiments, and then after performing all these n experiments together, if you try to count the number of successes, see this, are to be performed if capital X represents the number of successes that occur in n trials, right? So you are conducting the experiment 10 times and you are actually counting how many times you get the success. Then capital X is called binomial random variable with parameters n and p, which means if you want to talk about a binomial random variable, you should give two values: how many times are you conducting the experiment, which is n, and what is the probability of the success in each experiment, which is p. If you can give these two parameters, you can talk about that variable. Now the probability mass function of the binomial random variable, that probability mass function is nothing but the probability function, right, for a discrete random variable. Again, this is a discrete random variable, isn't it? This is clearly a discrete random variable because we are going to have some fixed values. If you are going to toss let's say 4 coins, the success can be 0 or 1 or 2 or 3 or 4, isn't it? Which means you have finite values and these are all discrete values, right? That is why it is a discrete random variable. Then the probability mass function is given by p of I equal to nci into p power I into 1 minus p power n minus I. nci means, you know that, n factorial divided by n minus I factorial into I factorial. You please look at the combinatorics videos, you will understand this better. Are you getting this? nci means n factorial divided by n minus I factorial into I factorial, right? So that is what just we have explained here. So p of I is nothing but what is the probability of getting I successes, that is nothing but nci into p power I, because successes have to be I times, isn't it? That is why we are taking p power I. And what is 1 minus p? It is failure. So out of n trials, if I are successes, then n minus I are going to be failures. That is why nci into p power I into 1 minus p power n minus I, right? So also we can prove that if you take all these probabilities and if you add them up, it is going to be 1. Why? See this. If you are conducting n experiments, then how many successes will be there? Successes will be either 0 or 1 or 2 or so on n. Now you add them all. nci into p power I into 1 minus p power n minus I. So which is nothing but this is a formula in the binomial expansion. If you remember that, a plus b power n, right? Then each term is nothing but like this, isn't it? Where a is this and b is this. Therefore, you can think of it as p plus 1 minus p power n, which is nothing but 1 power n, which is equal to 1, right? Which means sum of all probabilities is again going to be 1. Got it? We shall see some problems on this, you will understand it better. It is known that any item produced by a certain machine will be defective with probability 0.1 independently of any other item. What is the probability that in a sample of 3 items, A, exactly 1 is defective, B, at most 1 is defective, C, at least 1 is defective? So which means a machine is producing some items and the probability with which it will be defective is 0.1. Let us say the probability with which it is defective be denoted with P and it is 0.1. Now it is similar to the binomial we can use the binomial random variable to explain this. Okay, so how can we do it? Each one is going to have a probability of 0.1 for failure or defective. Let's consider that event. Instead of considering the success, let's go with the defectiveness as the success, right? Then they are asking exactly this. If x denotes the random variable, that binomial random variable, then first one is exactly one defective piece, which means they are asking about p of capital X equal to 1. What is the probability that you have exactly one defective piece? Exactly one defective piece is out of 3 pieces, 1 has to be defective, right? And what is the probability for that? 0.1, which means 1 has to be defective, that 1 will have the probability 0.1 and other 2 have to be normal. So non-defective is 0.9. So if the defective piece is 0.1, then the non-defective is 0.9, right, square. So this is the probability for exactly one defective piece. Now the second question is at most one defective piece, which means either the defective pieces can be 0 or the defective pieces can be 1. So what does it mean? P of x equal to 0 is 3C0 into 0.1 power 0, which means nothing is actually defective, all the three are working fine, right? Into 0.9 power 3, or you can directly, you could have written it as 0.9 power 3, which means all the three are going to be non-defective, and the probability that each one is going to be non-defective is 0.9. That is why 0.9 power 3. Now if you see this question B, they are asking about at most one defective piece, means both, exactly 0 defective pieces plus 1 defective piece. So if you sum these two up, you are going to get at most one defective piece, and C is at least one defective piece. So at least one defective piece means probability that one is defective plus probability that two are defective plus probability that all the three are defective, if you had to sum these three. And for x equal to 1, we have already seen this. What about x equal to 2? P of x equal to 2 is 3C2 into exactly two of them have to be defective. So probability that each one is going to be defective is 0.5. Since there are two defective pieces, I am writing 0.1 power 2, and one of them is non-defective, that is why 0.9 plus P of x equal to 3, it is nothing but probability that all the three are defective. So using the formula, you can write it as 3C3 into 0.1 power 3 into 0.9 power 0, right? So which is nothing but 3C3, you could have directly written it as 0.1 power 3. Why? There are only three pieces, all of them are going to be defective. Even by this formula also, you will eventually get that 0.1 power 3. Okay, so you have to add this one plus these two, then we are going to get exactly. So this is how we can apply this binomial random variable in order to solve the questions. Okay, let's see the next discrete random variable. It is called as Poisson random variable. A Poisson random variable capital X taking on the values 0, 1, 2, so on. So it can be any values like 0, 1, 2, 3, so on, is said to be Poisson random variable with parameter lambda if for some lambda greater than 0, P of I equal to P of x equal to I equal to e power minus lambda into lambda power I by I factorial. Just remember this one. Okay, so how do they ask questions on this is, they will say that x is a Poisson random variable, and then they will say what is the probability that x will take the value I. But in this case here, you should remember that they should always give you the parameter lambda. See, whenever they are asking about questions on this binomial random variable, they should give you the parameters n and p. But then here we need only one parameter, which is lambda. Okay, remember this formula. What is it? P of x equal to I is equal to e power minus lambda into lambda power I by I factorial. And again, as with all the other random variables that we have seen till now, we can show that sum of all these probabilities is going to produce a value of 1. If you want to see it, just check this one. Sigma, I am just adding it up. Sigma I equal to 0 to infinity, P of x equal to I is equal to sigma I equal to 0 to infinity e power minus lambda into lambda power I by I factorial. Now this term is completely independent of I, so you can bring it out of the summation. Therefore it is going to be e power minus lambda into sigma I equal to 0 to infinity lambda power I by I factorial, right? So from series and sequences, you can find out that this particular expansion, this particular term is actually expansion of the term e power lambda, which means this is going to be e power minus lambda into e power lambda. This one, if you want to know it, you please refer to any book on series and sequences, which we don't have in syllabus for GATE, but then I think that is one of the subjects in the engineering course. But anyway, you will not get any questions on that because we don't have that one in GATE syllabus. Okay, so you just remember that the expansion of this term is e power lambda, so which is nothing but 1. Got it? So what is the main advantage of this Poisson random variable is it can be used to approximate binomial random variable in some cases. So it is very important, you write down as a note. The note is Poisson random variable can be used to approximate binomial binomial random variable whenever, okay, see this, whenever n is very high and p is very small, then we can use Poisson random variable with lambda to approximate this, which means if you are talking, if you want to find out the probability that a binomial variable will take a value having parameters n and p, instead of that you can find out the probability that Poisson random variable will take that value with parameter lambda in such a way that lambda equal to np. Both the values will be approximately same. Are you getting this? See, if you have framed a question and if you are solving it using binomial that random variable using parameters n and p, and in that example you found out that parameter n is very large and p is very small, then instead of using that binomial expansion formula, you can even use this formula, right? If you are talking about p of x equal to I, instead of using nci into p power I into n minus that 1 minus p power n minus 1 n minus I, instead of using that formula you can use this formula where you can substitute in place of lambda n and p, right? Therefore binomial random variable can be approximated using Poisson random variable. You can get the proof if you want, but then it is not required. Just remember this point. The important point about Poisson random variable is it can be used to approximate binomial random variable. We shall see some questions on it, you will understand. See this example on Poisson distribution. Suppose that the number of typographical errors on a single page of this book has a Poisson distribution with lambda equal to 1. Calculate the probability that there is at least one error on this page. So in this question what they are exactly asking is they have given that it is a Poisson distribution, whatever they are talking about, and whenever they talk about Poisson distribution they are supposed to give one parameter which is lambda. Therefore lambda is given. Now the question is, suppose that number of typographical errors on a single page of the book has a Poisson distribution, which means they are talking about the number of errors on a page of the book. So which means if you want to find out the probability that there will be exactly 2 errors on the page, then they are saying that it is given by the Poisson distribution with lambda equal to 1. What is Poisson distribution? E power minus lambda into lambda power I by I factorial, right? This is Poisson distribution. Now if you want to find out what happens for x equal to 2, if you want to find out that the number of errors on that page is exactly 2, then you are supposed to use this formula, right? And in place of lambda you are supposed to put 1 because lambda is given as 1, right? And in place of I you are supposed to put 2 divided by 2 factorial in case if you want exactly 2 errors, but that is not what they are asking. Calculate the probability that there is at least one error, which means they are asking about this. What is the probability that there is exactly one error? What is the probability that there is exactly 2 errors? What is the probability that there are exactly 3 errors, plus so on infinity. Now we know that we have already seen that probability, all the probabilities put together is equal to 1. For any random variable it is true, isn't it? For any discrete random variable. Now they are asking about this part. Now how can you write it? Probability of getting exactly one error is nothing but probability that random variable will take, at least one error is nothing but probability that it will take greater than or equal to 1. Probability that x is greater than or equal to 1 is equal to 1 minus probability that x equal to 0, right? Now you just substitute in the formula 1 minus, what is this formula? E power minus lambda into lambda power I by I factorial. It is given that lambda equal to 1 and I equal to 0 here, that equal to 1 minus e power minus 1 into lambda power 0 divided by 0 factorial. So it is simply 1 minus 1 by e. This is the answer, right? So this is the probability with which they are talking, there will be at least one error on the page. Got it? What is the probability with which there will be no error? That is nothing but p of x equal to 0, right? So p of x equal to 0 is nothing but e power minus 1, right, which is 1 by e. This is the probability that there will be no errors, and this is the probability that there is exactly one error. And also you can see that if you add these two, you are going to get 1, because they are exactly mutually disjoint events, and also all the events are covered. That is why we get that. Okay, so anyway, such questions will be asked on this Poisson distribution. Okay, if the number of accidents occurring on a highway each day is a Poisson random variable with parameter lambda equal to 3, then what is the probability that no accidents occur today? Which means they are saying that if you try to find out the number of accidents that will occur on a highway, let's say we denote it with a random variable capital X, then the probability that there will be I accidents on the highway is given by this distribution, Poisson distribution, which means it is given by e power minus 3 into 3 power minus I divided by I factorial, right? So this is the probability with which there will be I accidents on the main road. So how did I get this? In the formula of Poisson distribution, which is e power minus lambda into lambda power I factorial, lambda power I by I factorial, I have just written this. Okay, so in place of lambda I substituted 3. Now they are asking that what is the probability that no accidents will occur today, which means what is the probability that number of accidents is equal to 0, which is equal to e power minus 3 into 3 power 0 divided by 0 factorial, which is e power minus 3, 1 by e cube. What about if the question is what is the probability that there will be exactly one accident today? So x equal to 1 equal to e power minus 3 into 3 power 1 by 1 factorial, which will be 3 by e cube, right? So what is the probability that, I'm just writing them, okay, just for your understanding, that the number of accidents will be at least 1. Then probability that number of accidents will be at least 1 is equal to probability that number of accidents on the highway is at least 1, which means p of x greater than or equal to 1 is equal to 1 minus probability that number of accidents are going to be 0, right? So which is equal to 1 minus 1 by e cube, right? So this is the probability with which there will be at least one accident. This is the probability with which there will be exactly 0 accidents, probability with which there will be exactly one accident, right? So that is how we can answer them. Okay, let's see a new type of random variables. Till now we have seen one class of random variables which are called as discrete random variables, and in those discrete random variables we are able to discuss about what is the probability that a random variable can take exactly a particular value. For example, while rolling two dice, you can talk about what is the probability that the sum of two dice is going to be exactly 3. If x is a random variable, discrete random variable denoting the sum of two dice when I roll them, then what is the probability that the sum happens to be exactly 3? For this we are able to derive the probability. What are the events that will be covered in this? One is 1 2, other is 2 1, and the probability of this one is 1 by 36 and probability of this one is 1 by 36. When I add them up, it is going to be 2 by 36. Therefore the main difference between a discrete random variable and a continuous random variable is, in discrete random variable we'll have some countable number of values which our random variable x can take on. Are you getting this? We will have a countable set from which our x can take on. For example, in this one our x can take on values from 2 3 4 so on 12, countable set, right? We'll have some countable values, and then for these elements in this set we'll have some particular probability which is greater than 0. Got it? But then there will be certain kind of experiments which cannot be solved or which cannot be expressed using discrete random variables, and such experiments, in such experiments we use continuous random variables. To give you an example, let's say there is an archaeological department, and in their diggings they found out that they found out an object. Let us say they found out a pot, and now based on the properties or based on the characteristics of the pot, the chemistry or whatever, based on the properties of the pot, archaeologist has to determine when is this pot exactly made. Now in such an experiment, if you assume that capital X is a random variable which will give us the age of the pot, then this particular value X will not be able to take exact point in the time. Are you getting this? See, while digging up while if you found out an object, and you cannot, there is no way that you can say exact date on which it is made, but then what you can say is a period. Let us say they will say that this pot might have been made during 1852, maybe 1865, something like this. But then if you ask them what is the probability that it is made exactly in the year 1850, they will not be able to say it. But for a range they'll be able to say it, which means if our random variable is not going to take discrete values, if it is going to take a continuous range which is uncountable, then in that case our random variable has to be continuous random variable. Got it? So what is the difference between a discrete random variable and continuous random variable? In discrete random variable, we'll be able to, our random variable will be able to take up some points in a countable set. But in continuous random variable, our random variable will not be able to take any point, it will be able to take a range, right? We talk about a range, and in fact the number of values that our random variable can take is uncountable. In discrete it is countable, and in continuous it is uncountable. If you want one more example, maybe if you are conducting an experiment to find out what could be the lifetime of a car, then you will not be able to say that it is exactly 2 years or it is exactly 3 years, but then the probability that it is going to be between 2 and 3, you can be able to say it, right? So coming to these continuous random variables, we will not be exactly interested in a point, we will be interested in a range, right? Therefore if you have a period of time, right, so if you are trying to find out the probability that the lifetime of a car is this point, you will get it as 0. But then if you try to find out the probability that the lifetime of a car is from here to here, yes, you will be able to find out using the continuous random variables. The same as that archaeological department and our object, the same experiment. Likewise, we can perform many experiments in which we will not be able to find out the probability that a random variable will be able to take a point, but then we will be able to find out the probability that will be able to take the period. Now just see the definition. Let capital X is a continuous random variable if the set of possible values it could take is uncountable, like that. Uncountable means if you are trying to find out when an object is made, then the set of values that our random variable can take is minus infinity to present day, isn't it? Whatever today is. If you found out an object today, and if you are trying to guess what is the period that it is made, it can be anywhere from minus infinity to present day, isn't it? And how many elements are there? Uncountable, right? Just in a set 0, 1, you have uncountable number of numbers, right? So about countable and uncountable, you please watch TOC videos with that. There we have exactly discussed about it. Okay, so first thing is, if you have to have a continuous random variable, then the number of values it should take is going to be uncountable. In case if it is going to be countable, then it is discrete. Okay, and the second one is, and there exists a non-negative function called f of x, called the probability density function, having the property that for any set capital B of real numbers, probability that our random variable belongs to that set is given by integration of that particular function. So what is the meaning of it is, if you are defining a continuous random variable, then you should also define a function, right? And the function should be like this. Let us say this is x, and our function, let us say a function is defined like this. And now if you are interested in finding out what is the probability that our random variable has taken a value between a and b, then you have to find out what is the area under that curve between the points a and b, right? This particular area, and this particular area is going to give us the probability with which our random variable x will take any value between a and b. This is f of x. Alright, so what I mean by this is, if you are interested in finding out the probability that a random variable will take certain value between a range, then you are supposed to have a function for every continuous random variable. A function should be defined that is called as probability density function, and once you know the probability density function, the probability that our random variable, that our continuous random variable for which this function is defined, can take the value between a and b is equal to the area under this curve, and we know that the area under this curve is given by integration of the curve, right? So later in integration we shall again see how to integrate, what is definite integrals and how to integrate it, but I assume that you know the basics of this integration, so I am directly writing it here. Here we are not going to have complex functions, they will be very simple. You need not again go to the integration topic and see it. You can directly do them, they will be very simple. I'll just show you how we can use this function f of x. So let us say we have defined a random variable capital X, and then a function f of x is defined for that. Now if you are interested in finding out the probability that our random variable will take a value from a to b, right, probability that our random variable capital X can take a value between a and b is given by integral a to b f of x dx, where f of x is probability density function. Are you getting this? The probability that our random variable capital X can take on a value between small a and small b, this range is nothing but area under the curve f of x. And how do we get the area under the curve? It is nothing but integration between these two values, right? Now let us say you are interested in finding out the probability that our random variable will take a value less than or equal to a. Then how can you find out? So you have to find out the probability, which is nothing but the area under this curve, less than or equal to a, which means everything less than or equal to a. That is nothing but area under the curve f of x from the point minus infinity to a. Got it? Now interestingly, since it is the area under a curve, what happens is, if you try to find out the exact probability that a continuous random variable will take a value a, some particular value a, is nothing but area under the curve between this range, and the range is from a to a, isn't it? Which means you have to integrate like this, from a to a f of x dx, right? So what does it mean? You have a curve like this, and now from a to a is nothing but this one. So you are interested in finding out the area of this part. Now if you see this, it is nothing but a kind of rectangle, and for a rectangle the area is nothing but breadth into height, and height we know it, right? It is nothing but f of a, but if you see the breadth, it is nothing but 0, therefore area is 0. So what does it mean? Using this formula, generally this is the formula which we use for any continuous random variable. If you try to find out the probability that a random variable is going to take exactly a particular point, it is always going to be 0. But in case of discrete random variables, the probability that a random variable takes on a value might sometimes be non-zero. For example, in case of rolling two dice, what is the probability that the sum of the two dice is going to be 3? It is actually 2 by 36, right? So like that, we know in some of the problems in discrete random variables, we have the positive probability that a random variable can take a point, but in continuous random variable it is always going to be 0 for a point. And also you can understand one thing, the total probability, the total area under the curve is always going to be 1. That is what we have already seen, right? So for any random variable, the total probability has to be 1, which means if you try to find out minus infinity to infinity f of x dx, this should always be equal to 1. So these are the properties any random variable, any continuous random variable should satisfy. And then based on the exact function f of x, depending on what f of x is, we can again classify the random variables into various types. Now we shall see what are the different types of continuous random variables. Till now whatever we have seen is what are the different types of discrete random variables which are exactly in GATE syllabus. I have discussed only few of them which are exactly required for GATE syllabus. Not everything is required. So now we shall see what are the continuous random variables which are in GATE syllabus only. Even though we have a lot of continuous random variables, I'll be taking only the part which is present in the GATE syllabus. If you are interested in knowing everything, you can read various books. Every textbook, almost every textbook on probability will have them. Okay. Now see this uniform random variable. Let capital X is a random variable. Okay, so first of all you understand what is meant by uniform. So this one is one of the types of continuous random variable, which means we are going to have, or this particular random variable is going to take on a set of uncountable values. So it is not going to be a countable set, it can take uncountable values, that is for sure. And the second thing is it is uniform, which means if you see this probability density function, it is going to look like a straight line. It is going to be uniform forever, right, or wherever it is defined. Now see this, capital X is a uniform random variable on the interval alpha comma beta if its probability density function is given by f of x equal to 1 by beta minus alpha if alpha is less than beta, alpha is less than x less than beta. So what they mean by this one is, if you see the uniform, this probability density function, let us say this is alpha and this is beta, and this particular value is 1 by alpha beta minus alpha. Okay, and now our random variable will be 0 till this part, and between alpha and beta our random variable will take uniform, which means it will continuously be 1 by beta minus alpha. So between these 2 points it will be uniform, and for all the other points it is 0. Got it? So then such a random variable is called uniform random variable. Remember, we are going to classify the random variables based on what is its probability density function or what is the probability mass function in case it is a discrete random variable. In case of continuous random variable, we'll just see what is its probability density function, and then we decide whether it is uniform or some other type. Got it? Now why is the name uniform given? If you observe it, see this one, it is exactly uniform here, right? It is not changing, and in the other part it is changing. Got it? And now how to find out the probability of a particular interval in this particular interval alpha comma beta? Just see that one, or let's see whether it is for satisfying that property that the sum of everything is going to be 1. So if you try to find out the entire probability of this random variable from minus infinity to infinity, anyway from minus infinity to this one, so how to find out the probability? There are actually 3 periods here. One period is minus infinity to alpha, and other period is alpha to beta, and the other period is beta to infinity. So we have these 3 periods defined, or these we can divide this entire total period from minus infinity to infinity into these 3 periods. Now let's try to find out what will be the probability in each of these areas. From minus infinity to alpha, the probability given is 0, which means for this part the probability is 0. From alpha to beta, the total probability of this random variable is going to be this area. Now what is the area? If you look at it, it's looking like some kind of rectangle, isn't it? And for this rectangle, clearly the height is 1 by beta minus alpha, and the breadth is beta minus alpha. So we know that for a rectangle the area is equal to length into breadth, so which means if you have to multiply these two, so length is 1 by beta minus alpha, and then breadth is beta minus alpha. And for this one it is 0 again, because after beta it is not defined, it is given as 0, right? It is defined and it is given as 0. See this, for only between alpha and beta the value is 1 by beta minus alpha. For all the other values it is actually 0. Therefore if you see this, if you sum all these terms, this one is going to be 1, this probability is 1. Or if you want to see it from other way, using this formula itself, now I told you that from minus infinity to infinity f of x dx has to be always equal to 1, right? Now let's see if it is true or not here. So I can write it as if it is from minus infinity to alpha f of x dx plus alpha to beta f of x dx plus beta to infinity f of x dx. Now this one is 0. Why? Because from minus infinity to alpha it falls in this case, it is given as 0. And also this one is 0 because from beta to alpha it falls again in otherwise, which means 0. And for this part the integration is going to be alpha to beta 1 by beta minus alpha dx, and this is it is a constant which is independent of x, so we can get it outside the integration. So what do we get? 1 by beta minus alpha to beta dx. What does it mean? It is x, alpha to beta minus alpha, which is nothing but beta minus alpha by beta minus alpha, upper bound minus lower bound, right? Beta minus alpha, which is again 1, so it is 1. So that is the meaning of it. So why do we choose exactly 1 by beta minus alpha is, we have chosen this particular value so that this particular rule will be satisfied. What is the rule? Sum of all probabilities should always be equal to 1. For that particular rule we are going to use it. Why is it called uniform? Is in this particular range it is continuously the same value. Why only this particular value? Because if I take that particular value, then only I'll get this sum as 1. If I take any other value, this sum will not be 1. That is why this particular value. Now if you want to define a uniform random variable between the range 2, 4, then what should you do? See this, from 2 to 4 if you want to define, right? Now you have to find out what is 4 minus 2, which is 1 minus 4 minus 2, you have to find it out. So which is nothing but 1 by 2, which is 0.5, right? Therefore between this range you see that the value of f of x is 0.5. So let us say this is 0.5. Then for this range we are going to have this, and for the remaining we are going to have 0. Therefore even if you apply the total probability this like this, you are going to get 1 as the output. Therefore if you want to define a new random variable between uniform continuous random variable between 2 and 4, then you should have f of x equal to 1 by 4 minus 2 for the range 2 less than x less than 4 and 0 otherwise, right? And so you will get a function looking like this, and even if you try to find out the total probability, you are going to end up getting 1. Got it? So this is how uniform random variable is actually defined. So let's see some problems on it, you will understand better. See this one. If capital X is uniformly distributed over 0, 10, calculate the probability that x is less than 3, x is greater than 7 and 1 less than x less than 6. So if you observe this, they are saying that it is a uniform distribution. Therefore, you should be able to find out its probability density function. Let us call it f of x. Now f of x equal to, I told you that in case if it is defined between the range alpha comma beta, right, then the value of this is going to be 1 by beta minus alpha. In this case it is defined between 0 and 10. Therefore the value is going to be 1 by 10 minus 0 for the range 0 to 10, and otherwise it is 0. Got it? So now what does it mean? For the values from 0 to 10, this is going to be 1 by 10, which means 0.1, otherwise it is going to be 0. Now after drawing this one, you can easily guess what is that they are asking. They are asking about x less than 3, so 3 will be somewhere here. X less than 3 means from here to here, right? So the area under the curve from here to minus infinity, but from minus infinity to 0 there is nothing, so you need not count it, so you have to count this part. So what is it? 0 to 3. So what is the length? The length is going to be 1 by 10. And what is the breadth? The breadth is going to be 3, isn't it? 3 minus 0 is 3. Therefore, the probability of question A is 3 by 10. What about x greater than 7? Which means they are talking about this from 7 to infinity. Which means you have to talk about 7 to 10 and then 10 to infinity, right? Now in this case, what is the length? Length is 1 by 10, and what is the breadth? This value is again 3, which means both are same. This probability and this probability both are same because the areas are same. And the next one is from 1 to 6, isn't it? From 1 to 6 they are asking. In that case, what is the length? It is 1 by 10. And what is the breadth? From 1 to 6 I think it is going to be 5. 6 minus 1 is 5, which means 1 by 2 is the probability. 3 by 10, 3 by 10 and 1 by 2 is the answer. Or if you want to do it from the other way, so what is the other way? We are going to apply integration from minus infinity to 3, right, f of x dx, right? So which is nothing but minus infinity to 3. I am solving question number A, right? Probability that it is less than 3. Less than 3 means minus infinity to 3, right? So from minus infinity to 0, we know that it is again 0. Therefore I can actually count it from 0 to 3. F of x is 1 by 10 dx. Now which is nothing but I can pull out 1 by 10 outside, and integral dx is x itself. And what are the bounds? The upper bound is 0 and lower bound is 3. Now if you substitute it is again going to be 3 by 10. Likewise you can solve B and C also, right? So in uniform distribution, the only thing you should be able to find out is what is the probability density function. Once you find out, everything is straightforward. It is just finding out the areas of the rectangles, right? How to find out the length, we know that, and how to find out the breadth, that depends on the area that they are talking about. That is why there will not be any difficult questions asked on this one. Okay. Now let's see this exponential random variable. A continuous random variable whose probability density function is given by for some value lambda greater than 0, which means lambda is a parameter here, and in the question they are supposed to give us the value of lambda as well, right? Without this lambda we will not be able to find out. So in case if they have given this lambda, then its probability density function is lambda into e power minus lambda x if x is greater than or equal to 0, 0 if x is less than 0, which means it is defined only from 0 to infinity. For the values which are less than 0, this probability is 0. Got it? So what you should be knowing here is this formula. You should by heart all these formulas. Now I have given you what is the formula for uniform random variable. That is, I think, easy to remember, right? Given the range you can derive it, right? And here also you should remember this formula. Now, once you remember this formula, there is nothing much to this, only integration problems will be there. So even though this is probability question, mainly you should know how to integrate that one. Again, how to integrate this one we shall see in integrations. Okay, so it is very simple only. Now what are the questions they might ask you on such a topic is, they will ask you, okay, one more thing that you should be knowing is since it is a probability density function, we know that from minus infinity to infinity, if I try to integrate this e power minus lambda x, it should be 0, right? Later, after finishing our integration topic, you can again cross verify it. You can integrate it over the definite integrals minus infinity to infinity, and you can see that, okay, this is 1, sum is going to be 1, sorry, not 0. Got it? So this one has to be followed, and it will definitely be followed. And the second thing is, second kind of questions they will ask you on this one is, what is the probability that our exponential random variable will take a value between a range a to b, which means they might ask you something like this: what is the probability that our random variable a will take a value which lies between random variable x will take a value which lies between a and b. They'll ask you something like this. Then you are supposed to integrate it, definite integrals, a to b lambda into e of minus lambda x. So you should remember this one. So once you remember it, it will be easy. Got it? So that is what is about exponential random variables. Again, we shall see all these random variables together when we are talking about the mean or expectation. For now, we shall just focus on simple questions on this, and simple questions on this will be asked like this, and which can be solved if you know how to integrate it. And integration, we shall see in integration. Okay, I'm not going to extend this topic bit. Later I'll explain it in detail when we talk about expectations or mean. Later we shall see it. Okay. Now let's look at one other type of continuous random variable. It is called as normal random variable, and in this topic you have to by heart it, in the sense you have to see what is the density function, probability density function. You have to by heart it. There is no other way. Probably this is the only topic in which you might have to by heart some things, and there is no shortcut to remember it. Okay, and the formula is not very small, it is somewhat big. See this? So we say that a continuous random variable capital X is a normal random variable, or capital X is normally distributed with parameters mu and sigma square if the density of X is given by, which means this is the probability density function. If you see that f of x is given by this function, then we can say that that particular variable is normal random variable. So there are no questions that are being asked on this till now, but in case if they ask, they might ask you the question about what is the distribution function, right? The density function. See this: 1 by square root of 2 pi into sigma multiplied with e power minus x minus mu square divided by 2 sigma square. This is somewhat difficult to remember, but you have to do it anyway. Okay, and don't take any risk. They didn't ask anything like that. They might ask you. And whenever we are talking about these random variables, we have always been speaking about some parameters like np or lambda, right? And in this case, we are talking about mu and sigma. So why all these parameters are important is, later when I talk about expectation is a special topic, and when I talk about expectation, I will explain you why these various parameters are important. But remember here, the parameters that are important here are mu and sigma square. And if you want to see this function visually as a graph, you will see that it is actually a kind of bell. It looks like a bell. Okay, so people call it a bell function also. And if you see this bell is symmetric over this parameter mu, right? So if you think that this is parameter mu, this bell is actually symmetric, so on both the sides it will be same, right? So what is this mu and what is the significance of it, I'll tell you later. I'll tell you when we talk about expectations. Okay, so just remember this formula and remember that it is distributed like this, and it is having a parameter mu, and it is symmetric across the mu. Okay, we see more about it later. Okay, so as with any probability mass function or probability density function, if you add up all the values, all the probabilities, you are supposed to get 1, which means in this case integral minus infinity to infinity f of x dx. In this f of x, you substitute this entire formula, right? If you substitute this, you are supposed to get 1. And also, if you want to find out the probability that x takes a value in the range, this is a continuous random variable. Therefore, if it is given that it is a normal random variable, and if they are asking about probability at a point, it will never exist. Probability at a point will be 0, but probability in a range it will exist. Let us say this is a point A and this is a point B. Now if they want to find out, or if they are asking what is the probability that this particular normal random variable is going to take a value or will take a value between A and B, that one you can say, right? So how can you say it? It is nothing but the area under the curve. So if you want to derive it, it is nothing but integral A to B f of x dx, right? If the question is like this, so they don't ask such questions because integrating this function is not very simple. That is why they don't ask such questions. But in case if they ask, they might ask you the formulas. That is why I'm just giving the formulas. Okay, probability that capital X will take a value which is less than or equal to A is nothing but, so if they are talking about less than or equal to A, we have to go from minus infinity to A and integrate it, just like how we did for all the other functions, right? And similarly they might ask what is the probability that X is greater than or equal to A, then you have to start from A and go till infinity f of x dx, right? So actually this function is defined for minus infinity to plus infinity. That is why I am not dividing it into range. It is not like it is defined only for positive numbers. Got it? So all these things, if you can remember, you can answer any question on this, right? So later I'll talk about more properties about this. Okay, let's see this concept called as expectation or mean. The initial when they invented this concept for the first time, they did it so that when they conduct an experiment, they wanted to know which value is most probably the one to come out. See, what I mean to say is, let us say you have an experiment and you are conducting it, random experiment, and now even before the experiment is conducted, if you want to guess which value is having the highest possibility to come out, in order to know that, they have invented this concept. But then later what happened is, in many of the cases this concept will not be so much useful to guess it, because in most of the cases all the outputs will be equally likely. But anyway, knowing this concept will be useful in some of the experiments for sure. Okay, now what I'll do is, I'll take an experiment and I'll explain you this concept. Later I'll discuss about the exact formula and how to apply it in the case of discrete and in the case of continuous random variables. First I'll take an example on discrete example. Okay, discrete random variable. Assume that x is a discrete random variable which denotes the number of heads that might come up while flipping two coins. Okay, so what are the various possibilities? So one is, I might get x equal to 0, which means I might not get any head. So what is the probability that x will take a value 0? The probability that x will take a 0, or I'll do it in another way. Let me write it in a table. Okay, now this is the random variable x and it is the probability that x will take some value. Now when I am flipping two coins, what are the various possible values that I might get for x? So when I flip two coins, both the coins might get a head, or one of them might get a head, or 0, which means x might take 0, or x might take 1, or x might take 2, right? So when I flip two coins, I might not get any head at all, or when I flip two coins, I might get only one head, or when I flip two coins, I might get two heads, right? Now how does this event look like? This is nothing but the event of getting two tails. This is nothing but the two events getting first tail and head, or first head and then tail. This is nothing but getting head and head, right? Therefore, what is the probability of each one? The probability of getting 0 is nothing but 1 by 4, and the probability of getting this one is nothing but 2 by 4, or it is 1 by 2, and the probability of getting a 2 is 1 by 4. I hope you know how I'm writing this, isn't it? In the sample space we have totally 4 elements, and each element can take 1 by 4, and since this is taking 2 elements, it is going to have 2 by 4 as the probability. Now if I multiply them and add them, right, which means if I apply this sigma I into probability that x will take a value I, if I multiply this value with this value and I add them all, right, for all I such that p of I is greater than 0, which means for all values if we take this, then that is called as expectation. So in this case, what is the expectation of this discrete random variable is 0 into 1 by 4 plus 1 into 2 by 4 plus 2 into 1 by 4, right? Now just check this. It is nothing but 0. This is 2 by 4. This is again 2 by 4, isn't it? 2 by 4 plus 2 by 4, which is nothing but 1. Alright. So what does this one show? This one is showing that when you are the expectation of this random variable x is going to be 1, which means even before conducting the experiment we can guess that there are more chances that you might get a value of 1 if you conduct this experiment. And in this case it is of course true, isn't it? If you check it, the probability of getting a 1 is high compared to probability of getting a 0 or probability of getting a 2, isn't it? Here it is 1 by 4, here it is 1 by 4, here it is 2 by 4. That is why we got the expectation 1. So that is why it is useful. So what does expectation of a random variable give? What is the maximum probability that it will get some value, or what is the, if you conduct the experiment, what is the value that you might expect, or what is the value that might come up with a higher probability. It is true in some cases, but in some other cases, even though we get some value, it is not true that that value of that, the probability of that value is high. Therefore, even though it is useful in some experiments, it might not be useful in some other experiments. Let's see this. Let us assume that capital X is a random variable, discrete random variable, which denotes the number when I roll a dice. Okay, if I roll a die, then what are the numbers that might come up? The numbers that might come up is 1 or 2 or 3 or 4 or 5 or 6. What is the probability that X will get these numbers? The probability is 1 by 6, 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 1 by 6. Then what is the expectation of X? It is also represented like this, expectation of X, right? Expectation of X is equal to sigma I into P of X equal to I, which means I have to multiply these corresponding values and I have to add them up. Now what is it? It is 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. I think you understood how I am writing this. When I multiply these two, these two, these two, these two, for all of them the denominator is 6. That is why I am writing 6 there. Now this is nothing but sum of first 6 natural numbers, right? So what is the formula? 6 into 6 plus 1 by 2 into 6. So it is going to be roughly 3.5. Now it is saying that when you roll a die, the number that will come up will be close to 3.5, which means it will be either 3 or 4 with high probability. But then if you observe this one, all of them are equally probable. That is why we cannot say that exactly. So people have stopped saying it. Got it? So expectation has nothing to do with what comes up on the in the experiment in most of the cases. In some of the cases it will give you what is the highly likely event that will come up. Otherwise, in most of the cases it will not give you. It is actually depending on the experiment as well. Got it? So what I'll do is, so what is important for gate here is, once you know how to find out the expectation this way, there are two types of random variables. One is discrete random variables and other is continuous random variables. So what I'll do is, in exam they will ask you what is the expectation of this, what is the expectation of that, like that. Okay, so what I'll do is, I'll derive for every case what is the expectation of that random variable. You just see the derivation, don't by heart it, but if you want to remember, just remember the final answer, right? So in every case I'll give you what is the expectation of Bernoulli random variable, binomial random variable, or normal random variable. I'll give you what is the expectation of each one, Don't by heart them, but then by heart the final answer. The proof is not required, but still, just for the sake of understanding, I'll give you the proof to understand how they are actually derived. So once you understand all the derivations, in case if they ask you about a completely new random variable, if they define it in the exam and if they ask you expectation, you will be able to do that. But proofs are not required, just the values are required. You by heart the values, just see the proof. Okay, fine. Now let's see the discrete case in which we shall see all the discrete random variables we have seen till now. First one is Bernoulli random variable. We know that in a Bernoulli experiment, the random variable will take two values. One is 0 and the other one is 1. And 0 denotes the probability of 0 is nothing but a failure and 1 is nothing but a success. And let us assume that the parameter p is given. What is the parameter p in Bernoulli experiment? I already told you that it is nothing but the probability of the success, which means it is the probability with which the variable will take a value 1, right? Now say this. So we know that Bernoulli random variable will take two values. Either it will take a value 0 or it will take a value 1. 0 means failure and 1 means success, right? Now probability of x. Now we know that since the parameter is given as p, the probability of success is nothing but x taking the value 1, which is equal to p, and the probability of failure is nothing but x taking a value 0, which is nothing but 1 minus p, right? And the same thing in every case. Whenever you are talking about the discrete case, you have to multiply the corresponding values and you have to sum them up. So in order to find out its expectation of x is equal to, you have to multiply them and sum them up. Now just multiply them and sum them up. 0 into this and 1 into this, which is nothing but p. Now what does it mean? Expectation of x is equal to p, right? So there are some applications, especially on this Bernoulli random variable. Now one other way of understanding this expectation is, you can think of it like this: the expected number of successes in one trial is equal to p. So expectation of x equal to p means, you can note it down, the expected number of successes that can happen in one trial. One trial means when you do this one time. In one trial is p. Actually this is meaningless. The reason is, the number of success should be a number, right? Natural number, but p is a number which is between 0 and 1. Therefore it is actually meaningless. But you can understand it this way: in one trial, if you are going to get p successes, right, then how many trials will be required in order to get one success? Then for one success, how many trials are required? 1 by p trials. So this is the important one, right? Try to remember this. This is very, very important. They might ask you questions only on this. As of now, nothing else has been asked from any random variables. Only this one has been asked, and this is most popularly used in many of the other theories, which means in most of the applications of probability theory, we use this Bernoulli random variable and we use this formula. In order to get one success, we might have to perform 1 by p trials. The question might be like this: in a Bernoulli random experiment, they might say that the probability of success is 0.2. Then how many trials are required to get one success? Then it is nothing but 1 by 0.2, right? 10 by 2, which means 5 trials are required. Got it? In 5 trials you might get one success. It is not guaranteed, but it is theoretically, that is how you derive it. Theoretically, that is how you think of it. So the likeliness of this event is 1 in 5 times. If you conduct 5 times the experiment, you are supposed to get one success, right? So it is actually okay, fine. So instead of talking about here only, later I'll expand it to the next topic and I'll again talk about it. So in case if we conduct 10 experiments, then what happens? That is nothing but binomial, right? So I'll take binomial and then I'll show you the expectation, and then we shall again discuss there. In case if I do it for n times, then how many successes are expected? This is nothing but only when I try for one time, how many successes will come. That is what we got. From that I am trying to derive how many tries are required to get one success. Got it? But the next one is, if I try n times, out of these n times, how many successes will be there? That we shall discuss using binomial. Let me go to binomial, you'll understand it there. Okay. Now let's try to find out what is the expectation of binomial random variable. I hope you remember what is binomial random variable. If you are going to perform an experiment n times, what is the probability that the number of successes is going to be I, right? That will be given by binomial distribution. And this binomial random variable is nothing but the number of, this random variable will count the number of successes when I perform the experiment n times. In Bernoulli, it is nothing but when I do it one time, what is the probability of getting a success? That is given by Bernoulli, right? But here it is, if you are doing it n times, how many times you are going to get this success? That is being counted by the random variable x. Let us say here I am going to use the random variable name as x, and whenever I say any random variable, we are supposed to know what are the parameters, and here the parameters are n and p, where n is the number of trials I am going to use and p is the probability. N is the number of trials I am going to use and p is the probability, right? And also we know that the probability that the random variable capital X equal to I is nothing but, in out of n trials, how many times I am going to, what is the probability that I get exactly I successes. So out of n trials, how many times I can get I successes? It depends on NCI, which means out of all these n, any of these I choices, we have I experiments can be chosen to make them success. That is why NCI, and then for one of them, which means if it is going to be p successes and n minus I, or I successes and n minus I failures, then it is going to be p power I into 1 minus p power n minus I. This is the formula which we already know. This is the probability that the random variable x takes a value I. It is equal to NCI into p power I into 1 minus p power n minus I. Now what are the possible values for this I? We know that if you are going to perform the experiment n times, then the number of successes can be either 0 or 1 or 2, so on n, which means I can take a value from 0 to n. Got it? So now using this knowledge, we want to find out what could be the expectation. Now I told you that in case of discrete random variable, and in case this is a discrete random variable, one of the discrete random variables. Now in this case, we have to multiply the value with the probability, right? Every I has to be multiplied with p of I, and if I add them all, then I am going to get the expectation. Now see this. Expectation of this random variable is sigma I equal to 0 to n I into p of x equal to I. Now what is its value, and then what is the probability that this particular random variable x takes that value. See, I am going to explain you the proof. Proof is not required, but just for the sake of understanding I am doing it. In case if you don't understand it, leave it, but remember the final answer. In exam, final answer is useful. Okay, so now see this. But it doesn't mean that you stop the video now and just directly note down the answer. No, just watch it. It will be interesting. It might be useful for you in somewhere in some other subject also. See this. Sigma I equal to 0 to n I into p of x equal to I. We know that p of x equal to I is given by this formula. Just now I have shown you that. Now I is multiplied with this, and in this equation I am going to expand this term. This particular term NCI is nothing but n factorial. I is already there, that is why I am writing I from here to here, and then n is this formula is nothing but n factorial divided by n minus I factorial into I factorial, and this one is same. I have written, I didn't do anything much. And now if you observe it, here there is I and here there is I factorial. Now we can cancel out one of them, right? Which means if I cancel out this, I'll get I minus 1 factorial. That is what I did. I taken this I and cancelled out I from here. That is why I got I minus 1 factorial. Got it? And now I want to apply some modifications on this. I want to simplify it so that I can reduce it. So what I am trying to do is, from this n factorial, I'll pull out n. Since n is independent of I and sigma is based on I can pull it out, right? And similarly, from this p power I, I'll pull 1p out. Then what I get is, if I pull one n out, in place of n factorial I get n minus 1 factorial. And if I pull out 1p out, in place of p power I get p power I minus 1. I didn't do anything, simple things, okay? And the remaining I written it as it is, right? Now what I do is, see this, here there is I minus 1 and here there is I minus 1. Just to simplify it, I want to substitute, in place of I minus 1 I want to substitute k. Let I minus 1 equal to k or k equal to I minus 1. Then I want to modify all these terms, right? This term is not going to change if I substitute it. That is why I directly write it here. This term is not going to change because it does not contain any I. That is why I have written it as it is, n minus 1 factorial. And then this term n minus I, this is going to change, and I minus 1, this is going to change. What should be written in this I minus 1? I minus 1 is equal to k. Therefore, just write k factorial, which means this term. Okay, and here also I minus I is there, so just write k, right? And now what about these two terms, n minus I and n minus I? How to change these two terms? In place of I, you substitute k plus 1. In place of I, you substitute k plus 1. Then what do I get? N minus k minus 1. That I just write it as n minus 1 minus k. Why? I'll show you later. Are you getting this? In place of I, I'm substituting k plus 1. Now that is going to be n minus 1 minus k. Got it? And here also I get n minus 1 minus k, right? And now what about these bounds? How does this run from? Initially I was running from 1 to n. Then what will k run from? If you want to find out k, see this. K is nothing but I minus 1. Now when I is running from 1 to n, then what happens to k? In place of k, if you want to find the lower bound, where does k run from? You take the lower bound of I and you substitute here, which means if I substitute 1 here, I get 1 minus 1, which means 0, which means k will run from 0. And in place of upper bound, if you want to find the upper bound, you have to put n. And if I substitute n, I am going to get n minus 1, which means when I is running from 1 to n, k will run from 0 to n minus 1. That is why 0 to n minus 1. Now if you observe this one, if you observe this formula, how does it look like? This factor can be written as n minus 1 ck, isn't it? N minus 1 ck. N minus 1 ck. Why? Check this. N minus 1 ck is nothing but n minus 1 factorial divided by n minus 1 minus k factorial into k factorial, right? And then the remaining parts, this one is nothing but n minus 1 ck into p power k into 1 minus p power n minus 1 minus k. So this entire thing is nothing but in a kind of the formula of this one, isn't it? In place of n, we are going to have n minus 1. So if I write all the terms and if I add them, sum them up, it is nothing but it will form a plus b power n minus 1, where a is p and b is 1 minus p. So it is going to sum up to p plus 1 minus p power 1 plus p power n minus 1, which is going to be np. So that is how we can prove that the expectation of binomial random variable is np. Now what is the literal meaning of it? What is the meaning? What do you understand from it? It means that if the probability of single success is p, and if you are conducting n trials, then the number of successes you will get is going to be n into p. So how will the questions be asked on this? So they'll ask questions like this. See this. They'll say that we are conducting a Bernoulli experiment, or sorry, binomial experiment with parameters n equal to 10, with parameters n equal to 10 and the probability of success p equal to 0.6. Then what is the expected number of successes? They'll ask some question like this. Then what is the expected number of successes? You have to multiply these two, which is nothing but 6, which means if I perform 10 experiments and if the probability of success in each experiment is 0.6, then the number of successes we might get will be 6. Alright, so such kind of questions will be asked. So especially Bernoulli and this binomial, these two you are supposed to remember. In case of Bernoulli, the expectation is p, right? In that one, what the question will be asked is how many trials are required, what is the expected number of trials to get a success. That is nothing but 1 by p. And in this case, what is the number of success or expected number of successes we will get if you perform these many experiments with this probability? It is nothing but np. These two are the only questions which might be asked from this topic, even though we are going to discuss the complete, for all the random variables we'll see this topic expectation, but still these two are very important coming to gate. Okay, but then even though questions are not asked, we shall not skip those topics. So please don't skip those topics, they are not very important, but still don't take any risk. Okay, now see this. Calculate expectation of x if x is a Poisson random variable with parameter lambda. Again, this is a discrete random variable case, and also the parameter is given as lambda. And whenever we are talking about these distributions, parameters are important. Here the parameter is given as lambda. Now we are going to have the probability density function in terms of lambda. So we already know that formula anyway, right? So now what I'll try to do is I'll try to find the expectation using the discrete case. So what is it? We have to sum up all the products. What are the products? I into probability of I for every value of I possible, for which the probability of taking an I is greater than 0. So which means see this, sigma I to infinity, I equal to 0 to infinity, I into, this is the probability that x will take the value I, isn't it? So if you see this is the probability that the random value variable x will take the value I. So this one we have already seen, I just substituted it, and now we have to evaluate it and simplify it, right? So just see step by step what I am trying to do here. Now I is running from 0 to infinity. If you try to substitute I equal to 0 here, this entire thing is going to become 0, and so it is not useful, or it is not going to affect the sum. That is why you can just simply remove the term for which I equal to 0. So if you remove the term for which I equal to 0, then I should start from 1. That is why I is starting from 1 officially. So I have deleted whatever the term which is starting with 0. So the remaining is going to be I equal to 1 to infinity. So both are actually equal, because even if you include that I equal to 0 term, it is not going to change anything. That is why I am starting from I equal to 1, right? And now if you see in the numerator there is I, and in the denominator there is I factorial. So you can cancel out these two i's, then I get I minus 1 factorial in the denominator. Now I got I minus 1 factorial in the denominator, right? And now if you see in the numerator, there is a term e power minus lambda, and that is independent of I. So since it is independent of I, it does not play any role in the summation, so you can simply bring it out. Correct? So I am bringing out e power minus lambda, but I cannot bring out totally lambda power I, because it is dependent on I, and I cannot bring out I minus 1 factorial because it is dependent on I. Since for the summation it is running in terms of I, you cannot bring out any terms which are containing I. You can only bring the terms independent of I. So I'll explain the reason later, but for some reason I even want to bring out lambda. Now if I bring out 1 lambda and e power minus lambda, then I get e power minus lambda outside and then lambda outside, and what will remain here? Lambda power I minus 1. See this, lambda and e power minus lambda, I brought them outside. Now what is remaining here? Lambda power I minus 1 is remaining. Got it? Lambda power I minus 1 divided by I minus 1 factorial. I is running from 1 to infinity. Now in place of I minus 1, try to substitute k. Let k equal to I minus 1. In place of I minus 1, I am trying to substitute k. Got it? Now what happens is, see, since I is running from 1 to infinity, in place of I if you substitute 1, then k will be 0. Therefore k will run from 0 to infinity. Since I is running from 1 to infinity, in place of I if you substitute 1 here, k will run from 0 to infinity. That is why k will run from 0 to infinity, lambda power k divided by k factorial. Lambda power k divided by k factorial. Now if you try to expand that series, it is this one. If you try to expand this summation, this entire summation, only this summation I am talking about. If you try to expand this, it is going to look like this. Lambda power 0 by 0 factorial plus lambda power 1 by 1 factorial plus lambda power 2 by 2 factorial plus so on. Now this is nothing but in sequences and series, you will know that according to the sequence and series, this is the series expansion of e power lambda. So this entire thing is nothing but the series expansion of e power lambda. Therefore in place of this summation, I am writing e power lambda. Now what does it give you? Lambda into e power minus lambda into e power lambda. So finally you are going to get lambda. So that is why this parameter lambda is important. Got it? Therefore if it is given that it is a Poisson random variable, then the expectation is going to be lambda. Just remember that one. Okay, you need not remember whatever the entire proof we did. Just remember this fact that in case of Poisson distribution, it is going to be, expectation is going to be lambda. They might ask you some question about what is the expectation. Okay, now see this continuous case. Till now we have seen how we do with this discrete case. I have given you some examples also, but then for continuous case it is different. The reason is, in discrete case, we know exactly the probability that a random variable will take a value, but in continuous case we don't know that. See, in discrete case what we are trying to do is, we are trying to multiply I with the probability that x will take the value I, isn't it? In discrete case we can do this, because in discrete case this is how the probability is distributed. It is not going to be continuous. Only for discrete points the probability is going to be greater than 0. That is why I was able to do this. But then coming to continuous case, if you try to apply the same thing, I into p of x equal to I. Now for a given point, I told you that the continuous, for any continuous random variable, the probability that it will take a given point is 0, which means if I apply the same formula for continuous case, it is going to give me 0. The reason is, you will multiply I into probability that it will take I, which is 0. So if it's anything, if you take like that, everything is going to be 0 only. Got it? That is why we are going to use a different formula here. So the expectation, in order to find out the expectation, the expression that we should use is integral minus infinity to infinity x into f of x dx. So where f of x is the probability density function. Okay, see the definition. If capital X is the continuous random variable having a probability density function f of x, then the expected value of x is defined by integral minus infinity to infinity x into f of x dx. So how could questions be asked on this is, in exam they might define a new random variable which we have not seen, and then they'll say that it is a continuous random variable and they will give you what f of x is. Then they might ask you what is the expectation of this function, right? So it is a kind of question which is a combination of probability and integration. In order to solve this question, you are supposed to know integration, isn't it? It is actually an integration question, minus infinity to plus infinity x into f of x dx. Now what we shall do is, I'll try to derive this expectation for every, till now they didn't ask any question on this, but then in case they ask, that is what I am talking about. Now I'll try to derive expectation for all the random variables which are defined in which are given in the syllabus. I'll try to derive it. You need not by heart it or learn that, just see how I am trying to do it. But then again, same exactly like the discrete case, you have to remember the final result. They might ask that. As of now they didn't ask it, but still it is better that you know them. Okay, fine. Now let's see expectation of uniform random variable distributed over alpha, gamma, beta. So you know how does the uniform random variable look like? So if it is alpha and if it is beta, the probability that the random variable will take any value less than alpha will be 0, and from alpha to beta it will be constant, and then after beta it will be 0. And what will this value be? This value will be 1 by beta minus alpha. Since it is uniformly distributed across this interval, that is why it is called uniform random variable, and this is nothing but the probability density function. So the probability density function f of x is 1 by beta minus alpha if x lies between alpha and beta and it is 0 otherwise. Okay, now I'll be applying the same formula. What is the formula? In order to find the expectation, integral minus infinity to infinity x into f of x dx. But then if you observe it, from minus infinity till this point alpha, we don't have anything in f of x, right? Therefore even if you observe this term, it is going to be 0 because f of x is 0. So it is not worth writing minus infinity to alpha, so I can cut it off. And then from beta to infinity, again f of x is 0, therefore that part will also be 0, you can cut it off. So what will be remaining? Only the part from alpha to beta, which means from here to here the part will be remaining. Therefore expectation is nothing but integral alpha to beta x into 1 by beta minus alpha dx. See this. Therefore expectation of x is integral alpha to beta x into beta minus alpha dx. Now we know that this entire thing is constant, right? You need not do that, so you can take it out as well. Now integral x dx is nothing but x square by 2, simplest form, you know that. So it is nothing but x square by 2 into beta minus alpha. This beta minus alpha doesn't change because it is a constant, or it is independent of x. And now here the integral is definite integrals, and the definite integrals are having limits alpha and beta, right? So upper bound is beta and lower bound is alpha. So you are supposed to substitute upper bound minus lower bound. Now in place of x, if I put beta, it is going to be beta square, and if I put alpha, it is going to be alpha square. Therefore it is going to be beta square minus alpha square divided by 2 into beta minus alpha. So that will be beta plus alpha by 2. Got it? So what is the meaning of it? It says that if your probability is uniformly distributed, then the chances are maximum that x will take a value in the midpoint of the interval. That is what is they are saying. It is nothing but a kind of average. That is what is we got. Even though the probability that we get any point between x, alpha and beta are same, expectation is saying that the most expected value will be close to the middle, or it will be the center point. That is what we are getting from this formula, right? So in case if it is distributed between 1 and 2, then what will be the expectation? If it is uniformly distributed, 1.5. If it is distributed between 1 and 3, what will be the midpoint? 2. That is nothing but the expectation. So in this case, if you want to know what is the expectation, you are supposed to know the parameters alpha and beta. That is the interval in which it is uniformly distributed. Once you find out that interval, then the expectation is nothing but the middle value or the midpoint. Okay. Let's see the expectation of exponential random variable. Here, if x is exponential random variable distributed with parameter lambda, that is what we are going to take. So lambda is important. Lambda is the parameter here. Again, you need not by heart this proof. You can just remember the result. Now say this. In order to find out the expectation, in case of discrete we are using sigma, and in case of continuous we are using integration, right? So now integral 0 to infinity, which means it is valid from 0 to infinity. Since it can give any value between 0 to infinity, I am taking that range, integral 0 to infinity and x multiplied with the function, right? So what is f of x for this? F of x for this is lambda into e power minus lambda x. And now in order to integrate this, we are going to apply a formula called as integrating by parts. So what is integrating by part? We can see it in calculus. In calculus, I'll tell you how to divide it and integrate it. So using that integration by parts, I divide into two parts. Okay. So those two parts can be integrated separately, and once you integrate them, this is the answer we are going to get, 1 by lambda. So this is the proof. Anyway, you need not worry about it even if you don't understand, but what you should remember is the final one, right? So if the parameter is lambda, then it is going to be 1 by lambda. The questions in this may be like this: what is the expected? They'll say that lambda equal to something like 2, and they'll ask you what is the expected number, then it is 1 by 2, 0.5, right? Okay, now see this expectation of normal random variable. So let x be a normally distributed random variable with parameters mu and sigma square. So as you know, this normal random variable is having two parameters, mu and sigma square. Okay, and now in order to find out the expectation, we are going to do the integration as same, because since it is a continuous random variable, we are going to apply integration. In case if it is a discrete random variable, we would have applied summation. Now here expectation of x equal to, I am going to multiply, this is f of x with x, I am going to multiply with x this entire f of x, and whatever are constants I pull them outside, and I am applying integration from minus infinity to infinity, and the remaining steps whatever we are doing here is just to simplify the integration part and get the final answer. Anyway, you need not remember all this, just remember the final answer. But in case if you want to know how we got the answer, I am just giving you the procedure here. And coming to integration, you can learn about this integration when we talk about this in calculus integration. Okay, so here don't worry about the integration, just assume that it is possible to do it this way. Now see this expectation of x equal to, so what we are trying to do is, in place of x, wherever you see x, we are going to replace it with x minus mu plus mu. Now if you substitute x minus mu plus mu here, we get the same thing, x minus mu itself, right? And when we substitute x minus mu in this, we are going to get x minus mu. So why did we do this? So that we can split it into two parts, right? So observe this. So one thing is, we have in place of x, x minus mu plus mu is substituted. Here also it is same thing is substituted, but anyway we are going to get x minus mu itself, right? And here x minus mu plus mu is there, right? Because of that plus mu term, I get this entire term extra. And after we get this, in place of x minus mu, I am substituting y. So here I got y and then y, and here this entire part, if you observe it, it is simply f of x, right? So if you observe this entire part, it is simply f of x. F of x is nothing but the normal density function, isn't it? F of x, this entire part is nothing but the density function, and as you know, this density function is symmetric across y-axis. Therefore, when you integrate it from minus infinity to plus infinity, if you integrate it over the entire area, it is supposed to give you 0, because entire this part is going to give you a negative number, and this part is going to give you a positive number. Negative number plus positive number, which are same, because it is symmetrical, is going to give you 0. Therefore this entire part is going to become 0, right? And anyway, when you integrate it, yeah, by symmetry, the first part, this one is going to become 0. Okay, yeah, this is the second part, right? Yes, the second part is the normal distribution, and this one is going to become 0, and this one, when you integrate it, this one is going to become 1. Sorry, so when you count it all, it is going to become 1, and when you perform integration on this, since it is symmetrical over y-axis, it is going to give you a 0, right? And whatever you are going to get is mu. So whatever it is, finally what you should remember is the expectation of normal random variable is mu. So with this topic, we have finished with all the expectations. So coming to this random variables, they didn't mention about anything. They have just mentioned normal all the random variables. Now we have found out even the expectations of random variables. There is one more concept called as variance. So this variance is actually related to random variables, but it is specifically not mentioned in the syllabus. and even if you look at the previous gate question papers, it has not been asked even one time. Therefore we are not going to look into this variance because it is not mentioned and it is never asked, so we can leave it comfortably. And remaining things, sometimes questions may be asked on this. Coming to the expectations, just remember the final answer. Okay, fine. Now let's talk about mean, median and mode. So these three topics are actually related to statistics, not the things from probability, but then we don't have statistics specifically mentioned in the syllabus, but these three topics are included in the probability. Even if you look at the previous gate question papers, till now no question has been asked from this topic, but since they have mentioned it in the syllabus and it is a very small topic, let's finish it off. So it will not take a lot of time, you just watch it. Okay, so mean, median and mode, this is the topic. Mean, median and mode. So what is mean, median and mode is, all of them are some kind of averages. So if you have a collection of data, if you have certain readings, let us say you have conducted some experiment, and you have conducted the same experiment some 15 times, 20 times. Now you want to find out the average. Then there are various useful methods. One thing is, you might be interested in the average called mean. So I'll just take an example and explain it. Let us say when you conduct an experiment 5 times, the outputs turned out to be like this: 2, 3, let's say 1, 5, 4. Okay, now if this is the number of readings that you have collected, then what is mean is, you have to add all these readings and then divide it by the number of readings. So which means 2 plus 3 plus 1 plus 5 plus 4 divided by 5. That is the mean. Alright, and what is the median is? Median is, generally you are supposed to sort out the readings, and whichever value falls exactly in the middle, then that is called as median. So which means 1, 2, 3, 4, 5. Now we have sorted it out, and whichever falls in the middle, that is called as the median, which means in this case this one is called as the median. And the next one is mode. So mode means, if any value has appeared more than once, or most frequently occurring value is generally called as mode. For example, assume that we have 2 again here, we conducted 6 times. Let us say this is the 6 times we conducted the experiment, and these 2 are discussed for 5 times, which means for the first 5 values. But while coming to the mode, let us assume that we got this data. If this is the data, then what will be the mode is, if you try to put them together, 1, 2, 2, 3, 4, 5, you need not sort it actually, but then I am trying to sort it so that you will see some numbers repeating there. So 2 is repeated 2 times, so this is the reading which is most frequent among all the readings. Therefore mode is 2 in this case. Got it? So mean means sum them up and divide by the number of readings. Median means sort them out and take the middle value, and mode means you take the frequently occurring value. Got it? Now what we shall do is, we will take some examples and we will see what if there are 2 values in the middle, what if 2 values are repeating, 2 values are most frequent values. Like that, we shall see all the cases by taking some examples. Okay, now let's find the mean, median and mode for this. So let us say these are the readings we have, and for this I want to find out the mean. So in order to find out the mean, you are supposed to add them: 13 plus 14 plus 13 plus 16 plus 14 plus 21 plus 13 divided by, you have to add, you have to put the count: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and you are supposed to get something, answer like 15 or something, you just check it. And the next one is median. In order to find out the median, you have to sort out the numbers in any order, either in the ascending order or descending order. You are supposed to sort them out and then use the middle number as the median. Now if you see this, the smallest number is 13, and how many times 13 is repeated? 1 2 3 4 times. So 13 13 13 13, right? And the next smallest number is 14. How many times it is repeated? 1 2 14 and 14. And the next smallest number is 16, right? Only one time. And the next smallest number is 18, right? So anyway, since we have, I think I missed out one number, 13 14, yeah, 21 is there. After 18, 21 is there. Yeah, since we have 9 numbers in total, definitely the middle number will be the fifth one, isn't it? So 4 to the left, 4 to the right, and the middle number is here, right? Therefore median is 14. And let's talk about mode. In order to find out the mode, you are supposed to find out how many which numbers are most frequent here. Now if you observe this, 13 is most frequent. It occurred 4 times. Therefore mode is 13 for this case. Got it? So this is how we can solve them. Now we shall see what happens if it is even number of readings are there. Then we cannot find out exactly the middle one. And what happens if there is more than one number with the same with the higher frequency, or with the equal, if the numbers with the highest frequency are more than one, we have to discuss about that. Okay, we shall see that with the examples. Now let's consider the case when we have even number of readings. So even when it was odd number of readings, finding out the median was easy because there was only one median. But when we have even number of values, then we don't have any center point or the middle value, right? Instead we have two middle values, isn't it? See this, we have two middle values. That is why finding out the median in case of even number of readings is different from the earlier example where the number of readings were 9, odd number, right? So what we should do is let's find out everything. One is mean. So mean is going to be, you have to add them all 1 plus 2 plus 4 plus 7 and divide with the number 4. So it is going to be 3.5. And coming to median, you have to find out the middle value. In case if there is a middle value, you could find it out. See, in case if you would have had one more value like 9, then we sort them out and then find out the middle value. Always remember, we have to sort them out. Finding out the median, don't just jump and get the middle value right away. Sort them out either in the ascending order or descending order and then find out the middle value. Now in case if you would have had 5 readings, then definitely middle value is 4, and that has solved the problem. But since we have only 4 values, the middle value is not 4, right? So how can you solve it? Now we have 2 middle values, these 2 middle values. We have to take the average of those 2. 2 plus 4 by 2, which is 3. That is the median. Got it? Now how to work it out in general sense is, if the number of readings is n, okay, and if n is a odd number, n is an odd number, then you can find n by 2 and take the seal, right? Which means in case if it would have been 9 by 2 and take the seal, which is nothing but 4.5 seal, which is 5. So in case if you had 9 elements, then 5th element is the median, right? And what if n is odd? In case if the n is odd, then you are supposed to find out two values. What is the value at n by 2? See, after sorting we have to do this, okay? Find out what is the value is at n by 2 and also find out the value which is at n by 2 plus 1. These two values we have to find out average. This is the median in case if n is even. In case if n is odd, that is the median. In case if n is even, this is the median, right? And what about the mode? Mode is a number which has the reading which is occurring more frequently. But if you observe this, all the numbers are actually occurring at the same frequency, or all the numbers have exactly occurred once. So whenever there is only all the numbers have occurred only once, then we should say that there is no mode, which means mode for this case is none. In case if there would have been one more value like this 1 comma 1, then mode would have been 1, right? And one more dilemma is, see, if all the numbers are exactly occurring once, then there is no mode, and if any number is occurring more frequently compared to the others, then that is the mode. But when more than one number is occurring more frequently and the frequency of both the numbers is same, which means, let us take this example 1 1 2 2 and let us say 3 4, then in this case you can see that 1 is occurring 2 times, 2 is occurring 2 times, and both the frequencies are high and both of them are equal compared to others. Therefore mode are 1 and 2, so 2 modes are there. That is how you should solve such conditions whenever we have such. These are the extreme cases where there can be more than one number with the same frequency and both of them are having the highest frequency, then both of them are going to be mode. In case if we have 3 numbers, then all the 3 are going to be mode, right? And even though it is not in the syllabus, there is one more term which is called as range. So range is nothing but these are the terms in the statistics. So everything is from statistics, but I don't know why they have given it in probability. Anyway, we are never going to use them in computer science. Probably that is the reason they have never asked in GATE. So what is range is, you take the smallest number and you take the largest number and you subtract, you find out the difference, that is the range. So in this case, the smallest number is 1, largest number is 7, and if you find out the difference is 6. Therefore range is 6 in case if they ask. That is it. So these are the examples and the extreme cases that we have seen. Normal cases also we have seen. These two examples are enough for this. Anyway, there will be no questions on this.